Hello and welcome to the Go Cloud Architects AWS Certified Solution Architect Associate course. Hi, I'm Michael Gibbs, and I've been working in technology for 25 years. And during those 25 years, I've had the opportunity to work for Cisco, Riverstone Networks, which is now Nokia, Comcast, and MCI WorldCom, which is Verizon. And I've been considered to be a subject matter expert in global network design, cloud computing, and IT security. And I've been working with others in a teaching coaching manner for over 20 years while working in technology. I am the founder of Go Cloud Architects, and we created this course with one goal in mind. We want to provide the best quality online education available anywhere in the world. And we want to give our students real life skills. We want to make a big impact in your lives, and we want to give our students every advantage possible so they'll be successful in their world. We have an approach. We're going to have no fluff whatsoever. We're going to take all the fluff and remove it because we want you to know exactly what you need for the exams, but also real life. We're going to make everything simple. Our motto is we make cloud computing simple. And for us, we want to know that you have a deep understanding. And if you have to have a deep understanding, we've got to make it to something that's completely understandable. So we do everything we can to take the most complicated technologies and simplify them. And lastly, we're going to start at the beginning. We have no knowledge of your cloud computing background, so we want to give you all the foundational information that you need to make certain that you'll be effective in your current role. So let's begin. So to begin, what is cloud computing and how did we get here? So let's begin with the history of the enterprise network and data center. When I began working in IT, organizations were really just beginning to figure out that technology could be a competitive advantage. And at that point, what would happen is there'd be somebody's computer which would actually function as a server for an office, and then there'd be a couple of connected computers. And organizations said, wow, this enhanced productivity. So what ultimately happened is they began building large networks and large data centers. And what the data centers in those days looked like is they could be 5, 10, 15,000 square feet, filled from floor to ceiling with servers, routers, switches, and an enormous amount of other technologies. And these data centers drew an incredible amount of power, required an incredible amount of cooling, and they required a management staff like you couldn't imagine to try and maintain all these devices. And it was still financially successful for organizations, so they invested more and more in the data center. And they also said, wow, we're getting so much benefit that they started building out networks. And all of a sudden, an organization that had 100 locations now connected all 100 locations to this data center through their network. And that really worked very well. But it had with it the complexity of managing an incredible amount of technology and also having the people that could manage that technology, along with dealing some space, power, and cooling problems that were always challenging. And then computers became much more powerful. With Moore's law, we saw computing power increase exponentially. And as computers became much more powerful, all of a sudden it became feasible to have less computers. So that's where virtualization came in. And the first, early stages of virtualization are kind of blade servers. And what a blade server was you have the server chassis, and you'd have these cards that would be placed into the server chassis. And each card had their own CPU and memory, and they were effectively multiple physical computers inside of a computer chassis. And they worked great. They decreased the footprint of the data center and, to a large degree, the power consumption of the data center. But then processing power got even more powerful. So then we started with the development of a hypervisor. And what a hypervisor does is it enables a single physical server to be partitioned into multiple logical servers. And now that's realistically what we're doing. We're taking servers, we're chopping them up into logical servers through a hypervisor of some kind and creating virtual machines. And that really was the key driver to cloud computing, was the ability to virtualize your network and then actually connect to the network, which is the next component of where we got to cloud computing, which is high-speed networking. When I began working with networking, a 56K leased line could be thousands of dollars per month. And the performance was very slow. So what organizations did is they had their data center, they would build these big offices right near the data center, they would connect them to their LAN, and through the LAN they would get the best performance they possibly could, and then they would have remote offices connecting through the WAN. And that worked well for a while, but it's extremely costly to maintain some of these large networks. Some of these networks would have thousands of remote locations. And in the process, these organizations effectively became their own service providers. They all effectively had their own cloud, their own data center, their own high-speed network backbone, and that was the way organizations worked. And that was the best we could do at the time. But all of a sudden, networking speeds enhanced exponentially, but the price of networking went down. So now that we have really high-speed local area networks, and we can do wide area networks over Ethernet, all of a sudden it became possible to have a gigabit connection from your data center to the cloud, or a 10 gigabit connection, or multiple 10 gigabit connections. And now, in today's world, an organization's office can have such high-speed connections to the cloud that they wouldn't even know that their applications are housed in the cloud. So by housing applications in the cloud, an organization doesn't need to maintain the enormous staff that they would need to maintain if they're maintaining their data center. They have much simpler power, space, and cooling requirements. And we'll talk about it in a minute, but they have a whole lot less technology to build. So this is some of the drivers that actually brought cloud computing into feasibility and reality today. Now we're going to talk about a few more drivers. So we've talked about the key technology drivers for cloud adoption, but now let's talk about the business drivers. So before we discuss the business drivers, I want to define two terms as it pertains to cost. There's capital cost, otherwise known as CapEx, capital expenditures, and there's operational costs, otherwise known as OpEx, and they're very different. And with cloud computing, there's a big shift from capital expenditures to operational expenditures, so we're going to talk about what they are. But one of the key business drivers to moving to a cloud environment is to reduce capital costs. So for organizations that have their own data centers, they have to buy physical servers. They need routers, they need switches, they need firewalls, load balancers, racks, power distribution units, generators, and cooling. And that's just some of the capital expenses. There's others. And they still have some operational expenses. For example, if you have a data center that's got 3,000 servers in it, you need a pretty large IT staff to manage it. And you've got some pretty substantial electric bills, some related to both powering the servers but also cooling the data centers, because these servers don't like it hot and their performance will degrade and the reliability will degrade dramatically under heat. But an organization still has the WAN connections, they have their internet connections, and all of these things get more expensive. Now when you shift to the cloud environment, what you actually get is very reduced capital costs. For the most part, you don't have anything to buy. You're just purchasing, or I should say leasing, the technology on an as-needed basis from the cloud provider. So in this case, Amazon will be charging monthly or daily fees for every service used. So with a shift from the cloud comes a shift from the capital expenses that an organization would face to more operational expenses. Now let's talk about the key business driver to cloud adoption, and that's agility. And in a traditional data center environment, if you need a new server, you purchase a server. If you have a new application, you might need to order 10 servers. Now you might order the servers, they may take a month to build. By the time they're shipped to you, when you get them, you have to put an operating system on them, you need to put all the dependencies for the application and all your applications, and this can take a large period of time. Now with the cloud, all you really need to do is you need to log into your console, provision a server, and that's it. So the agility gain, business-wise, from being able to deploy a new application in minutes versus in days or weeks is enormously beneficial to an organization. So that speed of deployment is fantastic. And whether that's related to a server, a database, a network performance optimization, that's just a competitive advantage that cannot be matched in any environment other than a cloud computing environment. And now we have auto scaling. So without auto scaling, let's say an organization has a web and application server. They have to provision that server for the peak demand it might have 1% of the time. Now in a cloud computing environment, you can purchase the use of a server based on your average computing environment, and the server itself can auto scale by adding additional servers as needed. So you can purchase what you need and then still scale to almost unlimited limits. So not only does that increase agility, it can also substantially decrease costs. With that comes serverless environments where basically you can just deploy an application by uploading your code and have unlimited scalability. And that's really something you can't do without a cloud environment. So the ability to buy unused capacity at a discount if you've got some commuting batch jobs and have a network that's pre-built that you can deploy pretty much anywhere, anytime at a reduced cost over building it yourself are really the key business drivers to cloud computing. Now let's talk about how the AWS cloud is organized. So the AWS cloud is broken into regions and availability zones. And a region is a large geographic area. And inside of each region, there are multiple availability zones. Now many students get this confused. So imagine a region is a part of a continent. An availability zone is just a data center that's inside of that region. So when you realize an availability zone is just a data center, then it makes complete sense that you've got this region, which is a large geographic area, and inside of that area, there's multiple data centers. And each data center is called an availability zone. So since we're talking about cloud computing, an organization is effectively going to create their own virtual private cloud. So what is a virtual private cloud, also known as a VPC? And a virtual private cloud is a private network that an organization purchases from the cloud provider. Now, the AWS network is a shared network, meaning there's multiple customers that are sitting on that network, but they're logically separated. And since they're logically separated, one organization cannot talk to another organization unless they go to several steps to do so, which is something called VPC Peering, which we'll talk about more later. But the point being is AWS can have thousands upon thousands of organizations and none of them can see each other because they're private unless you do some work to enable them to talk to each other. And because each organization's network is private, they can use their own private IP address space. They don't have to worry about overlapping IPs with other organizations. They can be confident their security so other organizations can't see what they have. And it's really just using the AWS network. So AWS has their own network. It's got their own high-speed backbone. They have their own storage apparatus, and they have their own WAN and LAN. So by purchasing, or at least leasing, an organization's virtual private cloud, you're just purchasing access to the AWS network. So let's talk about the two types of cloud architectures you're going to see as a cloud architect. The first type of architecture is a hybrid cloud. And a hybrid cloud is just simply an organization has a data center, but they also connect to a cloud computing environment, meaning they're using both. And why might this be? Let's say an organization has invested an incredible amount of financial resources into building their own data center. They would like to leverage the investment they've made in this technology while still gaining some of the agility benefits that can be gleaned from the cloud. So in many cases, there's a migration to the cloud and people will have a hybrid cloud for quite a while. There are also ultra high performance applications, and there are not many, but there are some applications that literally benefit from being 1 nanosecond quicker than other applications. And just that latency requirement might make it better to have certain applications housed in an organization's data center and then house the rest in the cloud. This is not your typical customer, but there are applications that are that latency sensitive, especially for competitive advantages. Now, when it comes to disaster recovery, let's say you have your environment and you back up your entire environment to the cloud. That creates a perfect low-cost disaster recovery environment, and it's a perfect use case for the cloud. And then some organizations just want to place certain things on their own network and use the cloud for the rest. And that's typically when you'll see a hybrid cloud environment. Now, the next type of cloud architecture is what's called a pure cloud. And if you don't have a data center, for example, an organization has no data center, they have no technology, but they're deploying new applications, new services, a pure cloud computing environment is fantastic. And it's ideal because when you start an organization, you don't completely understand what your technology requirements are. You think you do, But what happens is you may think you're going to get a certain number of hits on a web server, and all of a sudden you receive 1,000 times that. And you just never really know. So the auto-scaling capabilities of a cloud architecture are enormously beneficial to a startup. Now, I mentioned auto-scaling a few times already, and the cloud computing environment promotes near unlimited scalability. So you can know that you can deploy your application with the least amount of resources you think are necessary, but it'll still grow to meet your needs. And that ability is something that can't be offered in any other environment. So that scalability, the auto-scaling that can be done with the cloud is incredibly beneficial for businesses. Now let's talk about the speed of deployment. If an organization has to purchase servers, have the servers shipped to them, and then they have to install their operating systems, find a place for them, put them in a rack, connect them to power, then install their application's dependencies in the application, this can take a long period of time, but with the cloud, you can simply just go to the website and literally click a few clicks, and all of a sudden you have a server. Of course, you can do it via an API, or you can do it via the CLI, which we'll talk about later. But the point is, you can pretty much instantly deploy things as needed. And if you're on the cloud and you have multiple partner organizations and they're also on the cloud, you could just simply peer them and enable them to talk to each other without building other network connections, which could take a lot more time, effort, and money. And generally speaking, a pure cloud computing environment can be cheaper than a traditional environment or a hybrid environment. But that's going to be dependent upon the organization and the application. Generally speaking, cloud computing environments are cheaper than traditional data center environments. But I've covered this before. You need to understand that with traditional data center environments, there's a lot of equipment to purchase, which is a capital expense. When it comes to a cloud computing environment, you could be paying by the minute, the second, the day, what have you. And you have much higher ongoing operational costs. It's a shift from capital expenses effectively to operational expenses. So let's talk about connecting to the cloud. If an organization is going to place their data in a cloud computing environment, which is effectively outsourcing their data center, then they need to be sure they have reliable and high performance connectivity between the organization and the cloud computing environment. So the first way we're going to talk about this is with a direct connection. And a direct connection is going to be your highest performance option, and it's going to be best for most customers. And what a direct connection is, it's realistically speaking, it's a wire between the cloud provider and your organization. So there's direct connectivity in between it. And because it's effectively a wire which will be used for Ethernet, realistically speaking, you know exactly the performance you're going to get. If you purchase 1 gigabit per second, you're going to get 1 gigabit per second because it's effectively a wire. This is different than a VPN, and we'll talk about why VPN performance is typically lower. But for right now, understand this is guaranteed performance. Now, it's not just guaranteed performance in terms of bandwidth. It's going to be guaranteed and consistent performance with regards to latency. You'll have an SLA that says latency will be less than a certain amount, and the latency will be consistent. This is very important to have consistent latency for voice or video applications because these applications are very sensitive to something called jitter, for which that is realistically speaking just variations in latency. If you always have 5 milliseconds of latency, that's typically not a problem. But if you have 5 milliseconds, 50 milliseconds, 10 milliseconds, and then 5, it's very hard for real-time applications such as voice or video to perform reliably and properly. So the direct connection gives you your best performance and is the best option for high availability, high reliability applications. Now, the next method to connect is actually with a VPN connection. And what a VPN connection is an organization connects to the internet, and AWS connects to the internet, and they have an encrypted tunnel in between the organization and the cloud provider. Now, this is typically cheaper, and the reason it's typically cheaper is you're not buying a private connection between the data center and the cloud. All you're buying is a connection to the internet. Now, because the internet is public, in order to maintain privacy, you have to encrypt that data. So the data will be encrypted via something called IPsec, and that'll encrypt the data, and it'll do a few things. It'll make sure that the data has maintained its integrity, that it hasn't been changed along the way. It'll enable the organization to verify the sender and the receiver, so you know it's the organization connecting to Amazon. And it'll also facilitate something called non-repudiation. Because of the way the messages are sequenced, if the organization connects to AWS, the message can't be changed, and the organization can't say they did not make a trade, they did not purchase a product. You can guarantee, because it's encrypted data and the data is measured, that you know that the person on the other end is who they say they are. You know that no one else can read it along the way. And if you're using it for signatures and the such, you can guarantee that the person can say it, but you also know that it hasn't been changed. Imagine trying to send a $1 million purchase order and have it come out as $1 billion because someone changed it along the way. So that's really why you're using encryption. Now, because you're using a VPN encrypting the data, you can use your private IP addresses that are going to be tunneled inside the VPN connections. So that enables you to have a private network across the public internet. Now, here's the thing with VPN connections. They're inexpensive, but there's really no bandwidth guarantees. And here's the reason. If you purchase a gigabit connection to the internet, you know that you have a gigabit connection to the internet. But the internet is comprised of multiple internet service providers and multiple other organizations called autonomous systems. And just because you can guarantee performance to the internet doesn't mean the internet, which is owned and managed by many organizations along the way, they don't have to prioritize your traffic. So you can get an SLA of certain guarantees to the internet, but once it's on the internet, whatever happens, there's no guarantees. It's best effort delivery. So with a VPN environment, you're going to have variable latency. And this can work for some applications, but not others. So you, realistically speaking, need to know what are your latency and performance requirements. If you have tight demands on latency and on strict performance requirements, a direct connection is what you're going to need to use. If you have much looser requirements with regards to availability, performance, latency, a VPN connection would work well. So the organization will have to determine whether it makes sense to purchase a direct connection or whether they can get away with the VPN. Now, let's talk about high availability. There's this saying that's called 1 is none and 2 is 1. Realistically speaking, when it comes to availability, you need at least 2 of everything. I mean, literally everything. If you're using a router, you want 2 routers, you want 2 power sources, you want 2 connections over 2 different providers, and the list could go on. So realistically speaking, most organizations that require high availability will have a direct connection backed up by a VPN connection. So that's your typical high availability architecture when it comes to connecting to the cloud. Now that you know how to connect to the cloud, let's talk about accessing the cloud and managing the cloud. So the first thing you're going to need to do if you sign up for a cloud provider is you're going to have to manage your virtual private cloud. So with AWS, realistically speaking, you have 3 options. The easiest option for most cases is to use the management console, and that's quite simple. You're going to log in to the AWS website, and inside there, there'll be a console. Inside the console, you'll be able to select what you choose to do, and there'll be help along the way. So this is the easiest option for most new people, especially because of the abundance of help that's available for you. Now, the next option is going to be to do it via the command line interface. So in this environment, what'll happen is the organization will set up a secure shell or SSH session between a terminal at their local facility and between the between the AWS cloud, and you'll be able, via the command line, to actually be able to monitor as well as configure and make changes to your systems. And that also works very good. Highly efficient, very quick, but you absolutely have to know the CLI and you have to know everything you want to do before you do it, because there's not going to be any help. It's not going to be an easy to click website. And the other option is to do it through the software development kit. So it's quite possible, and many large organizations configure things through the API or programming interface through the software development kit. And that is your perfect option, but you realistically speaking need to really know what you're doing. And this is for larger scale deployments. Now, that's typically the way most servers are managed, but if you have a Windows server on the AWS cloud, and many organizations have Windows servers, whether it be for Active Directory or some other Windows-based application, then you're going to have to use a remote desktop protocol, and that's going to be something where basically you'll be able to see the remote desktop. Windows typically doesn't do well with a SSH configuration like a Linux or Unix system, so when it comes to dealing with Windows servers, you're going to be using Remote Desktop Protocol, also known as RDP. Let's talk about storage on the AWS cloud. So before we get into the types of storage, let's first define storage. And storage is the environment where you're going to keep an organization's data. So we like to define storage in terms of volatile storage and non-volatile storage. Volatile storage is something that goes away with a reboot. So for example, the storage that comes with an instance storage is volatile, meaning as soon as you reboot or terminate the instance, all the data that's there is gone. So now you know that instance storage is volatile. Don't store anything critical on instance storage. And then we have non-volatile storage, and non-volatile storage stays there after the system is rebooted. So for anything that matters, you're going to put your data on non-volatile storage. And storage is an absolutely critical component to your VPC, and choosing the right storage options based on whether you need host storage, network file storage, or high performance storage can be the matter between an application being successful and an application being a failure. So we'll cover those types of storage in depth, but let's first talk about the types of storage. So the first storage we're going to talk about is block storage. Block storage is a highly efficient, high performance form of storage. And with block storage, you take the data is chopped up into little blocks, and each block has an identifier. And the data is reconstituted based upon the identifier when it's needed. Now this scales well and it's extremely high performance. The reason it's so high performance is blocks can be placed anywhere on the storage array that's most efficient. So by being able to place the blocks anywhere that's most efficient and then being able to reconstitute them on demand by the block identifiers, you're getting really good high performance storage. And we'll talk much more about block storage when we talk about EBS or elastic block storage. Now we'll talk about object storage. And object storage is a bit different than block storage. In block storage, data is broken down into blocks, but in object storage, data is broken down into objects. And each object will have its own unique identifier, and each object will have metadata. And the fact that each object has metadata gives you some really interesting things that you can do with object storage, and we'll talk about that much more when we talk about Amazon S3. And then there is file storage. Now your file storage can be attached to the host or it can be on a network. And typically we think of file storage as traditional storage. It's the hard drive that you have in your computer system. And these are typical volumes that can be formatted based on what a host would use. For example, a Windows host would use NTFS volumes. Those are the three primary types of storage used on the AWS network. So let's begin by discussing Amazon Simple Storage, otherwise known as S3. Now, S3 has a tremendous number of use cases on the AWS cloud, and it's typically used for backup and archival of an organization's data, static website hosting, distribution of content, media, or software, disaster recovery planning, and with the integration of things like Redshift, big data analytics, and datalakes. So because an organization's lifeblood is its data, anytime you have a lot of data that you're going to store, you're going to have to make sure your data is secure. So if you're going to secure your data in an S3, realistically speaking, you have two options with regards to data security. You can create a bucket policy, which is by far the preferred method. And this is very granular, and it's based upon IAM, and you can determine who can access what and what they're allowed to do with the data in a very granular manner. Now, the alternative is more of an access list, but this is really not so granular. I mean, it gives you the ability to do read, write, or full control like typical Unix type permissions, but you've got much more security options with a bucket policy. Now, S3 is used for a wide variety of use cases, as I mentioned. So they also have multiple storage classes, and each storage class has different use cases. So we'll begin with Amazon S3 Standard. So the typical S3 that you think about is S3 Standard. It's very high availability, it's very high durability, and it's very high performance. And I'm going to repeat that again. It is extremely durable data, meaning it's 99.99 all the way to 9 places after the 99. Which is considered to be 11 nines durability. So that means that the data is going to be there. and not be destroyed, even if it's temporarily unavailable. And the data is 99.99% or 4 nines available, meaning when you actually want to use the data, chances are pretty strong that it's going to be there for you. But it's durable enough that even if it's not available at that one time, it's extremely likely that it'll be available for you later. And you're going to use S3 for data standard for data that you're going to use on a typical environment. So this is for frequently accessed data. It's also the highest price of the S3, but if it's data that you're going to use on a consistent basis, this is by far your best option. Now, there's something called S3 infrequent access. And what S3 infrequent access is, it's S3, but they give you a discount, but you actually have to pay when you retrieve your data. But it's still incredibly high availability, it's still incredibly durable, and you're going to use this when you have data that is very important to your organization, but you don't need to access it very frequently because you're going to pay every time you access it. So if it's frequently accessed data, it'll cost too much to use as data storage, but if it's infrequently accessed data, this is going to be a great option for you. Now, for people that need data, but they don't need it to be as completely available and they're still looking to save costs, they can do an Amazon S3 infrequent access, but it's only in one zone. So it's going to be reduced availability storage at a lower price. And this is good for data that you may not need critical instant access to, that you don't frequently access, because it's going to give you some better pricing for the reduced availability. Now there's a new feature and function called S3 intelligent tiering. And what that is Amazon will actually monitor how you use your data on S3, and it will move your data to the appropriate storage class, meaning if it's something you don't use almost ever, it'll move it to S3 infrequent access. If it's something you never use, it can move it to other forms for you as well. But we'll talk about those other forms right now. So the last two forms of S3 is Amazon S3 Glacier. And Glacier is really for deep archival purposes. And traditionally speaking, you put your data on Glacier, you just don't access it because you pay for a retrieval fee when you need it. And when you need your data, it's going to be multiple hours, 3 to 5 hours on average. Now you can pay an expedited retrieval fee to get it sooner, but you don't put anything on Amazon Glacier that you're typically going to need. Now you can do a vault lock option with Glacier. So let's say you're a healthcare institution or a financial institution and you have to store records for a certain number of years. With the Glacier vault lock option, it'll put it in an immutable vault, which means the data can't be modified. So you pop it in, it can't be changed until you take it out. So that's really good for regulatory environments. So some things to know about Glacier is it's just very low cost, but you have to pay for data retrieval. So you have to understand all the types of data that you're using when you're using S3 to pick the right option. Because when it comes to cloud computing, you can easily have very high ongoing operational expenses if you make the wrong choices. Now let's talk about lifecycle management. In order to save costs and make the best use of their data, you can do what's called lifecycle management with S3. And let's talk about this typical use case. It's very frequent that organizations have some fresh data that everybody needs to use for a period of time. And then they have some data that some people need to use for a period of time. And then they have some data that they need to maintain for archival purposes or future machine learning purposes. So they want to save the data, but they're almost never going to use it. So what you can actually set up is you can set up lifecycle management. For example, let's say you need to use your data every day for 30 days. You could pop it on standard S3. Now after 30 days, you might only need that data twice a month. So you can then migrate that data automatically with lifecycle management to S3 infrequent access. And let's say after a period of say 30 days or 90 days, you no longer need that data, but you want to maintain it, you can have that data moved to Glacier, in which case you'll pay the least amount of money to store the data, but you'll still have access to it. So let's discuss protecting your data. So there's a few options to help protect your data, and one of them is S3 versioning. And what S3 versioning is, when you take a file and you store it into your S3 bucket, it creates the file with a version number. Now, if an organization updates or modifies that file, S3 creates another version number. And then if you modify the file again, S3 will create another version number. So every time a file is modified, S3 will store another version of that file. And that way, if one of the files were to be lost, at least you have all the other versions. Now, an excellent way to protect very sensitive, important data for which the business is relying on is with S3 multi-factor authentication delete. And here what goes on is if you're trying to delete a file, it will use a multi-factor authentication delete to make sure that you're the right person and you truly want to delete that file. So here's how it's going to work. A user tries to delete something in an S3 bucket. They'll receive a challenge which will ask them for a one-time password, if you will. It could be an authentication device, it could be a text message, but the point is, with doing it this way, at least you receive a challenge so they know that you are actually you trying to delete it. Then now you'll use your authentication response, which is the one-time password that you'll use. You'll send that challenge, and if your challenge is accepted, the file will be deleted. So this is really a two-step process. It's first making sure that you want to delete the file in case it's accidental, but it's also making sure you are you instead of you being a hacker. Now, when you organize data in S3, it's a little bit different than traditional file storage. So S3 is object storage and not file storage. And S3 is organized a whole lot like a database instead of file storage. And some of those S3 database type features become very useful when it comes to some big data analytics and some other things which we'll talk about later in the course. So S3 is completely flat storage. Anything that's in your bucket is flat storage. So what happens is when you store something new into an S3 bucket, there's a pointer in the database-like structure that shows how to get to your data that's stored in this flat storage. And because of that, you have the opportunity to do incredible things in the big data environment and other environments and run SQL queries on your data. But that's, again, we'll cover that more at a later portion of this course. But understand that S3 is more like a database than traditional file storage. But if you want your S3 to feel like traditional file server or file storage, you can use some tricks to make it happen. For example, you can use a / or a / to as a delimiter to make it feel like Unix or Windows-based storage for the user that's trying to retrieve their data on S3. So anytime you have data and the data is valuable to your business, or you might have some business secrets in that data, you need to protect that data. One of the best ways to protect your data is through encryption, and you can definitely encrypt your data on S3. So you have to protect sensitive information, because if you don't, it'll at some point be compromised, and if trade secrets are lost, an entire business can be lost. So data protection is absolutely essential. So encryption is a means to make the data that you have unusable to anyone unless they have the decryption key. And brief overview of encryption. What encryption typically does is it takes a specialized key and it takes that key and it runs it through a mathematical encryption algorithm, and then it decrypts your data. And the data will be, like I said, unusable, and then you need that key to actually decrypt the data on the back end. And that's how IPsec works, that's how VPNs work, but also that's how many things in blockchain work, but that's also how you want to protect your data. And we cover encryption algorithms in much deeper depth in networking and security courses. So for now, understand that encryption makes your data unusable to anybody without the decryption key. So if you want to encrypt your data on S3, there's really two ways you can do it. You can encrypt it on the client side before you send it to S3, or you can encrypt it on the server side. So let's talk about the first type of encryption keys and the way you can use them with AWS. The first one is called the SSE-KMS system. And realistically speaking, this is where the customer manages their own encryption keys, but they're using the AWS key management system to do it. And the AWS key management system is a full system to manage keys, rotate keys, and really take a lot of the overhead away of managing encryption keys that occurs when you're using encryption in a business environment. So with this environment, the user manages the master key, and the key management system will basically make a data key, and it'll manage it, and it will provide an audit trail of how, when, and who accessed the data. So this is a really great way to do things if you want to manage the encryption key. Now there's also another version called SSE-LKMS S3, and that's where AWS manages all the keys. And this is a complete key management solution. So what happens is the key management system makes the keys, it automatically rotates the keys, and every object is actually encrypted by a unique encryption key. So this is a great automated way for key management, but some businesses, for security reasons or regulatory reasons, may need to manage the keys themselves. And for those reasons, some people might want to do, customer managed keys. And let's talk about the last option, and that's going to be SSE-C, which is customer provided keys. And in this case, the user will have complete autonomy over their security keys and encryption keys. So they'll have complete autonomy over all keys, but then again, they also have to manage the keys and all the overhead associated with key management and encryption of your data. Let's discuss tuning S3 for optimal performance. We're going to be discussing pre-signed URLs, multi-part uploads, and cross-region replication. But let's begin with pre-signed URLs. So you have to understand that everything that you store on S3 is private. And if you want to share data, you're going to need to provide access to the data to anyone that you want to share the data with. And the simplest and easiest way to do this is to just generate a pre-signed URL. So what happens is, from your account, you'll create a URL, and it's going to use your own encryption key. And it's going to create that URL, and then you'll share that URL with the person that you desire to receive the data. And they'll have access to that in a secure manner and a temporary manner. So you can temporarily provide very secure access, and it's the simplest means to do this. Now, when you're using a pre-signed URL, the URLs will expire, and the expiration length is determined based upon how you signed the URL. So if you sign the URL with an IAM instance profile, it's going to expire in up to 6 hours. Now, if you signed it with an AWS security token device, the expiration time you can make up to 36 hours. Now, if it's already an IAM user, then the data is good for up to 7 days, or you can configure it to be the URL up for 7 days. And if it's a temporary token, it expires as soon as the token expires. Now let's talk about multi-part uploads. So S3 is some pretty interesting storage. It enables you to store files as big as 5 gigabytes. But a 5 gigabyte file transmitted over the internet, there's just so many things that can go wrong. You can reach a congestion point on the internet, data can be lost, and the whole file can be lost. So it is recommended that any time you need to send a file that's greater than 100 megabytes, that you actually use a multi-part upload. And what happens with a multi-part upload is the file is broken down into many little files, and the little files are sent. And once all the little files are received, the data gets reconstituted into one. But if any of the mini files get lost along the way, they're just retransmitted instead of retransmitting the entire file. So that's how this is so much more efficient, and it's recommended anytime you have a file larger than 100 megabytes. Now let's talk about cross-region replication. As we previously discussed, AWS has multiple regions. You can have an S3 bucket, say for example in the East Coast region of the US, and want to ship it to an Asian region. And you might do this for 2 reasons. One is you may have a main business in both the US and Asia. Another reason you might want to do this is you've got a tremendous number of customers in Asia that are using an S3 based website. So by bringing the data to the website that's hosted off S3 locally to Asia, it'll be much faster for your Asian customers than if they had to reach back to the US for the data. The third reason you may want to do this is just disaster recovery purposes. Have your data literally backed up automatically by the way, into another region geographically that's far away. What a great way to protect your data. So just understand cross-region replication basically takes everything in your bucket and will replicate it to another region. So that's cross-region replication, and great way to really protect your data and make sure you have a perfect backup at all times. The next type of storage we're going to discuss is instance storage. So instance storage is just storage that's attached to an EC2 instance. Now, you have to remember that instance storage is volatile, meaning that as soon as you reboot or terminate an instance, all the data that's on that instance storage is lost. So as a boot VM, you could possibly use instance storage. Having said that, you can't store any data there, at least if you want to be able to access that data later. Now let's talk about elastic block storage. Elastic block storage is block storage on the AWS cloud. And elastic block storage, which you'll hear called EBS, is a very high performance storage. And it acts like a virtual hard drive. And you typically would use this in an EC2 instance when you need high performance storage or storage that does not go away upon instance termination. Or you would also use it with your database, because it can be some very high performance storage, and certain databases need access to very low latency, high performance storage. And this is also for mission critical use. It's very high availability. It's 5 nines available, so you're going to have access to your EBS storage when you need it. It's optimal for high throughput and high transaction workloads. And you're going to have multiple options, performance options with EBS volumes, which we'll talk about in a minute. Now, EBS volumes are associated with a single availability zone, and you really need to remember that they're associated with a single availability zone, because that'll come up in examinations, and it'll also come up in actual practice. And EBS volumes are actually automatically backed up to another availability zone. So, great way to make sure that the volume itself is completely backed up to another location should anything happen to the location where your data is stored. And EBS volumes are actually backed up via a snapshot. So basically what happens is an image is made of the data in the form of a snapshot, and it's typically stored on S3. As I mentioned, there were multiple options for the amount of performance that you can get from an EBS volume. And the way that occurs is you have to choose the correct EBS volume type for your application. And there's volume types based on different levels of performance requirements, specifically latency and throughput. So latency is, realistically speaking, how fast the disk can be accessed in terms of the number of times in and out per second. Whereas throughput is the amount of data that can actually be moved, measured in terms of megabit per second. And these are very different, and you need to make sure that you have the right volume type to support an application's requirements. So let's talk about the first and overall best performing volume type available, and that's EBS provisioned IOPS. And here's what you need to understand. With this option, you can actually procure ahead of time the number of input and output operations per second that you'll receive. And by doing that, you can make sure you have guaranteed input and output operations per second, which means lower latency. And if you've got an application sensitive to latency, this is the volume type you're going to be using, because it's giving you guaranteed performance in terms of latency. It's also the highest throughput of the options. So if you've got something that needs high throughput and low latency, this is your perfect volume type. And again, this is going to be used often in databases, because databases are very latency sensitive, but this could be used for any kind of application that could be latency sensitive, like gaming, for example. Now, let's talk about the next volume type, and that's going to be EBS General Purpose SSD. And this is general purpose SSD storage. It's got a really good blend of price for performance, and you might actually use this as a boot volume instead of using instance storage, because EBS volumes are non-volatile, meaning they don't go away with instance termination, they stay there. So this could be a great way to actually build a boot drive that's very high performance for one of your computing instances. And this type of volume is exceptional for transactional workloads because it's moderately low latency and it has still relatively good throughput. And another place we'll use this type of volume is, let's say you have a production database and production web application running on provisioned IOPS, and this is your lab environment where you're going to stress test it, but not to the ability to at least the levels that occur in the production environment. You can use the EBS general purpose SSD as a way to save costs in your test environment, as opposed to using the provisioned IOPS that you're using in production. Now, the next type of volume we'll talk about is magnetic storage. And this is EBS throughput optimized HDD. And this is relatively low cost magnetic storage, but it's got some relatively good throughput. So if you've got an application that needs to actually send and receive a lot of data, but it's not sensitive, this is an excellent option. And it's fantastic for log storage. And it's great when you have a lot of data that's going to be sequential reads, sequential writes, and it's got good throughput, but not for latency sensitive applications. And the last VM type we'll talk about is EBS Cold HDD. And this is the lowest cost option you can possibly buy in terms of storage of EBS volumes, but you're going to use this for workloads that are not accessed frequently. So low performance access for data that you want to store and maintain storage because you don't want it to go away with instance termination, but it's not for data you're going to access frequently. The next type of storage that we'll discuss on the AWS platform is the Elastic File System, also known as EFS. And the Elastic File System is network storage. So where an EBS VM looks like a virtual hard drive to a system, this is network file storage. In fact, it's extremely similar in structure to the NFS or Network File System that was originally developed by Sun Microsystems, which is now Oracle. And this is and NFS is running on millions upon millions upon millions Unix and Linux systems throughout the world. And it's also important to know that EBS volumes are highly scalable. In fact, they're so scalable that they actually grow as needed. So you don't ever have to worry about running out of network storage on an EFS volume. They're very high throughput, they have very high IOPS, so they're low in latency. So these are great performing network storage. And it's also something called POSIX compatible. And what you really need to understand about that is it means that it'll work with legacy systems. Now, the next type of storage we'll mention is Amazon FSx for Windows. And what Amazon FSx is for Windows is it's fully managed, high availability Windows storage. And because it's Windows storage, it uses the SMB or Server Message Block Protocol. And this is supports, Microsoft features and functions such as Active Directory. So for organizations that have highly Windows-dependent workloads that need Windows-dependent type storage, Amazon FSx for Windows is your option to use. So let's discuss scalable means to send an organization's data to S3. The first option is with a storage gateway. And a storage gateway is an appliance that you place in your data center that directly connects to Amazon S3 services. This appliance is actually a virtual machine. But what happens is the organization puts this virtual machine in their data center, and the virtual machine to local servers feels just like a traditional file server. So the organizations have their servers, they connect to this file server, but really it's a storage gateway, and then it copies all the data from the organization's data center to Amazon S3. So for an organization that wants to use this as a backup disaster recovery purpose, it will work perfectly. But also it would work, let's say an organization has a lot of data, they're planning on migrating to the cloud. It's going to take a lot of time to copy it over the network connection. They put this storage gateway in and data is asynchronously replicated all the way to S3. Now, the other place where you would use a storage gateway is for a hybrid cloud, where an organization has a data center and they also have a cloud, and this way they can keep their data synchronized. So the storage gateway is a really great way to get your data to AWS in a scalable manner. Now, I described the file gateway, where it's copying files and sending it to the AWS data center. Now, there's also an option to do this VM gateway in a cached mode. And what ultimately happens is you would then place the virtual machine in the data center, and let's say an organization's data is stored on S3. What'll happen is, as users request information from this storage gateway, it'll be pulled from S3 to the storage gateway and then distributed to the user. But if it's frequently accessed content, for example, and say another user requests the same data from S3 that the previous user would have, that data will already be sitting on the storage gateway in terms of being cached. So it'll operate like a web cache. So the point is new requests obviously will have to go to S3 and then be brought to the storage gateway, but for data that's frequently requested, it can be stored locally on the storage gateway in the organization's data center without having to traverse the WAN to actually get to the AWS cloud. Now, the storage gateway is a great way to migrate data if you have sufficient network bandwidth and you have sufficient time. Now, there are times where an organization has to move or migrate a tremendous amount of data in a short period of time to the cloud. And Amazon has a solution for it, and it's called a snowball. And here's what the snowball is. Amazon has these highly ruggedized computers with a massive amount of storage. And what happens when you have a tight time frame to migrate your data, or you have a long time frame, but you don't have anywhere close to the network bandwidth that you'd need to transfer all your data, what you do is you request one of these snowballs. So Amazon will ship you one of these snowballs with their massive storage capacity, and you'll place the snowball on your network using a 10 gigabit Ethernet port, and you'll copy all of your data from your systems to the snowball, or multiple snowballs if you've got a lot of data. And as soon as your data is copied to the snowball, you'll contact AWS, and then the package or the snowball will get shipped back to AWS. And when the snowball gets back into AWS's possession, they will copy it onto S3, and now you have your data on your VPC on S3. Now, AWS offers another option for organizations that have tight timeframes and moderate amounts of data, but not to the level where they would need something called the snowball, and that's called the AWS Import Export Service. And realistically, what happens, you take an external hard drive, you copy your data to it, and this could be multiple external hard drives, and then you ship the data to AWS, and then the employees at AWS take the data from your hard drives and they copy it onto S3 for you. So, in this module, we've talked about the types of storage: block storage, object storage, file storage. We've talked about S3, we've talked about EBS, we've talked about EFS, we've talked about FSX for Windows, we talked about storage gateways, the AWS Snowball, and the AWS Import-Export Service. What we're going to do is we're going to create a budget. And the reason we're going to create a budget is we want to train as efficiently as possible in every way, from a time perspective, but also a cost perspective. And I don't like to receive surprise bills at the end of the month, and I assume no one else does. So by setting a cost budget, we'll be in a position to know that what we're going to spend and be able to plan for what we're going to spend and make sure we don't overspend. So as soon as you log in, we're going to go to the Management Console. And inside of the Management Console, you'll see a section called AWS Cost Management. Inside of there's going to be an area called Budgets, and that's where we're going to click. So when we get to this area, we have the opportunity to create or manage a budget, refine an existing budget, or add a notification to a budget that already exists, assuming we haven't set it up yet. But in this case, we're going to create a budget. And we're going to create a cost budget because we want to be able to monitor our costs and get alerts once we receive a certain threshold. So now we're just going to set our budget, and we're going to call this the Go Cloud Architects budget. And in your particular case, it'll be something different. I'm going to have this every month, and I'm going to set a fixed amount. I'm going to set mine for $50. You, realistically speaking, don't need to go there, but I'm going to go there because that's typically what I would expect to spend given my situation, because I'm constantly doing labs. From here, we're just going to configure the thresholds, and we're going to set up the threshold to know when we reach a percentage of the cost. In my case, I like to get a little more notifications so I can see exactly what's going on. So when I reach 50%, I want to be notified. And I'm going to just set up a very simple email. Now, I could set this up with SNS, and there's other opportunities to do things with chatbot alerts, but I'm just going to do a simple email. And that's the email address for my company, so I'll have that as the location where it's going to set things up. And here you can see, quite simply, I've got a budget. I've set it for $50 a month. As soon as I reach 50%, which is $25, I'm going to get an email. And that's it. Now you've got a budget. It's completely set up, and you'll be alerted. So pick something that you can afford. And now it's time to start beginning our labs. Welcome to the program, welcome to the labs, and we hope you have a great time and learn a lot. to be doing is we're going to be creating an S3 bucket, just a basic S3 bucket, so you know how to do it. And in the future, we'll do more things with S3, like create some lifecycle policies and enable versioning and a few other things. But for right now, we're going to work through a very simple creation of an S3 bucket. So log in, and after you log in, go to the management console. And under storage, you'll have your various storage options. And we'll talk about much more about them later. But you've got your S3 or your simple storage, you've got your elastic file system, you've got your file system for Windows, you have your S3 Glacier, which is long-term storage for things you don't need all the time, at least access to. We have the storage gateway, and we'll talk about them much more, but that's a way to connect your data center to your AWS cloud and share information. And then we'll talk about backup options. But for right now, it's just S3. So we're going to go to the management console, and we're going to click on S3. And very simply, it's going to give us a tool in terms of how to do this. Now we're going to go and create a bucket. And you have to name the bucket. And since we're Go Cloud architects, we're going to use GCA for our abbreviations, and we're just going to call it bucket. This is a very simple exercise to just learn. And you can, at this point, pick the region that you choose to be in. I'm going to stay in the US East Ohio area. And if you wanted to enable bucket versioning, which we'll talk about a lot more, you can add tags to help know what's going on with your storage and your types of things that are there. And you can enable or disable encryption here. But for right now, we're just going to simply create this bucket. So we're going to click Create Bucket. Now you can see we have a bucket. That's it. So let's do something with this. Let's place a file in our bucket. So we're going to click the bucket. And over here, it's going to give you a great menu option. Now we're going to click Upload. And from here, we're going to just add some files or folders. I'm going to do it from my computer. And I'm going to click Add Files. And I have a cover of an ebook that we give away for free, this ebook. So I'm going to upload that cover to my S3 bucket. And then I'm going to click this. And then I'm going to click Upload. And there you have it. We've created an S3 bucket with some things inside of it, specifically my book. And you can click on the bucket, and you can see what's inside there. And of course, you can look at bucket properties, which will tell you what's going on about the bucket. Permissions, which we'll talk about later. And then you can see other types of associated things. But there you go. Now you have a simple means to create a simple S3 bucket. What we're going to be discussing is something called S3 versioning. S3 is a form of object storage, and by nature with object storage, anytime a file which is broken down into objects is modified, object storage typically creates a new object, which can get very expensive in terms of filling up space. Having said that, it can protect you against accidental deletion or file corruption. So let's say we have a file, and the file is going to be accessed and modified on a daily basis. S3 will actually store every version that existed. So for example, if a new version gets corrupted, you can just revert to the previous versions. Now we'll also talk about throughout this course other ways, such as cross-region replication, to make sure your data is in two places in case your data is actually corrupted. But in this particular case, versioning is a wonderful way to make sure you have a backup of the previous copy of your data. So very simple to set this up. We're going to go to the management console once again. We can go to storage S3 here, or because we were just there, we can click on S3 here. And from here, we're going to access our bucket. And if we look at our bucket, it's going to give us some information about our bucket. And that's all we need to do. So we're in this position, and let's look at the properties of our bucket, and we can see what's going on here, but we haven't set up versioning. It says versioning is a means to keep it up. So let's edit our versioning configuration, and let's enable versioning, and then we'll click Save Changes. Now, that's it. Every time we modify this file, it will create a new version of the file. And if we modify this file 10 times a day, it'll create 10 new versions. And if any one of those versions get corrupted, we can revert back to a previous version. So that's what you need to know about versioning. very simple to set up, and it is a fantastic way to protect you against accidental or malicious data loss. What we're going to be doing is we're going to be setting up something called S3 Lifecycle Management. And I'll explain what that is. There are times where an organization has new data, and they access that data really frequently for a period of, say, 30 days. And then that data that's accessed very frequently becomes accessed infrequently, but it's still occasionally accessed. And by taking your data out of your traditional S3 bucket and sending it to S3 infrequent access, you will actually be able to save quite a bit in terms of cost, assuming your data is accessed infrequently. Like we talked about in the lecture discussions, if every time you request information from S3 infrequent access, there's a charge for it. So if it's almost never accessed, it's a great way to save some money by placing your data into S3 infrequent access, and you'll have immediate access to the data. You just have to pay a retrieval fee. And then you might find that you don't need access to that data after a period of 30 days, 45 days, almost never again. But you still might need to keep that data. For example, you could be in the healthcare or the banking industry or another regulated industry that mandates you keep data for 7 years. So you need to hold on to it, but you want to do it in the cheapest way possible. So you could use Glacier. You might also be running some machine learning applications and want to save the data that you've gleaned in your S3 bucket for future training data for machine learning. So these might be some of the reasons you'd like to keep historical data. Or you might use it for other business intelligence applications where you can look at trending data and things that you've done in the past. So that's why we would use lifecycle management, to make sure that we save our data in the most cost-effective means possible. So we're going to go to the management console. And what you can see is we could easily click on S3 here, or we could look at recently visited services. And we just created an S3 bucket, so I'm going to just click here to make life easy. So here you can see the bucket that we created in the previous lab called the GCA bucket. And in the bucket, you can see the one file, our book cover template that we uploaded. So let's talk about some lifecycle management and how we're going to set that up. We're going to click on the Management tab. And under the Management tab is going to be quite simple. We're just going to click Create a Lifecycle Rule. And we can call this rule anything we want. So let's take it, let's call it S3 Data Management. And we're going to create some kind of a prefix to limit it. In this case, we're just going to do something very simple. And something very simple, we're just going to call it S3 Bucket Access. Now, when you do this, you need to come up with a tag. And when you're creating tags, it enables you to identify things that are going on, or you can limit the scope. For example, you could create a tag and tag things as secret, and then use that to make sure that certain things aren't taken outside of a region. For example, you might be working in a government environment, and the government may mandate that things are not copied outside of the US. For example, if you're in the US environment, and you can create a tag, and then you can create rules later based upon those tags to protect your data. But in this case, we're going to come up with a very simple tag, and we're going to call it S3 Data. But we're actually going to put that in the value, and we're going to list it over here as the name. So, like a database kind of environment, it goes with key values. So there we go. And then I'm just going to create a rule. And we're going to transition things. So now what we're going to do is, let's say I have my data on my standard S3 bucket, like I do. And after 30 days, I want to take that bucket, because it's not used that often, and I want to send it to S3 infrequent access because it's cheaper. So what I'm going to do is I'm going to pick my storage class, which is going to be S3IA, and we're going to put 30 days. And it's also pretty common for people to keep their things in S3 for a period of time and then send them to Glacier. And the reason they're going to send them to Glacier is they want to create an environment where it's cheap to store things for a long period of time that they're not going to be accessing frequently. Now, bear in mind, when things are on Glacier, it's going to take a period of time to retrieve them, hours. Now, you can pay an expedited retrieval fee to get them sooner, but it's going to take hours to get your data. We're going to acknowledge that this lifecycle rule will increase the cost, especially if we're transitioning a lot of small objects. And I'm going to create the rule. And after we create the rule, it'll check and see if we've done everything properly. And if we've done everything properly, the rule would be created. If not, it will throw an error. And as you can see, the lifecycle management rules have been completed. We have data that's going to go to from our current place where it's there to 30 days later to S3IA to 60 days it's going to go to Glacier. That's it. That's how you set up lifecycle management on S3 buckets. This video is about S3 cross-region replication. And there's lots of reasons you might want to actually replicate your data across regions. Region 1 could simply be, if you have your data in one region and that region were to go out and be compromised, you'll still have your data in another region. But most frequently, the reasons people are setting up S3 cross-region replication is actually to make sure that their data is in a bucket in another region. And they're going to do this because in a lot of cases, people host static websites through S3. And when your website is hosted on S3, that you're going to pay for data transfers across regions. So let's say, for example, you have a website in the East Coast of the US, and you've got a lot of customers on the East Coast, and you also have a lot of customers in Asia. If your Asian customers are accessing your data from an S3 bucket that's sitting inside of the US, there'll be latency that's associated with those long cross-region transfers. And some of this will get better with CloudFront, which we'll talk about later, but there'll be a latency issue. Plus, there's also going to be a cross-region data charge every time that information is accessed. So by getting your data closer to the customers, it may be more cost-effective if you don't have to pay the cross-region charges, and that's going to be based on the amount of data that's being transferred, but it will also give your information in another location for extra redundancy, and it can improve performance because latency will be less as you don't have to travel so far. So here's how we're going to set up this S3 cross-region replication. The first thing we're going to do is we need to have a second bucket to transfer our data to. So we're going to do so. So we're going to create a new bucket, and we're going to call it GCA bucket 2 because I have a GCA bucket 1. Now I'm going to place this in a different region. For our purposes in the lab environment, we're going to create US region West. We'll pick something and say California. And we can copy our configuration files from a previous bucket, or we could set up something different. But these are going to be replicated buckets. It would be best to have the same configuration on both sides. So let's choose the bucket. And as you can see, it's going to take policies. Bucket versioning was disabled before, but now it's enabled. So we're going to quite simply create our bucket. And after the bucket comes up, you can see we have the primary bucket that we previously created, and we have the new bucket. So we're going to replicate from this bucket to this bucket. So the first thing we're going to do is we're going to click on the current bucket we have. And we're going to go to the Management tab of this bucket, and we're going to create a replication rule to replicate our data from the first bucket to the second bucket. So let's do that. We'll create a replication rule. And like anything else, you've got to create a rule name. And these names are things that you logically identify. So we're just going to call this S3 bucket, and I'm BUCK bucket replication. And I'm not the best speller in the world, but we're also doing this for speed and expedience because we want to create the best environment for everyone. And we can see that this is going to be enabled because we obviously want it to work. And we're going to create the source bucket. And then we're going to create we're going to choose the bucket, which is going to be the place that we want to send our data to, which is going to be GCA bucket 2. Now when we do this, we typically have to choose an IAM role. Let's see what we have here. I created a role, specifically designed this, and we're going to just choose that role. And if we wanted to replicate encrypted objects, we could do that with the key management system, but we're just trying to make this as simple as possible. And we're going to just save this configuration. And one of the great things when you're using the console is it will tell you if you erred. And occasionally throughout these videos, we might intentionally forget something
just so you can see how great it is, the guidance that you're provided, because it can really make life a lot simpler. And as you can see, our replication configuration settings are up and they're up and running. So as we have new data, it will be replicated to the new bucket. So there you go. S3 bucket replication has been set up, and now you know how to do it for the future. Something you definitely want to know, especially when you're dealing with S3 hosted websites or when you're looking for additional redundancy in your environment. We're going to create an elastic block storage volume, and we're going to encrypt it. And before we do that, I want to do a quick refresher over storage, because storage is an essential part of the cloud computing environment. So as a reminder, we have a few options for storage. We have S3, and S3 is object storage, and it's a great place to store data or share data between others. We have elastic file system volumes, which are network volumes. It's very similar to the network file system that's typically used on Linux and Unix systems. We have FSX, which is the file system that's been designed for Windows. These are Windows servers, and they're designed for Windows-based workloads. We have Glacier, which is really an environment to archive your data. And when you're using Glacier, again, remember the data is not immediately available. It's going to be there in a period of time that's going to be several hours. And if you need your data prior to that, you're going to have to pay an expedited retrieval fee. We have the option to use storage gateways. And what storage gateways do is they sit in your local data center, and they enable you to retrieve files from S3 and make it feel like it's standard traditional file storage. They also enable you to mount your local servers to the storage gateway appliance sitting in your data center, and then it will then take your information and send your information over to S3. And that's a great way to replicate your data to two different environments, or to migrate from a traditional data center to the cloud. So in this case, we're dealing with elastic block storage, and elastic block storage is not listed under storage, but it's actually listed under the compute services. More specifically, it's going to be under EC2. So under EC2, what we're going to do, we're going to look for where it says elastic block store, and we're going to look for the volume area. So under volume, we have the standard volume that comes with my instance, and we're going to create a new volume. And I'm going to just choose the standard general purpose SSD. We could probably use a cheaper option, but we're only going to keep this EBS volume up for a little while. We're going to pick the size, which is 100 gigabytes. And then we're going to place the availability zone. We could bring it up from a snapshot, but in this case, we're just going to launch a new volume. We're going to encrypt the volume, because whenever you're dealing with security, you should deal with encryption. We're going to click default, and we're going to create this volume. Now, realistically speaking, we now have a volume, and it's now been created. And you can see the volume's been created. And that's really all we have to do. Now at this point, to use it, you'll just choose which devices you choose to mount the EBS volume. There you go. That's how you create an EBS volume, and that's how you encrypt it.
So now let's discuss computing on the AWS platform. Now, Amazon has what they call a computing instance, and they call their computing instances Elastic Compute Cloud, or EC2. And what EC2 instances really are is, for the most part, they're virtual machines, and they're sized in the same way you would size any other virtual machine. And you're going to size your virtual machines based on CPU cores, memory requirements, storage requirements, and that's in terms of both capacity and performance, and then network performance, how fast of the network access do you need. Now, Amazon has a whole lot of different types of virtual machines that are specific for certain instances. I would suggest that you just look on the Amazon page, because these are updated frequently, but we have a list and a table for you to understand them. But they change frequently, so at least when it comes to specific computing on the AWS platform, whether it's a G-type instance or an R-type instance, there's a table and a chart which we'll include, and we recommend that you look at that and know them in case you see any questions, but in real life, you're going to check these on an as-needed basis. So let's talk about giving an operating system to your EC2 instance. And EC2 instances support Linux and Windows, and as of a few days ago, they actually support Mac OS, which is run on a Mac Mini. And you have the option to use a pre-built virtual machine or create your own. Now, pre-built virtual machines are available in the form of something called an Amazon Machine Image. And this Amazon Machine Image is essentially a fully built machine in an operating system, and all you have to do is boot it. Now, the AMI has to have a few things. It's going to need a storage volume, and you're going to specify that. I've mentioned before under storage, you can have what's called instant storage, which is enough to boot the system and run the system. But that instant storage completely goes away as soon as the instance is terminated or rebooted. Or you can use EBS or elastic block storage. And with EBS, you can choose the performance requirements, but it will also not go away upon instance reboot or termination. Remember, if you use instant storage and you upgrade the operating system and cause a reboot, the entire drive will be wiped out. So don't store anything that you need on instant storage. Store it on an EBS volume or store it on a network type volume such as an EFS share, and we'll talk about that more later. So while we're working with AMIs, you have to know where to find them. Because if you're going to build your instance based on an AMI, where are you going to get it from? And you really have four options. So Amazon publishes AMIs for pretty much any use case. And you can get yours directly from Amazon. If you want a CentOS version, for example, a Windows version, for example, an Ubuntu version, or an Amazon branded Linux version, it's available for you. Now, you could also buy a pre-built AMI from a marketplace. And the AWS Marketplace sells pre-built AMIs for specific needs. And these are typically run by a third-party vendor that's got a specific application, and they build this virtual machine to be completely optimized straight out of the box for your application. And that's a good option. Now, another way you can get your AMI is you can basically take an existing virtual machine that you have running on the AWS cloud, and you can snapshot that virtual machine, create an image of it, and from there, you basically what you have is you've got an AMI, which then could be booted or relaunched anywhere in the world on the Amazon cloud. And lastly, let's say you have a traditional data center, you've got servers. You can basically convert that physical machine to a virtual machine image and then place that on the AWS cloud and then boot it up with an EC2 instance. So let's talk about the components of an AMI. So the AMI is going to have an operating system, it's going to have launch permissions, and it's going to have a block device storage mapping. So when you set up your AMI, you're going to tell it boot from instance storage, boot from an EBS volume, or boot from instance storage, but mount these 3 EBS volumes. And that way when it comes up, the system knows where the data should be done. And what's really interesting and great about an AMI is basically you can have a system running on a region in the US, and then you decide that you want for disaster recovery purposes to basically take a copy of that and copy it to another region in Europe or Asia, for example. You can place an identical copy of all your systems in another region, and as needed, you could just literally boot them right up. And if you boot them right up, they're going to be completely running and functional. So it's a great way to do disaster recovery in a very inexpensive sort of manner. So now that you know about EC2 instances and AMIs, let's talk about automating the first boot of an AMI. So let's say you're taking one of the Amazon Linuxes or any of your favorite flavors of Linux as an AMI for your first boot. When you take that virtual machine, there are certain things that you want to do with it in almost every case. You want to update that and patch the operating system, and whether it's like a sudo apt-get update on an Ubuntu type system or whether it's a yum type update on a CentOS type system, no matter what, you want to update it to make sure that your system, before you apply any of your applications or dependencies, is updated to be the most stable and secure version. You may also have some applications you want to install. Maybe you want to install an Apache web server, for example. You may also have some applications that need to be installed, and you can do all of these things with a startup script, which is called a Bootstrap script in the AWS cloud. And realistically speaking, it's a very simple shell script that you would just put as a Bootstrap script for a Linux type instance, and it's a PowerShell script that you would use for a Windows instance. But the key is you're basically taking the operating system and you're going to patch it automatically by your Bootstrap script as soon as it boots up. So now let's talk about purchasing instances on the AWS cloud. And realistically speaking, there's 3 primary versions, and that's on-demand instances, reserved instances, and then spot instances. But there's two forms of reserved instances, and we'll talk about them. So let's first begin with an on-demand instance. And an on-demand instance is just what it sounds like. It's an instance that you create when needed. And this is really what makes cloud computing so great, is you can have an instance, it can go up as needed, and then it can auto-scale, meaning there's two ways you can scale your instances. You can scale them up and you can scale them out. Scaling up is basically more processor power and more memory in your system. Scaling out is basically using more systems. So one of the best things you can do in a cloud computing environment is you can have these on-demand instances, and if the CPU reaches a certain threshold, or the memory reaches a certain threshold, or disk usage reaches a certain threshold, you can have the system open up a new instance. And by that, you can scale out. Because overall, over time, scaling out will give you, meaning adding more instances, will give you much more capacity than scaling up. There is a point where no matter what in a single machine, you just can't throw enough memory, processing power, and disk speed. But if you are scaling out, you definitely can. And on-demand instances facilitate auto-scaling, which facilitates scaling out. Now, I mentioned all the great things with on-demand instances. You don't need to know exactly how much data you're going to use, your compute capacity, or how long you're going to need it. But with that comes more expensive pricing. And you're paying by the second, but this is obviously your most expensive of the options because it gives you the most flexibility. Now we're going to get into reserved instances. And what reserved instances really are is you know exactly how much compute power you're going to need, you know your memory power that you're going to need, you can actually purchase ahead of time a virtual machine or an EC2 instance, and you can get a contract for up 1 year or 3 years. And by having a contract, what actually happens is you get a substantially reduced price. And the longer the contract, the bigger the discount. And this is great when you know you have an application that's going to run for 3 years or 1 year. Now, what if you have an application that is doing a batch job, that you have known computing power requirements that you're going to need every Friday through Sunday for 24 hours a day while that period is running, and it's a critical batch job, and you need to know that no matter what, under any circumstances, the batch job gets completed. Well, you can use what's called a scheduled reserved instance, and that's really just a reserved instance where you schedule it for a short period of time or a medium period of time, like a few days. And by doing that, you still get a discount over on-demand pricing, but it's guaranteed you own the bandwidth and you're getting a discount. Now, the other main option is something called the spot instance. And what a spot instance is you're purchasing unused capacity from the Amazon network. And you bid, like an auction, on this. And if your bid is above the spot price, just like an auction, your bid is filled. So let's say you bid on an on-demand instance at a certain price. If the price actually rises above your bid price, your spot instance will be shut down. Now, there's a few ways you can tweak that, but just remember that spot instances shut down if the bid price, if the current market price goes above your current bid price. So, spot instances are a phenomenal way to purchase unused computing power to run any type of a job that actually needs to be performed where you need a lot of computing power. But this job has to be able to tolerate being shut down or being stopped and then being rerun later. So you don't ever want to use a spot instance for any mission critical applications. Now, there are certain times where you might actually need something that's a little more dedicated to you than the traditional virtual machine. And this is, let's say you have an application that's literally tied to physical hardware, and it needs, or you need access to say, I know exactly what the CPU is, I know of the hardware, I need to know exactly what utilization is of something else, then you can purchase a dedicated host, which is really just a dedicated server. And on this dedicated server, you can do, realistically speaking, anything you want on it, because it's your server. It'd be no different than any of your servers in your environment. So you can install whatever you want in terms of applications, operating systems, and it's your server. Now that you know the instance purchasing options, AWS has something called tenancy options. And what the tenancy options are is really where your machines are actually housed. So for the majority of users, they're going to have something called shared tenancy. And basically with a shared tenancy environment, Your virtual machine is on a server, but other customers' virtual machines are also in that same server. And that's fine because they're logically separated, they're completely secure. But just understand that your systems and somebody else's systems are on the same server. And that's fine for normal situations, but there might be times where you want to know that you have access to the entire server. And for that, you can buy a dedicated instance. And with a dedicated instance, basically, all of your virtual machines are going to reside on the same server, or the same set of servers if you were to purchase multiple dedicated instances. And that means all the machines are yours. And that's great if you need a little more control. And I mentioned previously a dedicated host, and a dedicated host is basically just a plain bare metal server. It's a server that you're purchasing access to, and you can do absolutely anything you want with it, and you have full visibility, and you have full access to the hardware just like you would any server sitting in your own data center. So if you're going to place computing assets on the cloud or even your data center, you're going to have to make sure those servers or systems are secure. So the way you secure EC2 access is with a security group. I want to emphasize that again. EC2 access is secured via a security group. And later on in this course, we'll talk about something called the network ACL. And a network ACL keeps unwanted traffic out of a subnet, but a security group keeps unwanted traffic out of an EC2 instance, or in many cases, an AWS service. But we're talking about EC2 instances right now. Now, the default policy of a security group is deny all traffic. So basically, if you don't allow any permits, all traffic will be denied. So whatever your application is, if you don't configure the security group to allow what you desire, it won't work. So remember that if all of a sudden you spin up a new instance and it's not working in its intended way, did you put a security group on it? And is the security group correct? Is it allowing the traffic you want and nothing else? Now, when you write a security group policy, you're going to write it like you would any type firewall policy or access list type policy. And basically what's going to occur is you're going to specify a source and destination subnet. You're going to specify a protocol like TCP or UDP, and you're going to specify a port number, say port 80, for example, for www or HTTP type traffic. Now that you understand about security groups, now let's talk about providing an IP address to an instance. And if an instance is going to communicate on a network, it's going to need to have an IP address. Now, something that not everybody understands is every time you have an interface, each interface is going to have to be on a different subnet. So if you have 3 interfaces, you're going to need 3 subnets. So that's something that's pretty critical. We want to make sure that you truly and deeply understand that all interfaces have to be on a different subnet. You can use a private or a public address. Now, private addresses are used for anything that you don't want to be on the public internet that needs higher security. Public addresses are going to be used that anything that's going to be placed on the public internet. And if you're going to place something on public internet, it's going to need a whole lot more security. But for right now, understand private addresses are used inside of your VPC, public addresses are used outside of your VPC. Now, Amazon automatically gives you a fully qualified domain name that matches your instance. So for example, instead of actually knowing the IP address of the instance, they will give you something more clickable that you can that'll be much easier to reach based on a name. Now, we'll talk much more about DNS later in this course, but understand if you want to go to www.amazon.com, you could find out their IP address and put their IP address in your browser, or you could just type www.amazon.com, and what'll happen is you make that request will go to a DNS server, and the DNS server will basically say, I have the address for www.amazon.com, and I'm going to give you that address, and therefore you can connect to it. Now, Amazon will also give you an IPv6 address, but you can disable that, but every instance is also going to get its own unique IPv6 address. Now, after you know about securing it and also addressing it, how are you going to manage your EC2 instances? So you can manage your instances in 3 realistic ways. You can manage it directly from the EC2 console, nice browser-based interface, very easy to use. If you're using a Linux-based system, you can SSH or use secure shell to SSH into the machine and manage it the way you would any other virtual machine. With a Windows system, you can use what's called remote desktop protocol and manage it the way you would any other Windows machine because you'll have full access to the screen and you can click as necessary. And you can also use for certain things like a lot of them, but not all of them, you can use the software development kit and work through it and manage it through an API interface. So let's talk about what we've discussed in this section. We've discussed EC2, we've discussed AMIs, we've discussed purchasing options for your specific type of virtual machine, meaning do you want like a GPU-based virtual machine or a memory-optimized virtual machine? We talked about the tenancy options of what you could get, like a shared server, for example, versus a dedicated host. And we also talked about securing your EC2. We talked about addressing your EC2, and then how to manage and access your systems.
So what we're going to be doing is we're going to be configuring an EC2 compute instance. As we taught in the lectures, the EC2 is the primary computing platform on the AWS cloud. So the first thing we're going to do is set up an instance, and then we're going to show you how to log into the instance via secure shell or SSH. So the first thing we're going to do is we're going to log in, and after we log in, we'll go to the management console where I'm already at, and then under all services, under compute, we're going to click on EC2. And when we get to EC2, we'll have the ability to launch an instance. And we're going to do that right now. So the first thing we're going to do is we're going to click Launch Instance. And here we're going to pick an AMI, and this is going to be a pre-made virtual machine that you're going to just launch from the Amazon machine image. Quite simple. We're going to select one. We're going to select Amazon Linux because it's both free and it's a pretty solid form of Linux. And we're going to select that. From here, we're going to choose our instance type. Now, AWS has a variety of instance type based upon your requirements of bandwidth, performance, and the such, memory, CPU requirements. But in our case, this is a lab, and we recommend for your own lab, you use something that's free tier eligible. So we're going to click a T2 Micro free tier eligible instance. Now, in this case, we could just launch it from here, or we can go to Next, Configure Instance Details. And while we're not going to really change anything, we're going to work with the standard defaults. We just want to show you what they are. So in this particular case, you can pick the number of instances that you want to launch. And you could, if you wanted to purchase it as a spot instance, you'll have that ability. We're going to choose the subnet that you want to be on, which is part of the network. And we can talk about capacity reservation if we need it. Would we like to start 2 or 3 or 4 instances? And here under shutdown behavior, we have the opportunity to stop or terminate. If we terminate an instance, anything that's on instance storage will be completely lost. So that may be appropriate under certain circumstances, but it may not be. And that's why we talk about using EBS volumes as opposed to instance storage for anything that you need to persist beyond a reboot. And if you're looking to prevent that kind of termination and instance loss, you can click Protect Against Accidental Termination. When it comes to monitoring, we have CloudWatch monitoring, which begins by default, but we can also enable detailed monitoring, and we'll talk about that much later during the course of the program. And then the tenancy, this gives you the option to run it as a shared instance or in different environments, and we'll talk much more about that later. So in this particular case, we're just going to go here and look at some of the advanced details. You can place some metadata, which is really data about data. And under here, if you desired, you can place some startup scripts or other configuration options, but we're not going to really talk about that for right now. And then we're going to just review and launch the instance. And what you see is it's going to tell us that the security group, that the configured one, is open to the world. And what they mean by that is, by default, it enables SSH from anyone to access these instances. Now, in reality, you only want to allow SSH from the subnets that require access to these instances, but in our case, it's a simple first lab. We're going to just do this with the default security group, and then we're going to click Launch. And from here, what's going to happen, in order to be able to access these things via a secure shell, you're going to need a key pair. Now, in our case, you can choose an existing one, create a new one, or proceed without a key pair. You want to use a key pair because it's going to be much more secure. I'm going to choose an existing key pair, and we're going to launch the instances. Of course, you have to acknowledge this first. So our instance is launching. It's going to take some time for the instance to boot. And here you can see that the instance is pending. You can also see that I've had another instance that I've already terminated. But in this case, our instance is pending, meaning it's coming up, it's booting. So we'll give that a few minutes, and we'll keep checking. These boot faster than you can see. And there you go, it's already up and running. So we're going to click on the instance ID. And under the instance ID, we can see the instance's private IP address. We can also see its public IP address is what we're going to use to access the instance. And you can see that it has a publicly available DNS name. So we can address this by the DNS name. We can connect to this name without actually having to connect to the IP address. And this is going to be much easier to remember the DNS name than the actual IP address. Now, you can see more information about our instance here. You can see the details of the instance. You can see the security group that's actually running. You can get your information regarding the network. On this place where it says storage, you can actually see what we're using in terms of storage and what the storage device is actually listed as. Under monitoring, you can see what's going on with your instance. You can look at the CPU. You can look for system failures. You can look where network is going and disk reads in and out. That's your typical basic CloudWatch options. There are other options that you can do for an additional price, but these come with it. And then if you wanted to tag your instance or add information about your instance, you could do that here. So imagine you have 10,000 servers. If you don't have some kind of information about your instances, it's going to be hard for you to remember them. But in our particular case, we're going to just work with the standard. So from here, what you would do is you've downloaded those key pairs. Now you're going to have to download those key pairs, and you're going to have to place them in a directory on your computer. And you're going to want to SSH from the directory where you store your key pair if you're using a Linux system, a Unix system, or a Mac. Now, if you're using Windows, you're going to have to use an SSH client like PuTTY, which will be much easier to set up. There'll be a place to just import your key pair. But we're going to do this on a Mac because I use a Mac, and most tech people, in many cases, are going to be coming from a Linux machine or a Mac or a Unix machine for this purpose. So we're going to show you this way. So I had already downloaded my key pair. And I'll bring my key pair over here for a second. And what we'll do is I know where my key pair is located. But if you don't know where you're at, first go to your PWD will take you to your present working directory. And in this case, I'm under user/Mike Gibbs. Now, if I look at my files, you can see that I created a folder called AWS where I stored my key pairs. Keep your files in a folder that's going to be very secure. So in order to SSH into the system, I'm going to go to the directory where my key pair is. Now, if we look very carefully, you'll be able to see there my key pair is there. But we have to make sure we have permissions. And we want to use the least number of permissions necessary to get our job done without enabling too much permission. So what we're going to do is we're going to do a change mod, which enables us to change the permissions. And in this case, we're going to use 400 or 400. And then we're going to actually enter the name. Press enter, and now we have the permissions. So now we want to connect to the instance. All we have to do is SSH into the instance. So we're going to see the address. Obviously, once you do this a lot of times, you're going to know what to do. But in the case where you don't, AWS actually works with you with your key pair and the DNS, and they tell you exactly what to type. So take this, copy this, Control-C, Command-C, whatever you're using if you're on a Mac versus a Windows instance. And then come back here, and then we're going to have to go back to our terminal window. We're in my terminal window, brought it back. We're going to take the SSH information directly from AWS, and we're going to click enter. Now it's going to ask if I want a fingerprint. And anytime you SSH, basically there's like an RSA type SHA-256 fingerprint that actually comes through, and you're going to have to say yes if you want to be able to connect to this, because this is how the authentication and the encryption between your device and the instance is going to occur. Click yes, and as you can see, I am now in my EC2 instance. And if I were to list ls to see what's in the folders, if I want to look at my IP address, I can do that. Now, something that's very interesting, if you look at the IP address in this video, notice that it's a private IP address, 172.31.40.43. That is a private IP address. Now, how am I connecting to a private IP address? Through the internet? And the answer is I am not. I am connecting to the public IP address that was automatically assigned. This EC2 computing instance does not have any knowledge of that public IP address. So what's going on is Amazon is knotting this private address into a public address, and that's what I'm using to connect. And over here, we could do anything we needed, like if we wanted to do a yum update, which would update the operating system, we could do that. And in many cases, if you don't have permissions, it's going to force you to do a sudo or super user. And as you can see, I've been given the ability to do this. My permissions are good. And all I have to type is Y. And all of a sudden, my EC2 instance is updating itself completely. So there you have it. That's all that's necessary to set up an EC2 instance and actually secure shell and remote access it. We're going to be setting up an EC2 instance, and we're going to be setting up a Bootstrap script. And in this particular Bootstrap script, we're going to set it up that it's going to actually upgrade the operating system to the newest packages, install the Apache web server, and we're going to give it a mini web server setup. So let's go to our EC2 instance, and let's launch an instance. Now we've been using, for the last few, Amazon Linux, which is a form of Linux I really like. It's based on the Red Hat type distributions, and it uses the typical yum update functionalities that you would get basically on something like a Red Hat or a CentOS. But in this case, let's use a Ubuntu server. Just showing you that we can use multiple server types. Again, we're going to configure this for the free tier. Let's configure the instance details. Now, under the advanced, what we're going to actually do is we're going to set up a mini shell script, and we're going to make sure that we're using the appropriate shell. So we're going to do /bin/bash. So it's a bash script. And then when you're working with Ubuntu or any of the Debians, it's going to be an apt-get for an update or an upgrade. So apt-get update. Now, obviously, this would be great to template this, so you can do the same thing with all of your servers. But in this case, we're building a lab, and we're just building it on the fly, especially since I'm recording on a window, and it's very hard for me to go to multiple windows without taking the screen off of you, which you could see. So now let's install the Apache. T-get install. We want to make sure we say yes. APACHE 2. And then what we want to do here is we're going to create our web page. We're going to do echo, very basic website, and we're going to say welcome to Go Cloud Architects. And we're going to take that, what we just echoed, and we're going to send it to a main web page file called index.html, which will be the root of our website. And then we're going to copy index.html to our directory where we actually store the website, which is going to be /var/www/html. So let's make sure we didn't make any errors. I always like to double check. apt-get update, apt-get install Apache 2, echo the web server to form our web page, and then we're going to copy the index to the appropriate location. And that's it. Let's just review and launch. And we're using the default security group, and it's warning us that you typically would not want to use this in reality. You'd want to use something that's a little more sophisticated. We're going to choose an existing pair. There you have it. We've set up an instance. Now the instance is pending, so let's wait and see the instance come up. We'll give it a minute because not only we asked the instance to come up, but we've also asked it to do some upgrades along the way. So it looks like our instance is up and running. And that's really all that's necessary to set this up.
So in this section, we're going to be discussing databases. Databases have become an absolute essential tool in today's business environment. And they're a mission-critical application for which businesses depend many of their applications, but also their decision-making. So databases are really critical. So let's talk about what is a database. And a database is really a place where you're going to store large amounts of information. So you'll store large amounts of information in a database. But a database is different than standard storage, where you could also store large amounts of information. A database facilitates the sharing, the sorting, the calculating, and the reporting of information gleaned from your data. So because of the ability to draw such good conclusions and see the relationships between different objects, at least within relational databases, businesses have become absolutely dependent upon databases. So AWS has three primary forms of databases, and they all have specific applications. AWS supports a relational database, NoSQL databases, and a data warehousing database. And we'll talk about data warehousing and data lakes to some degree later in this course. But let's first look at relational databases. Now, relational databases are by far the most common forms of databases that are actually used by businesses currently. And what's so interesting about relational databases is they provide a relationship between variables. So you can see what happens if one variable is changed, how it will relate to something else, which gives you great business information. And the way they're stored in a manner that's just like a spreadsheet with regards to rows and columns. And each row is going to have a unique ID, which is called the key, and each column is going to have something called the value. And that's where in relational databases we get this concept of a key-value pair. Now, when we're dealing with relational databases, they may operate slightly differently than NoSQL databases, at least with regards to the consistency of data. So we like to say that relational databases all follow the ACID model. And the ACID model means they're atomic, meaning it either works or it doesn't work. The reads and writes are consistent. And what I mean by that is if I write information to a database, every other user that's accessing that database will get the newest information the second or even the millisecond that I write it to that database. It's not going to take time to become consistent. It's immediately consistent. It's isolated, meaning one component of the database will not affect another component of the database, and the data is durable, meaning once it's there, it's not going anywhere. Now, AWS supports a variety of relational databases. They support Amazon Aurora, which is the Amazon branded relational database, very common database used by many AWS customers. They support MariaDB. They support Microsoft SQL Server. They support MySQL. They support Oracle's database, and they support the Postgres database. And we'll talk a little bit more about each of these databases and their support on the AWS platform. So now let's explore the different types of relational databases available on the AWS cloud. And we're going to begin with Amazon Aurora, which is going to be an exceptional option for most people. The reason we like it is Amazon Aurora takes the feature set and functionality and performance of big commercial databases and they give it to you effectively for free. So it's kind of a cross between an open source database and a big commercial database. So the performance is great. In fact, it's up to 5 times faster than MySQL, and it's up to 3 times faster than Postgres, according to AWS documentation, and we've seen very good performance in this. And this is typically used in enterprise applications or software as a service applications. Very high performance and great pricing structure. Now, the next relational database that's available on the AWS platform is MySQL database. And MySQL is an open source database, and it's been around for a very long time. It's an incredibly popular database, and it's used by a wide variety of web applications, but there's some scalability features or challenges with MySQL, and that's why some of these other databases were formed. And Postgres is another type of relational database, and it's another open source database like MySQL, but it has a very sophisticated feature set and functionality compared to MySQL. And the next version that you can use is actually going to be called MariaDB, and MariaDB is another open source relational database, and it's actually created by the people that actually made MySQL, but it's a newer version designed to address many of the scalability and other problematic shortcomings of MySQL. But this has a very good feature set, and it's really designed for enterprise applications, and it's open source, so it's free. So let's move on to some commercially available databases on the AWS platform. We'll begin with Microsoft SQL databases. And Microsoft SQL Database is a paid database, and is typically used for Microsoft-specific workloads. And it's got a lot of tools like the Server Management Studio, which enable organizations to use it quite easy compared to other forms of databases. And AWS supports the main licensing types, and it supports most of the versions. We'll show you what the versions are in text, but understand that the Microsoft database is a paid database, and it's available for you if you have Microsoft-specific workloads placed on the AWS cloud. Now, the next thing we'll talk about is Oracle database, and the Oracle database is the most common paid relational database in the world. And it's got an incredible feature set and an incredible functionality. And there's, realistically speaking, two ways that you can use Oracle databases on the cloud. You can use the AWS type licenses, which is the standard version, the standard one, or the enterprise version, and these are available. What happens is AWS has these licensed, and you're actually borrowing their license when you use them, and that's completely appropriate, completely legal, and that's what most organizations do. Having said that, if you need more functionality, you can actually do this bring your own license version with you of your Oracle database. And with this model where you bring your own license as opposed to the license included with the previous method that I described, you have access to every one of the Oracle database options to your disposal. So the next type of database we're going to be discussing are something called NoSQL databases. And NoSQL means not only SQL. And NoSQL databases provide enormous flexibility when compared to SQL databases because they allow for much more flexibility in their schema structure, which is what's going to make NoSQL databases scale much better with much more capabilities than an SQL database. So there's going to be applications where you're going to use an SQL type database or a relational database, and there's going to be instances where you're going to use a NoSQL database. What's great about NoSQL databases, they work with both structured and non-structured data, and that flexibility really helps a lot. One thing to know is I had mentioned previously that SQL and relational databases followed an ACID model. But here we're going to follow a base model, and we're not talking about pH. What we're talking about is the model is they're basically available, soft state, and eventually consistent. And what all of that really means is that if I were to make a write to the database, instantly at the time I make a write to the database, someone reading from that database may not get the newest information. It may take a few seconds for everything to become consistent. And with that comes a lot more flexibility and scalability. But with that also comes the ability to get stale information for a very short period of time. Now, NoSQL databases typically work with a key value var environment, and you can see we've drawn that out for you so you understand at least what a key value pair type environment is. But the things to remember are they're very flexible. And because they are not bound to the same exact schema that you'd find in an SQL database or a relational database, they can scale much more. Now, AWS has their own branded form of a NoSQL database called DynamoDB. So let's dive into that. So now let's discuss DynamoDB, which is the AWS version of a NoSQL database. Now, DynamoDB is a fully managed service by AWS, and it's very high ability, and by default, it's in multiple availability zones. And one of the great things about DynamoDB is it's completely serverless. And since it's serverless, you don't have any compute instances to manage, no operating systems to patch, and a lot of the things that go into managing a compute instance are completely done by AWS. But furthermore, it will scale to almost an unlimited manner because it's serverless. So normally with the server, you run out of cores, you add some additional instances, or you can use a bigger server. But in this case, it's almost unlimited scalability. And DynamoDB is also very latency because it stores all its information on very high performance SSD drives. Now, one of the things that's pretty incredible about DynamoDB is the latency. And it's based because of the type of drives, but also the way the database is architected. And it's typically low millisecond latency, but you can actually set it up by using DynamoDB Accelerator to be sub-millisecond latency. And all data is encrypted by default. So you don't have to worry about your data being protected. And it can be backed up with little to no effect on database performance. And some things to remember about DynamoDB is it's typically designed to work with a key value pair environment. Now you can have a primary index or a secondary index, and that's one of the reasons you can make this scale so well. When you purchase DynamoDB, you actually provision your capacity ahead of time. Just like a provisioned IOPS volume, you're going to provision your DynamoDB ahead of time. So realistically speaking, you need to know what your requirements are prior to using DynamoDB. Now you could set up DynamoDB with auto scaling, and that's a totally good option, and it will scale up based upon needs, but it doesn't scale back down. So if it scales up temporarily, you're going to have that bigger instance and be charged for that bigger instance all the time. So you really want to know what you're doing so you can manually provision this ahead of time so you have the read and write capacity and the performance capacity you need without relying on auto scaling. Now the price of this is going to be based on throughput. So the way they actually work DynamoDB, it's priced on throughput. So that typically occurs with how much data is moving in and out of the database. I just want you to understand that. So where would you use DynamoDB? You're going to use this in a wide variety of use cases. You're going to use this when you need, for the most part, unlimited scalability and unlimited performance. You're going to use this if you have extremely low latency requirements. And if you've got a tremendous number of devices, think Internet of Things, think having millions of sensors constantly reporting every few seconds and sending it to a database. Perfect use case for this. So this is ideal for storing, say, game state. It's really ideal for any time you have a large number of transactions and you need to move it quickly. Lots of e-commerce applications, lots of financial applications where you're just storing a tremendous amount of data. Now, I mentioned previously that NoSQL databases, and DynamoDB is a NoSQL database, are eventually consistent. And when I talked about the ACID version versus the base version, I said that they're eventually consistent, meaning if you make a write, the read may not be immediately available after a write. Now that is the default configuration. You can change that if you need to be instantly consistent or immediately consistent, but with that comes a performance and a scalability cost. But it's definitely an option should you need that in your business. So let's talk about data warehousing databases, and this is a big data application. And a data warehouse is really a way to, in a very structured manner, in a searchable manner, store very large amounts of data. And it's going to be a combination of using a database, it's going to use S3, it's going to use some tools to try and take some of the data from S3 and put it in the database. And then the reason you're doing all this is to gain actionable insights from your data, because if you've got all this data, the data can help you make inferences for business decisions, but if you don't analyze the data or use the data, then you won't get there. And Amazon has a tool called QuickSight that helps you visualize the data that you've gleaned from Redshift, as well as your entire data warehouse. So what is Redshift? And Redshift is the Amazon data warehouse solution. And it's a fast, powerful, fully managed service. And it's based on the Postgres database, which is good because it enables you to do SQL queries on your data. So it can use any platform that can do SQL queries can actually work with Amazon Redshift. And the way it's built around a architecture of computing clusters. And the clusters are all of computing nodes. So what's going to happen is you're going to have this big cluster, and inside of there, they're going to have these little mini computing nodes. And the primary node is called the leader node, and all the other nodes are compute nodes, which are going to support the leader node. When you run a query, it's going to be directed to the leader, whereas the other devices are doing much more processing. So when you're dealing with this data warehouse, you're going to achieve scalability or increased performance by scaling out, by adding additional nodes. And realistically speaking, the Amazon Redshift has two types of nodes that are available. And you've got the option for dense compute or dense storage. Now, dense compute stores their information on high-speed SSD arrays, where dense storage means you've got a lot of stuff to store and you're looking for a more cost-effective way to store it. You're going to store that on magnetic disk arrays. So the next big data application that we're going to be talking about is something called the data lake. And a data lake is really a repository that allows you to store a tremendous amount of structured and unstructured data in the same place at virtually any scale. And because you can put so much data that doesn't have to be structured, it enables you to have access to a tremendous amount of data to make better decisions. So the reason you're doing this is you're storing your data, and you're going to store it in a lot of different forms. I mean, you're going to have some data that's going to be stored in data storage, say for example S3. You'll probably be integrated with both Redshift for big data, like your data warehouse. You probably have a Dynamo DB. You might also have, a relational database. And you're going to have tools that are going to extract and transform this data. But the point being is data lakes hold a tremendous amount of data, and they keep them there until you need them. So you'll be able to do queries on them to search for relevant information when you need them, or you can save this data and use it for future applications such as machine learning. But the point being is it's a great place to store structured and unstructured data, lots of data, and keep it available for a future date when you're going to need it. So in this section, we're going to be discussing how to optimize databases and improve their performance. And one of the things we need to start with is storage. So Amazon databases are stored on EBS volumes. Now these are basically the same EBS volumes that we talked about when we talked about storage. So let's talk about the 3 EBS volume types that you would use on your databases. Provision IOPS, and you're going to use this. This is the fastest and best performing option on the AWS cloud, and you're going to use this when you need low latency, high performance storage. So for any type of database that you need to really scale, and you need low latency, it's going to be on a provisioned IOPS volume. Now your next option is going to be a general purpose SSD, and this is a medium latency, medium throughput environment, and it could be used for databases in a lab environment, or it could be used on databases that are not critically latency sensitive. And the last option you have is going to be for magnetic storage, which is great for storing large amounts of data. It's low cost, but it's much higher latency, so do not use this for latency sensitive applications. So I mentioned databases are an absolutely mission critical application in modern business. And anytime you have data and an organization is dependent upon that data, you need to maintain that data under any circumstances. So we need to back up the data that's on all of our databases. Now the good news is AWS does this automatically for your databases. And when it's backed up, the database backups which occur automatically, it backs up the entire instance. It doesn't just back up your data, it backs up the operating system, it backs up the dependencies, it backs up your database, it backs up your configuration and all of your data. So effectively what's happening is you're going to have a snapshot that's automatically created, which is effectively the same as a machine image to relaunch the instance from a snapshot. So you're getting everything. Now, when these automated backups occur, you have to understand that it's actually taking resources away from the database. So it's possible during the short period of time that a database is being backed up, performance is either degraded or even the database is somewhat unavailable for a very short period of time. Now, I mentioned that databases are backed up in the form of a snapshot. And you can also perform a manual snapshot. So you can take the automated ones or you could snapshot them manually. And because it's a snapshot of the entire EBS volume, as I mentioned before, it's a complete copy of the server. And when you do a database snapshot and a manual one, they're going to be maintained until you delete them, as opposed to an automated database backup, which is going to be there from 1 to 35 days based upon configuration. A manual backup will be there until you delete them. So it's going to look very simply. You're going to see the database. It's basically going to make an image of the database, and it's going to store it. Now, if you want to restore the database, again, it's pretty easy. You're going to take your database snapshot file. You're going to open it up, and a new instance is going to be formed. Now, because a new instance is going to be formed, it changes a few things. All of your information is identical, configurations are identical, and everything will be the same about the server, but it's going to have a new IP address because it's a new instance. And with that IP address is going to come a new DNS name as well. So if you have anything that's connecting to it based upon its DNS name or IP address, you may need to change that, because even though the server is configured identically, it's going to have a new IP address and a new DNS name because a new instance has been formed. So I mentioned databases are a place for organizations to store an enormous amount of data. So if an organization is going to store a lot of their important data, they need to make sure that that data is secure. And one of the ways you optimize your database is with database encryption. Now, relatively speaking, there's two ways to do this. We're going to start with the primary way, which is complete database encryption. And that's the way that's going to occur is you're going to create something called encryption at rest, which means when the data is stored, it's going to be encrypted. And the way you'll do this is you'll actually encrypt the EBS volume for which the entire database is stored. And with that, everything on the volume will be completely encrypted. You enable that by enabling the key management service. And the key management service will automatically take care of the encryption keys and encrypt the volume. Now, the other type of encryption that's supported on the AWS cloud is something that's called transparent data encryption. And transparent data encryption is widely used in Oracle databases and Microsoft SQL Server databases. And what transparent data encryption really is the data is encrypted and decrypted on demand. So when you write information to the database and it's stored, it's encrypted. When you pull information from the database, it's going to be decrypted. So that's a way to basically do encryption on the fly, and that's called transparent data encryption. So as we're discussing databases, we have to discuss scalability. Since the database is such a mission-critical application, it's going to grow, and at some point, no matter what you do, it's going to struggle to keep up with demand. But there's a lot of tricks that we can do to increase the performance and the scalability to make sure the database can meet the business and customer requirements. So there's two means of scaling things out or up. One is scaling them up, and this is basically putting the database on the largest system you can with the most processing power, the most memory, and the fastest drives. That will work to a point, but no matter what you do, at some point, you're going to exceed the capabilities of the most powerful servers in the world. So then what you're going to have to do is you're going to have to scale out. And basically scaling out is basically just adding additional compute instances. And we're going to talk about how to scale out different types of databases. So we'll start with the NoSQL databases, like DynamoDB or Cassandra. Now, the good news is scaling these things out is very simple. All you have to do is partition the database. When you partition the database, it chops it into multiple more manageable pieces called partitions or shards. And the application will have the intelligence to route the correct information to the appropriate shard. And by doing this, it's going to scale well. So that's very easy for the NoSQL databases like DynamoDB. Now, relational databases, scaling them out, there's a lot of things you can do and a lot of performance optimizations. But we're going to start with scaling out, and then we'll talk about queuing and caching and things like that. So to scale out a relational database, you're going to create something called a read replica. And a read replica is effectively, with the exception of MariaDB, an identical copy of a database instance. But there's a difference between the master database and the read replicas. The master databases do read-write activity, and the read replicas do read activity, and they're meant to be a read-only copy of the database. And it's going to get synchronized in effectively near real time to the master database. And what this does is, by having multiple read replicas, you can point your queries to the read replicas and therefore you're not affecting the CPU of the master database. So you're going to scale out your databases with up to say 4 read replicas. And as you scale them out, you can increase database performance. So when would you use a read replica? You're going to use it when there's a lot of read activity. If all your database activity is write and you add read replicas, it's not going to make much of a difference because it's read activity. But what'll happen is query traffic is going to slow things down at some point if you've got a lot of read and write activity. And by taking all the reads off of the master database, you can substantially reduce the overhead on the master database. So anytime you need extra capacity, extra performance, and you're using a relational database, the first thing you're going to do is you're going to add a read replica. Now, I want to touch on one topic before we get off of read replicas. Read replicas are not for disaster recovery. Read replicas are strictly for performance. So if you see an exam question that's related to read replicas and disaster recovery, this is not a solution. This is a performance option. When it comes to disaster recovery and it comes to high availability, we'll actually talk about multi-AZ, and we'll cover that in much more depth when the time comes. The next way we can increase the performance of our databases is through database caching. So let's describe caching in the following manner. I previously mentioned that you can reduce read activity from the master database by adding a read replica. But at some point, if you direct enough traffic to the read replicas, they're still going to be too busy. So what can you do to offload traffic to the read replicas? Imagine a situation where you already had the information for a lot of the content and didn't need to go to the read replicas. So then your master database with your 4 read replicas could be the equivalent of say 10, 12, 30, based on how frequently you access new data. And that's where database caching comes into play. Database caching is basically a server that sits between you and the database. You've got this caching server. And here's what happens. I'm a user. I run an SQL query on my database, or any type of a query on my database. I first go to the cache. The cache does not have the results, so then it goes to the server. The server then responds to me through the cache. The cache stores the data for a period of time, and then the data is sent back to me. Now let's say my associate at work 10 minutes later needs the same data. He does the same query that I do, but in this case, he goes to the cache first, and the cache says, wow, I have this information, and sends it right back to the person. So not only did the person get it faster because it was cached, but it didn't have to go to the database server. And now let's say the next person requests the same information. Again, they're going to reach out to the server, but they're going to make a stop at the cache. The cache is going to say, I have this information, and send it. So that's how caching works. Caching takes frequently accessed information, stores it on the cache so it doesn't need to go to the read replicas or whatever type of database device you're using, whether you're using an SQL or a NoSQL database. By doing this, it can promote substantial reduction of read activity. So you're going to use caching to reduce read activity. So I'm going to say that again because you may see that. You're going to use caching to decrease read activity. And there is an AWS caching service, and that's called, for databases, and that's called Elasticache. There are going to be 2 versions of Elasticache. You're going to have Elasticache for Reddish and Elasticache Memcached. Now, Elasticache Memcached is a fully functional but very simple cache, and it's designed for simplicity. Now, Elasticache for Redis is a very high performance, very feature-rich set of caching capabilities if you need that. So again, caching is going to work by offloading read activity to your database servers. And one last thing that we should talk about while we're discussing caches is cache timeout. So I previously gave you an example where I pulled information from the database that got stored on the cache, and then 2 of my coworkers ran a similar query, and on the way to the database, they got their information from the cache, and it got brought back, and it's perfect. But let's say 3 hours later, someone actually updates that record on the database. Now the cache still has the old information. And what's going to happen anytime you use a caching service of any kind in any environment is you're going to have something called the cache timeout. And what that actually is the cache will age out or nullify the information stored in the cache after a period of time. And you're doing this because you don't want old or stale data. Anytime you use caching, you run the risk of having some stale data. And that may actually be okay. An organization will say, okay, my data can be stale for 6 hours, or 3 hours, or 10 minutes, or whatever it needs to be based on the effectiveness of the information and how that information could either help or hurt the organization. But they're going to have a cache timeout. And now the cache timeout, or how fast the cache actually ages out and gets rid of the data or purges the data, is going to be configurable. So we've discussed using database caching to reduce read activity, but now let's talk about reducing write activity. And we're going to be using database queuing to reduce the effect of write activity on a database. So what is queuing? Queuing is simply a means to schedule the data that's delivered. And without a queuing service, what's going to happen is the data is going to come in and be written as fast as possible directly to the database. But by placing a queue, we can place a man in the middle to effectively help out. So what's going to happen is we're going to take our data, we're going to send it to the queue, and then the queue is going to find when it's appropriate to deliver a message to the database. And by doing that, we can make sure that messages don't get lost. We can increase the availability of the application, because for example, what if the database were to go down, but the queue is still up? The messages can still be sent to the queue, and when the database comes back up, the message could be drained from the queue and placed in the database. And queuing is used with a tremendous number of applications. Queuing effectively decouples the components of your application. And you may see that as a test question somewhere along the line when you put in a queue to decouple the application's components. So in this case, it's decoupling the traffic destined for the database to the actual database. Now, Amazon has their own queuing system, so you don't have to build your own. And it's called SQS, which we'll cover in more depth in the section where we talk about Amazon specific features, but we're discussing databases, so we need to address it right now. And when it comes to queuing, you have two options. Now you have the standard queue, and the standard queue basically takes the messages in and takes the messages out and delivers them as fast as possible. Now, smaller messages might get delivered before bigger messages. It's very possible with an Amazon SQS standard queue that your messages become delivered out of order. And if your application can tolerate that, that's terrific because it's highly scalable. Now, if you need your messages to be delivered in a specific order, you're going to have to go from the standard queue to something called the FIFO queue, or first in and first out queue. And when you set this up, you can guarantee that the first message that comes in is the first message that goes out. The second message that comes in is the second message that goes out. And this is great. But realize, if the first message is still on the way out, you may have 30 other messages behind them that could be delivered quicker with a standard queue than with a FIFO queue. So you have to determine the right queue to use based upon your application's requirements. So when should you use SQS? You're going to use it to reduce write contention on the database. You're going to use it to keep messages from being lost. And when you want extra assurance that no message is going to be lost, and you want to increase the availability of the app and the performance of the application. So SQS is an ideal means to increase database performance by decreasing the effectiveness of the write activity, even though the number of writes that would be going to the database will be the same, but they'll be spread out over time. So they're going to smooth disk performance, it's going to smooth CPU performance, and it's going to increase scalability. As we've discussed, databases are mission-critical business applications. So if they're so important, we need to make sure that they're available. And when we talk about high availability, what we're talking about is making sure that the application is available when you need it. So how do we design an AWS database for high availability? And simply the answer is we're going to put that database in multiple availability zones. So as a quick reminder, AWS divides their network into both regions, which are large geographic areas, and availability zones, which are basically a data center inside of one of those regions. So by placing your servers or your database servers or your database in multiple availability zones, even if one availability zone were to lose power and network connectivity, and your server were to crash all at the same time, no problem, because the other availability zone will take over. So some things to remember: when you're using multiple availability zones, it does not increase performance. at all. In fact, what's going on is your master database in your primary availability zone is going to do everything. And it's going to synchronously copy everything that's in the master database to all the other availability zones. So it's not a means to improve performance, but it is a means to improve availability. So I typically like this saying, 1 is none and 2 is 1. You always have to have at least 2 things of anything that matters, and that's when we're referring to high availability. So let's talk a little bit more about if you're using this high availability design, when will it fail over? And it's going to fail under the following circumstances. If your primary database fails, well then the backups in the multi-AZ environment will take over. But if an availability zone were to lose connectivity, at least the one where the master's housed, one of the backups will also take over. So if you change anything on the database instance and make it temporarily unavailable, the backups will actually take over. If you patch a system and do a reboot, especially if the reboot's implemented with failover, it will fail over to another availability zone. So there you know how we create high availability database designs in AWS. We basically put them in multiple availability zones so you have a copy running in multiple data centers.
In this lab, what we're going to be doing is configuring a simple database. And we're going to start out from the management console, and we're going to go to the database section. Now you've got multiple options here. You've got your relational databases, which are RDS. You have DynamoDB. You have Elasticache, which is a caching service. And then you have Neptune, and then you have a few other sets of documentation and things like that, and ways that you can optimize your database. So let's go create a relational database. So we clicked on RDS, and from here we're going to click Create a Database. You could pick it in one of 2 places. Now there's really a couple ways you can do this. You can pick a standard create and specify all the options, which is totally appropriate, or you can use easy create. Now, depending upon your database knowledge and depending upon what's necessary for your world and your environment, it may be best to use easy create, especially because it's going to be configured with best practices. So unless you're an expert on databases, this is our recommendation. Now, when you're dealing with some complicated web applications, you may have to use a standard create, and then specify every option. So you have to choose what's best for you. So we're going to pick a MySQL database, just because it's the most common one that's out there. In terms of scalability, there's many better options, but we're going to do something, it's a lab environment, and we're going to pick a free tier. So then we're going to go to Easy Create, and from here, it's going to ask us, is this something that's going to be in a production environment? And you can see what's the information that you're getting with regards to EC2 instances and the cost. And then they'll give you something for a dev test environment. But for what we're doing right now, we're just going to be using the free tier. Now it's going to give you the database identifier, so you'll be able to know what it is. You can logically tell this what you want it to be. It's going to give you a master username, and then you're going to have to come up with a password. So typically speaking, the auto generation of a password is the best way to go because it's going to give you something that's quite good. And we're going to create our database. And you can see the provisioning is occurring as we're speaking. So let's see what's going on. Let's see what it's telling us. So you can see we've got the database identifier the way we set it up. We see that you have the IAM role, which is based on the instance. It's going to be MySQL. We can see the size of what we're doing and which VPC it's located. And no, we have not set this up as a multi-AZ database. So let's look a little more into it. As we're exploring, we can see that it's still coming up. And that's why there's really nothing to monitor yet at this point, because it's still coming up. But it will be in a moment or so. But you can see you'll have some logging functionality that you could set up with CloudWatch. You can see that it'll give you very good information under the configuration section of what you've actually set up. And then under maintenance and backups, you can set up EBS snapshots, and you can take snapshots of your database with a DB snapshot, which is very similar to an EBS snapshot because it's going to be on an EBS volume. And then tags would be things that you specify. So that's pretty much it. That's all that's really necessary to set up a database. You can see it's creating right now. It'll take a few minutes, and then the database will be up. This lab, what we're going to do is we're going to be creating a read replica. So recall from the lectures that a database only has a limited capacity, and that includes both read and write because they both affect the CPU and they affect the hard drive speed and access. Because you can only have so many input-output operations per second. No matter what you do, you only have so much memory and processing power. So any way you can offload the primary database, you can make the database scale. And you make relational databases scale by reducing read activity from the primary database with the creation of read replicas. So in this lab, we're going to create a read replica. So in the previous lab, we previously created a MySQL database. And now we're going to take that database and we're going to create a read replica. So from the management console, we're going to click on databases and we're going to click RDS, or Relational Database Services. And what will ultimately happen is we're going to have a dashboard and we can see what databases we actually have. So let's click on our databases and you can see this is the database we created before, the database 1. So from here you can see that the status is available. You can see what availability zone it's in, the subnets it's associated with, and how to reach it with both the endpoint as well as the port numbers. So now what we're going to do to create a read replica is actually quite simple. We're going to go to the Actions and click Create Read Replica. Now the read replica is in the process of being provisioned, and it's going to be the database source because this is going to be the primary database. And this gives us an option for a database identifier. And then we'll have the region. We're going to pick the instance size, which is going to be the same as our last one. And then the storage type, we're just going to use general purpose SSD. And we're going to enable automatic storage auto scaling. What happens there is if your database is getting full, it'll just increase the drive space. You never have to worry about things. And availability and durability, do we create a standby instance in a multi-AZ sort of environment? And for high availability, you're definitely going to do so. This is just a lab environment, so we're going to keep the cost as low as possible. And we're going to move forward with everything else in the current conditions that they are. Click Create Read Replica. And it needs a name, and that's totally fine. And what's great about the console is it reminds you of things that you might not place. So we're going to call this for read replica. Now, obviously you're going to pick a name that's going to be descriptive and do something for you. But in this case, I'm looking for something that's quite simple because I want to know what they are because it's a lab environment and I want to remember how to delete them when we're done. So we'll re-click Read Replica. And now you can see what's going on. You can see that on our databases, we have the primary database, which is what we've set up before, which is being modified right now to let it know that there's going to be a read replica. And you can see what's going on with the CPU. It's not quite busy, and you can see that our read replica is now being created. And realistically speaking, that's about all it's going to take to set up both an RDS database and set up a read replica. What we're going to do is we're going to be taking the read replica that we created in a previous lab, and we're going to promote that to the master database. Now, there will be times where you're going to want to do this. For example, let's say your master database were to fail. You could take a read replica and promote it to become the master. So we're going to start by going to the management console, and then we're going to go to the database section and click RDS. And as soon as this comes up, I'm going to show you the databases that we previously created. Remember in the first lab where we created a MySQL database, which is the primary, and then we created a read replica. So let's take the read replica and promote it to be the master database. So we're going to click the read replica, and then we're going to go to Actions, and we're going to take Promote. Yes, we definitely want automatic backups because we want to make sure that things are good. We're going to keep the backup retention period for 1 day for right now since we're doing automatic backups. And we're going to select no preference for the backup window. Now, ideally, the backup window is going to occur at a time where your organization is not very busy. Because during the backup period, the system may have severely degraded performance or even be unavailable to take new reads or writes for a very short period of time. So ideally, you can do the backup window at a time where it's not going to be used heavily by the organization. So we're going to click Continue. And they're going to ask you, are you sure? And they're being promoted. So we're going to watch and see if the read replica has become promoted. Now you can see what's going on. We have to give it some period of time. You can see that the databases are changing. You can see that the status is being modified. So in a few moments, what you'll have is a promoted read replica to be the primary master database. Now, that's really all that's necessary to promote a read replica to a primary database. What we're going to be doing is setting up a DynamoDB table. If you recall from the lectures, DynamoDB is an extraordinarily scalable, serverless database, and it's a NoSQL database. And NoSQL databases store data in tables, and the tables have more flexibility than you would with a relational database. So we're going to create our DynamoDB setup and a table. So we're going to start with the management console. And under the management console, if we go to databases, we can choose DynamoDB. So we're going to create our DynamoDB table. And we have to come up with a table name. So in this case, we're going to pick something simple. We're going to call it product catalog. And you can see that you have to be careful. Your spell check might actually fix things for you. And in the process of your spell check fixing things for you, you can find yourself in a position where it won't accept things. And we're going to create a primary key. And we can set this to, realistically speaking, anything we need it to be. So in this case, we're going to set the primary key to an ID, and then for that we're going to set the number. And then we're going to click Create. And as you can see, our DynamoDB table is being set up and created. And that's actually, if you look, it's pretty fast. You can see that the system is up and it's running. We'll be able to look and see what's in this. So you can tell we don't have anything stored yet. You can see what's going on with regards to read-write capacity in the system. Well, you'll get your alarms or alerts based on what's going on. With regards to the capacity, you have to provision your read and write capacity. Now, it could be done on demand. And if your read-write capacity is done on demand, it will grow, as we discussed in the lectures, but it will not shrink on its own. So realistically speaking, you're going to want to provision your read and write capacity units to be as much as you need ahead of time. And then you'll be able to look at your indexes and see what's going on, or the types of tables that are actually there. You'll be able to see backups that are there. And really, that's all that's necessary for you to create a DynamoDB table.
In this section, we're going to be describing the AWS Virtual Private Cloud. So to begin, what is a virtual private cloud? A virtual private cloud is a logically separated private network on the AWS shared network. So what that really means is when you're using a cloud computing environment, you're using their network. But you don't want Amazon, for example, to be able to see your data. So you need something private on the Amazon network. But not only do you not want Amazon to see your data, you don't want other customers that are sitting on the AWS network to also be able to see your data. So the VPC is a virtual private cloud, and it's effectively your own private network on a shared network. But they're logically separated, they're logically isolated, so you don't have any security concerns on the VPC. It is effectively your space through the way it's logically separated. Now, because it's logically separated, you can conceivably be using overlapping IP address space with other clients in the virtual private cloud. And in many cases, you're going to be, because most organizations are going to be using the address space from the RFC 1918, which describes private IP address spaces. And internally, most organizations are going to be using similar IP address space. Now, externally, if you have to connect to the internet, you're going to need a globally routable unique IP address or a public address. But inside of an organization, you're going to use a private IP address. And with the Amazon VPC, addressing is a key component of your VPC. Now, let's talk a little bit about, what needs an IP address. Every actual network interface on an EC2 instance is going to need not only an IP address, but each interface is going to have to be on a separate subnet. So we'll talk a lot more about IP addressing and subnetting inside of this section. But at least for right now, it needs to be understood that the VPC is a private network. And because it's a private network, it's logically separated from everyone else. Every system on your network will need an IP address. And every IP address on your network is going to need to be unique. And it works like this. Let's say, for example, you live in a home and you want your mail to be delivered. The mail gets delivered to you based upon your actual address, which is going to include a number, a street name, possibly an apartment number, a state, a city, and a postal code. And through all of that, the post office knows how to deliver your mail to your house versus your neighbor's house, or at least hopefully. Now, the same thing happens in the IP addressing world. The network will deliver the messages to the appropriate destination, and this occurs by the IP address. Therefore, every device inside of your network needs to have a unique IP address. And in the event an organization were to purchase another organization using the same addresses, they'll either need to readdress every one of them, or they're going to have to translate addresses through something called NAT. And we'll talk about NAT, or at least other applications of NAT, when we're talking about connecting to the internet. So when we're discussing IP addressing, I'd like to cover the two types of IP addresses. We have IPv4 and IPv6. IPv4 are the original IP addresses that were created. And for the most part, they're the primary addresses we're using on our computing systems today. Now, the original IP address was a 32-bit address. And unfortunately, we just don't have enough addresses. So when people planned this and they came up with the IPv4 addresses, the internet was very small. It was used by some academic institutions and a few military organizations, and that was it. And no one expected that today everybody would have multiple computers per home and every one of them needs an IP address. So two things occurred. The concept from the Internet Engineering Task Force came up with private IP address space, and that's basically using the 10.0.0.0/8. They're giving you the 172.16.0.0/16 to the 172.31.0.0/16, and you've got the 192.168.0.0/16. And these are private IP addresses, and organizations across the world use these private IP addresses on their internal network. Now with IPv6, it's a 128-bit address, and because of that, the chances of running out addresses are not that small, or not that great. We have more than enough addresses for people that right now believe we should be able to address every computer in the world, both current and future. Where you typically see IPv6 addresses in use is with mobile phones. Every mobile phone needs an IP address, and they typically have an IPv6 address. So AWS loves to use the term CIDR, or classless interdomain routing. And where this really comes from is a long time ago, we had something called a Class A, a Class B, and a Class C address. And of course, there was a Class D, which was used for multicast, and Class E, which are experimental, which aren't being used. And the point of these classes is they either gave you a /8, a /16, or a /24, and that refers to the subnet mask. Basically, the larger the mask, meaning as it comes to the lower the number. So a /8 will have a lot more hosts that are available than a /16, and a /24 will have less than that. And in our professional version of this course, we do a much deeper dive on networking. But right now, just understand that a network can be subnetted, and we'll talk about why networks are subnetted. We subnet a network, or we take an IP address block and we break it down to smaller blocks for several reasons. We have to be useful and careful with the addresses we have. So a WAN link, for example, if you had a point-to-point connection, only needs 2 IP addresses. So we wouldn't use a class C or a /24 and actually waste of the available 253 addresses that are usable for that subnet. We wouldn't want to waste them, waste that whole subnet if we only needed 2. So we're going to use subnetting to break a large network into many smaller subnets. And we're going to do that for IP address space utilization. Now we need to be so careful with IP addresses, because if you have a router that's got 100 interfaces, each interface is going to have to be on a separate subnet. If you've got a server with 6 interfaces in it, each interface is going to have to be in a different subnet. So if all you have is the /24, and you deploy that on one subnet, you won't have anything for the rest of the interfaces on that device. So you're going to have to be very careful with your address space, and you're going to do that by subnetting. And I've given you an example on subnetting where we took one subnet and we broke it down into multiple other smaller subnets, and therefore we can be good stewards of IP address space usage. Now, one might ask, why can't we just use a giant subnet and stick every host in the available subnet? And we can't do that, because what happens is once we get a certain number of hosts in an environment, the hosts tend to send broadcasts to identify each other on the network. And as they send broadcasts, it'll fill up the network and fill up the CPUs of devices. So practically speaking, we're never going to use greater than a class C to place our systems on the network. And the class C would be a 192.168.1.0/24, where the addresses that are usable are from the .1 to the .254. Which, like I said, gives you 253 usable addresses. The .255, or the highest number, is used for directed broadcast, and the lowest number is used by the router for a subnet. Now, AWS does subnets a little different than the rest of the entire networking world, and it's pretty essential that you understand this. AWS reserves the first 4 IP addresses of a subnet and the last IP address, which is the broadcast. So effectively, out of any subnet, you're losing 5 IP addresses. So I had previously mentioned that with a WAN, typically you would only use 2. So a WAN link typically has a /30, but that can't work with an AWS network, because you lose 5 addresses automatically. So if you only have a total of 4, of which 2 are usable, and you're going to throw away 5, that can't work. So with AWS, the smallest subnet is a /28. Again, the smallest subnet on AWS is a /28. And the way a /28 would typically work, there'd be 16 total addresses, of which the 0, which is the network, and the broadcast, which is the all one broadcast at the end, would be used, which would give you a total of 16 minus 2, which would give you 14. Now, I remember, AWS reserves the first 5 as well as the broadcast. So with AWS, a /28 subnet only gives you 11 usable hosts. So you may need larger than a /28 even if you have a few devices, especially if you have auto scaling. Because if auto scaling scales out the infrastructure and brings up more compute instances, they're going to use IP addresses. And the same thing can happen with your load balancers and other devices. So make sure you have an idea prior to determining a subnet size, how many devices may actually need to be on that network, and how many of them are going to scale up, and make sure you have enough addresses, or you use a larger subnet, meaning a smaller subnet mask, to make sure you have more available hosts. Now, if subnetting breaks down a network into smaller networks, supernetting actually takes smaller networks and brings them up to a bigger network. Now, for network utilization, you'd realistically never do this because your smaller subnets have constrained broadcasts. But in reality, with routing, you may want to send a summary address. It might not make sense to have an IP address for every single subnet when you're trying to create reachability. You might just need to create an address that says, hey, everybody, for this classless interdomain routing range, send it to this next hop. And that's typically what's used. So when you can think of supernetting, you can think of route summarization. The reason I'm making a big point of route summarization when we're talking about the AWS network as opposed to bigger, more broad scale, say Cisco or Juniper networks in a carrier, is when you connect to AWS and you use BGP, like with a direct connection, you are limited to 100 routes. And 100 routes is absolutely nothing in the grand scheme of things of a network. So if you only have access to 100 routes, you need to minimize the space in your routing table. And you're going to minimize the space in your routing table through route summarization. As I mentioned in the professional course, or on the networking course, we'll have a much deeper dive in networking. But in the associate course, at least understand that the smallest subnet you can use is a /28. The first 4 and the last IP address of a subnet are actually reserved. And understand that auto-scaling uses addresses, so make sure you have enough available IP addresses if your infrastructure needs to scale up. So now you know what a virtual private cloud is, let's talk about the key components of the virtual private cloud. The key components include routing, internet gateways, egress-only internet gateways, NAT instances and NAT gateways, elastic IP addresses, VPC endpoints, VPC peering, network access lists, and security groups. So let's begin with routing and routing tables. So all VPCs effectively have a virtual router. And it's this virtual router that maintains a routing table or a map of the entire network. And the routing table builds a map of the network, and that's how the router determines how to forward traffic. And routers typically forward traffic based on the following. They take the most specific address in the routing table and when they do a matching algorithm. So if you have 2 addresses, for example, let's say you have a 192.168.0.0/16 with a next hop 1, and you have a 192.168.0.0/24, with next hop 2, the router is going to take next hop 2 because it's always going to use the one that's most specific. Now the routers are also going to have routes via things that are directly connected, meaning they're right attached, or they're going to have things that are dynamically learned via, say, a routing protocol like BGP, or something where a static route, meaning you manually put a route to go to the internet, here's your next hop to the default gateway. And they're basically the two, or you could be running BGP, which is a routing protocol. And BGP is the routing protocol that's typically used when you connect to AWS. So we'll talk a little bit about BGP. A deep discussion of BGP is way outside of this course. For people that really want a big understanding of BGP, we recommend the book Internet Routing Architectures by Bassam Halabi. It's a Cisco Press book. We also recommend reading the relevant RFCs. That's a great way to learn them as well. But for here, it's a very basic implementation we're talking about. And the first and foremost thing you need to know about BGP is it's a TCP-based protocol using port 179. So if you're not a routing and switching guy like me, but you do know that BGP is on your network, you need to be certain that if you're going to allow BGP traffic into your network, you can't have an access list or firewall type function blocking TCP port 179, or BGP will just not work. So the reason BGP is typically chosen as a routing protocol when you're using an application like this is it's extremely tunable. You have the ability to manually configure which direction you want your traffic to go. And there's a lot of knobs that you have in BGP to be able to determine, the preferred way to exit a network, the preferred way to enter a network. It's very easy to actually summarize IP addresses. For example, take a bunch of addresses or a bunch of routes and then summarize it into a single route. And it's that tunability and the ability to send specific routes in one direction versus summary routes in another direction to allow you to perform deep traffic engineering. And again, that's beyond the scope of this class, but understand that BGP is the routing protocol you're going to use when you connect to AWS. This routing protocol is a very light implementation. It only accepts 100 routes, for example. The Internet Routing Table at this time has well over 700,000 routes. So to give you an understanding, BGP is quite scalable, but for here we're using it for very specific purposes. And one of the good things are the BGP implementation with AWS supports some very simple things like the no export community. And it works with other communities and many other tuning features as well, but with the no export community is a very well-known attribute. And basically what happens is you send your routes to somebody else using the no export community, and then that organization doesn't send your routes to anybody else. And that type of filtering is very helpful, because if you send all of your routing information to your upstream neighbor and then they pass it to someone else, all of a sudden your VPC could be an internet service provider for half of the internet if you've made some mistakes in your routing. So that well-known no export community that's supported by BGP is terrific. But understand that BGP is a highly tunable, highly scalable, TCP-based protocol. And if you understand that, you'll have the basic knowledge of what you need for BGP for the Solution Architect exam. So now we'll begin to talk a lot more about NAT, or network address translation. And network address translation takes a private address and turns it into a public address. And most organizations have their systems internally with private addresses, and their firewall will actually translate their private addresses to public addresses, at least in a traditional data center type environment. Now in this case, we have multiple NAT environments. We're going to begin with the NAT instance. And the NAT instance is more of a legacy product with the AWS cloud. Not the preferred method of doing things today, and much more complicated than the preferred method, but we just wanted to cover it just in case you hear about it. So a NAT instance is effectively a custom instance, or a virtual machine that actually runs on your network. And it translates your private addresses into your public addresses. And in order for the NAT instance to work, it's going to have to be connected to an internet gateway, and it's also going to have a route to the internet gateway. And you're also going to have a public IP address on the NAT instance. So there's a little bit of complexity in getting this set up. Now this is for egress-only connections with a NAT instance. So basically that means that your internal devices will be able to reach out to the internet, and the return traffic will be able to come in. But if you had a web server, for example, the traffic would be blocked before it comes into your subnet. So a NAT instance is for egress-only internet traffic, meaning your devices request information on the internet and the data can come back, but external devices will not be able to connect to inside of your subnet with a NAT instance. Now let's talk about the new modern way to do egress-only NAT in the AWS environment, and that's with a NAT gateway. And a NAT gateway is a very simple, fully managed NAT service. And it's going to be a redundant NAT instance inside of an availability zone. And it's going to enable you to connect your internal devices to the internet and allow the return traffic back. So for example, if you have devices in a secure environment and you want them to be able to go to the internet and update their patches, for example, and you need them to download new software, you do this with a NAT gateway. They'll be able to reach out to the internet and their traffic will be able to come back, but they will not be in an environment where they can be attacked from the internet. So this is good security and it provides good connectivity. Now, if you need a high availability architecture, every availability zone is going to need its own NAT gateway. So two things to remember for both the exams but also real life is for high availability with NAT gateways, each availability zone is going to need its own NAT gateway. And with a NAT gateway, you can reach out to the internet, but and your return traffic is allowed back for, say, patching of an operating system. Now, if you're going to connect to the internet, somewhere on the line, something is going to need a public IP. Now, you could have a web server that needs to be accessed from the internet, and that's going to have a public IP. Of course, you could also place the IP address on a load balancer or something and have your web server in a private subnet, but how you organize that routing is up to you as the architect. But realize that anytime you want something accessible from the internet, it's going to need a public IP address. And Amazon does this with something called elastic IP addresses, which you may also see referred to as an EIP. And what an elastic IP address is, it's a public IP address that Amazon owns, and they maintain a pool of these addresses. And when you need a public address for, say, your web server or your load balancer, you borrow one from the AWS pool, and you have access to that as long as you would need it. And when you're done with it, you've returned it and AWS puts it back in the pool and they give it to another customer. So elastic IP addresses are public addresses that are available for you to borrow from the AWS platform for as long as you need them, and then they get returned to AWS when you no longer need them. Now we're going to discuss VPC endpoints. And VPC endpoints are the means that you're going to connect to other VPCs or other AWS services over the AWS network. And let me give you two ways that you could possibly do this. Now, if you weren't using a VPC, and you're going to use a VPC, but if you weren't using a VPC, what you'd have to do, let's say you wanted to connect to S3, is you'd have to go from your VPC, you'd have to go out to the internet, you'd go across the internet and you'd come back from the internet into the AWS cloud, and then you'd go to S3. Now, that's problematic for a lot of reasons. First, you're going on the internet, which is not secure unless you use some form of encryption. You're using up your internet bandwidth, which is typically limited, so you definitely don't want to use that. And when it hits the internet, you don't know what's going to happen. And the reason I say it doesn't know what's going to happen is the internet is a collection of internet service providers connected together. And while you can purchase guaranteed connectivity speeds to the internet, your internet service provider, once it leaves your internet service provider, anything can happen on all the different internet service providers for which your data travels on the way to the end. So performance is definitely not going to be over the internet what it could be if you had, say, for example, a private line. And in this case, what we're going to be using, we're going to use the AWS network effectively as if you had a private connection with a VPC endpoint. So by using the VPC endpoint, your data is going to traverse the Amazon network as opposed to the public internet. Amazon can guarantee the performance of their network, they can guarantee the latency, they can make certain their network is secure, and it's going to cost a whole less to ride the Amazon network because it's already theirs, as opposed to riding the Amazon network to the internet and then back into the internet, back across the AWS network. So you want to use a VPC endpoint for security and performance purposes. Now, realistically speaking, there's two kinds of endpoints. And there's an interface endpoint and there's a gateway endpoint. And an interface endpoint pulls a private IP address base from your VPC's address pool. It basically uses the private link service and it connects your VPC to either another VPC through VPC Peering or to an AWS service. Now, the alternative form is something called a gateway endpoint. And a gateway endpoint is a high security, high availability, high performance gateway service, endpoint service. And what it does is it realistically places a route in your VPC routing table to the AWS service. And you're typically going to use this when you want to connect to something like S3 or DynamoDB. But the point being, VPC endpoints enable your data to traverse the AWS network in a private and secure manner, whether you're connecting to an AWS service or you're going to be connecting to another AWS client who has their own VPC through VPC Peering. So what is VPC Peering? VPC Peering is a method to connect a VPC to another VPC on the AWS network. And VPC Peering provides secure and high performance transport across the AWS network. One thing to remember is that VPC Peering communicates over private IP address space, and if your traffic is inter-region, it's going to be encrypted. But there's a special component of VPC Peering in that it's not transitive. And because it's not transitive, it means if you have two VPCs, they can send their information to each other. But if the second VPC were to connect to a third VPC, VPC A that would say go through VPC B would not be able to connect to VPC C because it's non-transitive. So for those of us that are familiar with BGP from the networking world, think of the way IBGP works, where you have to fully mesh your IBGP peers. Well, guess what? When it comes to wanting transitive connections in a VPC environment, you're going to have to do the same thing. These are very similar in function. So let's talk about the two types of VPC peering architectures. If you don't need transit and you want a highly scalable environment with a little less redundancy, you're typically going to use a hub and spoke environment. And in a hub and spoke environment, what you have is you have your center, and that's going to be your main VPC, and that's going to connect to ancillary VPCs across the network through VPC peering. It's going to work great, and you'll have good connectivity. Now, if you need transitive properties, and let's say you have 10 VPCs and you want every one of them to talk to each other, well, then you're going to have to use what's called a fully meshed environment. And in a fully meshed environment, every VPC will ultimately peer with every other VPC. Now, that doesn't sound like that it's that big of a deal, and it doesn't if you have 2 or 3. But if you have 10, 20, 30, 50, 100 connections that you need to peer with, this becomes problematic very quickly. So a fully meshed environment adds up the number of connections super fast. So in networking, we use the term n times n-1 divided by 2. So for example, let's say you have 10 devices that need to peer. You would have 10 times 10 minus 1, which is 9, so 90 divided by 2, which is 45. So with with 10 VPCs, you're going to need 45 total connections. So you can see how that'll add up very quickly. Now bring that to 20, 30, 50, 100, and you're going to need a whole lot of VPC connections. So the workaround to that is, let's say you want to use a hub and spoke environment which scales well, and at the same time you want to allow VPCs to talk to each other. AWS has a function called Cloud Hub. And Cloud Hub enables you to break those rules of fully meshing your VPC pairs. And you'll put them in a hub and spoke environment, and then Cloud Hub, which uses BGP, will propagate the right routing information to all the VPCs, so that all VPCs have network layer reachability information or knowledge of each other's network, and therefore full network reachability is achieved. Let's discuss network ACLs. And network ACLs are used to keep unwanted traffic out of a subnet. So I know I mentioned that security groups keep unwanted traffic out of an instance. Network ACLs keep unwanted traffic out of a subnet. So network ACLs allow or disallow traffic based upon the configured policy. And with a network ACL, the default policy is to deny all traffic. So if you want something to get through a network ACL, make sure you have some permits. So when you're writing a network ACL, you're going to specify the source and destination address, the protocol, and the TCP or UDP port number. And by protocol, I mean TCP, UDP, ICMP, that type of a protocol, but it's based on one of the IP protocols. Now, a network ACL is stateless, meaning it doesn't watch what actually occurs. So it's not like a firewall where if you send traffic out, the firewall notices that you send traffic out and monitors the connection, so it allows you to return traffic but doesn't allow external traffic in. Network ACLs are stateless. So that means you're going to have to create your rules both inbound and outbound for them to work. Now, anytime you're dealing with access control lists, as a rule, and it's no different with Amazon, they're processed in order. And they're processed in order of the rule set. So the order is going to matter, and it's going to matter critically. Because if you deny something and then desire to permit it later, the initial deny will make it that it can't be permitted later. So you're going to have to be very specific and very careful how you write them and write them in the correct order. So we're going to show you how not to do this. Let's assume that you have an inbound rule, we'll call it 100, that says deny all traffic. And then after that, allow TCP port 80, which is web traffic, to come in from any source. And now you've got an outbound rule that says deny everything, but allow the TCP port 80 return traffic. What do you think gets through? Nothing. And the reason nothing gets through is it's all blocked by the first deny long before your permit. So if we were going to write this differently, let's say we had our rule 110 that says allow TCP port 80 traffic from any source and allow the return of port 80 traffic to any destination. Now it's going to work and all other traffic will be blocked. But the order matters. So let's say, for example, we have a subnet. Call it the 192.168.1.0/24 subnet. And we've got a lot of system use from that. We would like to permit that. But let's say there's also one host on that subnet that's used for security services that's mapping and doing a whole lot of things that we don't want to be accessing our mission critical application. No problem. We write the first rule that says block that one host address. And we can do it with a /32, so that specific host address. And then the next rule, let's permit that subnet. But that's the way you would permit an environment like that. Because what if we said deny the subnet and then permit the host? Because the host is part of that subnet, it'll be blocked. So network ACL matters, and it matters a lot. And in this diagram, we can show you that when it comes to security, you're going to use a multi-layered approach. It's like dressing for cold weather. Layer up. Well, with security, you're going to use a network ACL to keep traffic out of your subnet, and then you're going to use a security group on your instance. And you're going to also probably use some firewalling at the perimeter of your network too. But the point is, you're going to access it through multiple layers, and network ACLs keep traffic out of your subnet. Now a little more on security groups, and I keep covering the topic of network ACL versus security groups, and the reason is when we interview students, we find they often don't understand it, especially new incoming students. By the time they take our program, they understand it very well, but these topics come up a lot on exams. And part of the security architecture, you're probably going to use both, but you need to understand how and where they work. So a security group is basically a host-based firewall. in that it's stateful and it monitors the state of the connections, but it's applied to an EC2 instance or some AWS services. And in reality, you're going to use both. You're going to keep unwanted traffic out of the subnet with your network ACL, and you're going to keep unwanted traffic out of your instance with your security group. Now, security groups, really all you need to do is provide allow rules, because the default policy is to deny all traffic. Now, the good thing with security groups is they're stateful. So you're only going to have to allow inbound traffic, and they automatically know to allow the return traffic. And another good thing about security groups is they actually process all rules before they make a decision to send the traffic or deny the traffic. So the order of the rules in a security group is substantially less important than something you would find in a network ACL. Still, we recommend writing all rules with all types of firewalls or security appliances with good logic, but with a security group, it's not as critical because the rules are processed completely, not just discard or throw away in like a network ACL would be. If you've got a deny rule and then permit statements, everything could be denied before you even permit it. So with a network ACL, you're going to be very careful and very specific. With a security group, you're still going to be careful, you're still going to use good logic, but at least you've got some cushion as it pertains to the order of the rule, and you don't have to apply them outbound because they're stateful. In this section, we're going to be discussing optimizing performance and networking. And the three types of networking performance optimizations we're going to be discussing are going to be placement groups, Route 53, and elastic load balancers. Let's begin with placement groups. So placement groups are really where you're placing your computing instances. And where you place your computing instances can have a big impact on performance or availability or both based on how you do it. So let's begin with a clustered placement group. And this is going to offer the highest performance option. And realistically speaking, a clustered placement group is a very low latency group. And in this situation, what you're going to do is you're going to place your servers very close to each other. And not only close to each other, you may have a lot of your virtual machines sitting on the same physical server, and they may be in the same physical rack. So when it comes to latency, it's going to be the lowest, because if it's going across the same physical server, the networking is going to be super high performance and low latency. And if it's in the same rack, it's going to be on the same switch in most cases. So this is going to give you the absolute best in terms of performance, at least with regards to latency. Having said that, if you've got all your servers sitting in the same rack, or all your servers sitting in the same server, if you have a power failure, if you have a physical server crash, your entire operation is down. So this is a great option when you have an application that is extremely demanding of latency, meaning it has to be very low latency. But if you're going to do this, perhaps you want to set up another clustered placement group in another availability zone. Now let's talk about the next option, which is a partition placement group. And in this case, instances are going to be placed across racks. And by doing this, you're going to spread yourself across multiple servers, multiple switch ports, multiple power distribution units, which is typically where the servers are getting their power. So you're going to provide some level of additional redundancy. Now this is still going to be relatively high performance because your servers or computing instances, whichever you choose to call them, are still fairly close to each other. So by doing something like this, you've got much better availability than if it's all on the same rack, for example, or the same physical server, but it's still going to be very high performance. Now your next option, which is going to be useful for most people, and that's called a spread placement group. And what happens is you're going to spread your computing instances across multiple servers, multiple racks, and you can even do across multiple availability zones. And by doing this, you create an environment where there's no single points of failure. So this is going to give you much better availability. But as you spread your computing instances over larger distances, for example, across availability zones, which is effectively across data centers, you're going to have higher latencies. So choosing the correct clustered placement group, partition placement group, or spread placement group can really help you optimize performance, but you have to understand the trade-off. The closer you get your things together, the lower the availability, and the farther they are apart, the higher the availability, but the lower the performance will be. Now we're going to be discussing the domain name system, or DNS. Every device on the internet or a network is going to have an IP address. And you connect to these devices by their IP addresses. But here's the problem. How do you remember the IP address for every website and every computer system in the world? In practicality, you can't. So the domain name system is effectively a database which maps an IP address to a name. And by doing that, it becomes much more simple because we can remember Amazon.com, but we can't remember its IP address unless you're one of those lucky geniuses with the photographic memory. So here's what happens. You're on your computer system, and let's say you want to go to www.amazon.com. You enter that in your browser, and of course your browser doesn't have an IP address, so your computer then says, how do I get to www.amazon.com? And it then sends a message to the DNS server and says, what's its IP address? And the DNS server responds to the computer and it gives an IP address, and then the computer connects to Amazon.com via its IP address. So that's what the DNS system does. It maps a name to an IP address. And you can check this on your computer. If you're on a Windows system or a Linux system or a Mac, from a command prompt, type nslookup www.amazon.com. And you'll first see the response, which is your DNS servers, your name servers, which is who you ask the question to, and then you'll get the response of its IP address. And that's how you know how you can map a name to an IP address. Now we're going to be discussing AWS Route 53. And Route 53 is the Amazon implementation of the DNS protocol. So let's dive into Amazon Route 53. So as I mentioned, Route 53 is the AWS platform for DNS. And the AWS platform is a highly available, high performance, highly scalable, low latency DNS service. And the reason it works so well is it uses what's called anycast services. And what anycast services are is you use the same IP address for your DNS servers. And that gets a little tricky, so let me just explain it in simple terms. Your computer has a DNS server attached to it, and that's how your computer knows how to find the name that maps to an IP address, or the IP address that maps to a name. But what if your DNS server were to go down, or your primary and backup? Your computer wouldn't know how to reach anything. But with Anycast, what happens is the DNS servers all publish to the same IP address. And you then, when you connect to the IP address, connect to the one that's closest to your location, and hence that gives you the lowest latency. But for example, if your location were unavailable, the next location will still be available, published to the same IP address. So your computer, which is going to be programmed to attach to the Anycast address, even if your local Anycast address isn't available, a remote one will be. So this gives you built-in high availability, but it also supports latency. Now, Route 53 comes from port 53, which is the TCP and UDP port that's actually used for DNS services. So if you're curious where that came from, most likely Route 53 comes from port 53, which is the DNS port. Now, something else to know about the Route 53 implementation is it supports health checks. And we'll talk a little bit more about why health checks matter, specifically when you're using DNS for routing, whether it be performance or failover or other things, but we'll talk about that. You should know that the AWS Route 53 implementation supports most of the DNS types and records that you would ever need in an environment, but there are really about 4 records that we'd like you to know. And we'd like you to know these 4 records because they often come up on exams, but more importantly, in your career, these 4 DNS record types are going to be pretty important. So let's just talk about them. The first record type we'd like you to know is something called an A record. And an DNS A record quite simply just maps a name to an IP address. That's it. Fundamental records used everywhere, maps a name to an IP address. Now the next record we'd like you to know is something called a CNAME record. And a CNAME record is really just like a DNS redirect or an alias. So let's say you have a website and it's existed for a while and your branding department says, I'd like a new name, but you don't want, and you want to use the new name, but you don't want to lose all the customers that are coming to your current website. You would start your new website with your new name, and then you would create a DNS CNAME record that would point from your old domain name to your new website. And that way you'll keep your current customers that you've had from the old name, as well as your new and future customers that come from the new branding that you're trying to do. So a CNAME record just maps one domain to another. The next record that we really want you to understand is something called the name server record. And that really just tells you who your name servers are. But it's essential to know who your name servers are and who are your authoritative name servers, meaning the name servers that you truly believe. The last record we're going to discuss is something called an MX record. And an MX record is a mail record. And without setting up an MX record, your organization won't be able to receive email. So these are the 4 key records that we'd like you to know. As we begin our discussion into DNS routing policies, I want to begin this discussion with talking about health checks. So the AWS Route 53 implementation supports health checks. And really what a health check is the DNS server will actually reach out to the server and it'll say, are you there? And if it's not there, it can be used to make decisions, maybe route to an alternate location. Because if you map a name to an IP address, but the IP address isn't there, you'll have an outage. So there are routing policies that enable you to fail over or use the one that's closest to you, or use the one that's the lowest latency. But one of the things that has to be an enabling factor for these things to work is you need to be able to do a health check. And health checks will also be used when we talk about load balancers, but a health check is really just a way to say, server, are you there? So, AWS Route 53 has several route policy options, so let's talk about what they are. The first is simple routing. And simple routing is very simple. It maps a DNS name to an IP address. And that's it. The next type of routing policy you can set up with AWS Route 53 is something called failover routing, which basically says, go to your primary location, and if that's not there, go to a backup location. And this is terrific. It's a great way to add failover to an organization. It's not that complicated to do. Now we can start getting into geolocation and geoproximity routing, which we're going to do next. And the next thing is something called geolocation routing. And what's going to happen is when you go to request something, your source IP address is going to be looked at. And because your source IP is going to be looked at, the DNS server is, realistically speaking, going to know your location. So what it's going to do is it's going to send you to the server that's in the closest region. And that's going to work really well for global organizations. They don't want their people in Asia coming to New York, for example, and having the latency of that long haul network. They might still want that to work, for example, if the Asian network is down. So using geolocation routing really gives you a great opportunity to find the server with the lowest latency based on region. And from there, make sure that you also have some failover capabilities. Now, another version of location-based routing is something called geoproximity routing. And while geolocation routing basically works on a region, geoproximity routing actually works on like an availability zone. So the way this works is you have your DNS server set up, and it will find inside of your region the closest availability zone. So theoretically, you should have the lowest latency. Now, you could also set this up by latency, and instead of geography, which usually equals latency, but you could do it based on purely latency. So there's an version to do Route 53 called latency-based routing. And in this case, the DNS system looks for the server that has the lowest latency, and then it sends you there. So this gives you extremely good performance. The last two that we're going to talk about is something called multi-value answer. And really, this is a record that says route to anywhere. Any available server that you've got, use one of them. So it's not very specific, it's not very performance oriented, but it does allow for load sharing. And the last one we're going to talk about is something called weighted routing. And what weighted routing really is you can set it up to say send 75% of your traffic to one web server and 25% to another web server. So there are your DNS routing policy options on the AWS platform. So let's discuss load balancers. Load balancers are a fantastic way to increase the performance and the availability of your systems. And what load balancers do is they enable you to share load across multiple systems. So we previously talked about scaling up versus scaling out. And as a refresher, scaling up is moving to a bigger server. But when you have applications that are really going to grow, there's going to be a point where the largest and most powerful servers in the world still won't be able to meet the demands of the application. Plus, if you put it all on one server and the server were to fail, your systems would be down. So you're going to want to place it on multiple servers. So as you would scale out, for example, by adding multiple compute instances, you have to find a way to load share across these compute instances. Otherwise, you'll have one up and the others will be backup. And load balancers are really the way that you're going to do that. You can do some of this with DNS, but you're going to do a lot more of this on the load balancer side. So load balancers enable utilization of multiple servers to share load at the same time. So there's realistically speaking two kinds of load balancers that are available, and there's network load balancers which are operated at the network level, specifically layer 4 at of the OSI model, which is TCP or UDP. Now, the next type of load balancers, which have a lot more intelligence in them, are actually application load balancers. And they work at layer 7 of the OSI model, or the application layer. So they're typically looking at HTTP versus HTTPS. AWS has 3 types of load balancers available. They have application load balancers, they have network load balancers, and they have classic load balancers, which are available in both network as well as application forms. Now we'll talk about the types of load balancers offered specifically by the AWS implementation. The AWS implementation of a load balancer is called an elastic load balancer. Now, these load balancers are very high performance, and they do a great job of distributing traffic across your servers or your compute instances. There's some things to remember about these. One of the things that makes these so great is their auto scaling. So if your load balancer is running at full capacity, it'll spin up another load balancer. So you're always going to have the ability to have extra performance with these load balancers. But you do need to remember, if the load balancer spins up a new instance and it's another load balancer, it's going to need another IP address. So plan your subnets carefully, because if you have auto scaling of your compute system and your load balancers and many other applications on your network, if you don't have a big enough subnet size and auto scaling occurs, you could literally run out of addresses and then your systems just won't scale. So try and remember that. Now, these load balancers support health checks, and that's key for performance as well as availability. You don't want the load balancer to send traffic to a server that's down. So the load balancers will use health checks, and that's how they can increase availability, by taking unhealthy servers out of the rotation. Now, these elastic load balancers can also terminate SSL sessions, so they can really take a lot of load off of the web servers by terminating SSL sessions. So let's talk about the 3 implementations specifically. We're first going to discuss the elastic load balancer, which at the network level. So this forwarding is realistically based on the destination port. And it's going to look at TCP and UDP, but these network load balancers are really fast. I mean, they can handle millions of requests per second. So if you're looking for the fastest option on the AWS cloud, it's going to be a network load balancer. Good thing to remember is these load balancers are stateful, meaning they look at the state of the connection and they remember it the entire time. So they use something called sticky sessions. So they're gonna know where the user is and which server their traffic's gonna be. And it's gonna stay there for the entire session. And we wanna do this to make sure the performance is good, but we also wanna make sure we don't have to go through authentication processes and the such. So sticky sessions are gonna make sure that you stay on the same server during the entire time of your session. Now let's talk about application load balancers. And application load balancers work at layer 7 of the OSI model. So they typically look at HTTP, HTTPS. But they can actually look at the path provided in the URL, and they can even look at the method. Is it a get or a push? So these things have a lot of intelligence in them, and they're going to work at the application level. Now they're also stateful. And because they're also stateful, they're going to make sure that things are on the same service the entire time. Meaning that if I connect to server B, I'm always going to be on server B. Now, application load balancers are really a great way to deal with microservice-based applications. So that, keep that in mind. If you're asked a question on microservice-based applications and a load balancer, you're going to want to use an elastic load balancer. So let's talk about the AWS legacy load balancers. They're still available, but it's not recommended that you use them now. You should use an elastic load balancer, at least with the AWS network. But they're still available, so I want to at least cover them. The classic load balancers are available in both network as well as application forms. For the most part, they work very similar to the elastic load balancers in that they're stateful, and they can also terminate SSL connections. But these are older load balancers, and we really recommend that you use the elastic load balancer, either the network option if you need extreme performance, or the application load balancer if you're looking for more intelligence in the load balancer network. What we're going to be doing is creating a VPC. Now, we've been working in the default VPC, but in this case, we're going to create our own VPC, and we're going to use that so we can create the networking the way we desire it in future labs. So, in order to do this, we're going to go to the Management console, and under Networking and Content Delivery, we're going to click VPC.
Now the good news is they make it very easy with the Launch VPC wizard. So what we're going to be doing is we're going to launch our VPC. And the first thing we're going to do is we're going to create the type of VPC, and then we're going to add our networking. So typically speaking, your addresses are going to be one that are specified in that RFC 1918 address space. And with that, what's going to go along with that is the 10.0.0./8, but we're going to be using the /16. We're going to have the 172.16 all the way to 172.31/16. So the 172.16 all the way to the 172.31/16. And then we're going to have the 192.168.0.0/16. And these are going to be the private address spaces that we could be using. But in this particular case, we're going to be using just an IPv4 CIDR block. We're not going to be using IPv6. We're going to keep this as simple as possible. And there you go. So we're going to create the VPC. Notice it's automatically creating us a public one, which is in the private address space. Yet what's going to happen is it's going to be knotted out to public addresses for when we need to use public. So there you go. Quite simply, that's how our VPC was created. And you'll be able to see the VPC in the VPC dashboard. Here you can see the default VPC. Here you can see is the new VPC we just created. And under the VPC ID, you can see certain things. You can see its state. You can see how the DHCP is being set up. You can see the route table and any network ACLs that are there. Doing is creating a subnet. Now, a subnet can be created via this CLI, but it could be created so easily via the management console. We're going to use the management console. And the first thing we're going to do is we're going to go to the networking and content delivery section, and we're going to click VPC. And from here, you can see the VPCs that actually exist. So we're going to go to these VPCs, and we're going to look at them. Now, this VPC is the default VPC that's created when you launch your organization and you set it up on the cloud. And it's going to be something that's going to have typically loose security policies. It's designed to be easy to use and set up right from the go. Typically speaking, I like to create my own VPCs, so we've already created this VPC. So now let's go into this VPC. And while we're into this VPC, we can see some information about the VPC. But in this particular case, now that we're in the VPC, you can see what we can do. We can edit our classless interdomain routing. We can edit DHCP option sets, host names that we'd use under DNS, tags that could help us do things, or we could, of course, delete the VPC. But in this particular case, we're trying to create a subnet. So what we're going to do is we're going to click subnets, and we're going to make sure we do the subnet inside of this VPC. But we're going to do this by creating subnet. Now, if you notice, default plus the one we just created. And here what we're going to do is we're going to specify a name for the subnet. And what we're going to do this is we're going to call this private subnet 1. And we can pick which availability zone we want to use for the subnet, or click no preference. In this case, we're going to let it pick its default one because we're being very simple. And the CIDR block that we're going to use a 10.0.2.0, and we're going to go /24 because that'll give us enough IP addresses that we don't have anything to worry about. We've got the name, we've got the private subnet, we can add a tag, or we can just create the subnet. Now let's look back at our VPC and look at the subnets that are actually there. Here's the new VPC. Under VPC, let's look at the subnets that exist. And there you can see we have two of them. We have the 10/0.0.0/24, which is the public subnet that was created. And we created a private subnet with a 10.0.2.0/24. There you have it. That's how you create a subnet inside of your VPC. What we're going to be doing is we're going to be creating an elastic network interface, and we're going to be attaching it to an EC2 instance. Now, when you boot up an EC2 instance for the first time, it already comes with a network interface. But there might be times where you want to dual home your system. For example, you might want it to be on a public subnet or a private subnet, or there might be times where you want to place it on two separate private subnets and have different security groups for different access for different people. So these are the kinds of things that you could do by creating multiple interfaces. So to create the interface, there's a few things we're going to have to do. We're going to go to EC2, and under EC2 what we're going to do is we're going to create a network interface. And you can see that under this section, network interface. So from here, we're going to create a new network interface, and we're going to give it a name. And I'm into very simple names, so we're going to give it something like GCA, Go Cloud Architects, Lab, INT. In reality, you're going to use something much more descriptive, something that's going to help you. But in this case today, what we're going to be doing is we're going to pick something simple. Now, under subnet, you're going to have to create a subnet where you want this to be. Now, recently I just created a new subnet, so we're going to choose one of the new subnets that I just created, and it's going to be a subnet in US East 2A. So I just created a subnet. I called it new subnet, so I'm going to use that subnet. Now we're going to have to attach in a security group, and I'm going to use the default one. The default one is a bit open because it allows SSH or port 22 in from anyone in the world, where in reality we're going to limit it to just the subnets that need access to SSH access. But for right now, we're just going to use the default subnet because we're only trying to work on one thing at a time because we want to create a good learning environment. So we're going to choose the default security group, and then we're going to create this network interface. And now we've created a network interface, but the network interface is still sitting there sort of floating around in the ether. We have to attach this network interface to an EC2 instance so it could be used. So we're going to do just that. We're going to look at our two interfaces, and what you can see is this on the bottom is the default interface that came with the instance, and you can see the public address, you can see its private address, and you can see the owner. Now we're going to go to the new interface that I just created. Under Actions, we're going to click Attach. So now when we choose Attach, we're going to have to choose the instance that we want to attach it to. And in this particular case, we're going to choose it to the only instance that exists. Click Attach. Now what you should see is you should see these network interfaces, and they should both say in use. And that's telling you, very good, they're in use. You can also see they're on separate subnets. And there you have it. So let's go to our EC2 instance. Let's see what's going on with the instance. And on this instance, you'll be able to see lots of things. Under networking, for example, you'll be able to see the instance ID. You'll be able to see the two interfaces and their respective subnets. That's it. Fairly simple. That's how you create an elastic network interface, and you attach it to a running instance. We're going to modify the default security group. And typically speaking, with a security group, when you're building it, you want to lock it down to just the subnets that need access to certain things. So in other words, if you have a direct connection between your data center and your AWS cloud, and the only people that need to access this are basically, say, working in a NOC where they're doing network operations, and part of the network operations actually includes managing the cloud environment, and let's say they're in a 10.1.1.0/24 subnet, in the security group you would only allow their subnet in. Because we're not coming from a direct connection or a VPN connection, and we're going to be doing things from a remote access environment, and because this is a lab, we're basically going to set up our security group to allow several protocols. And when it comes to security groups, we only have to permit statements because everything else is going to be denied. And the security groups actually look at the state of the connection. So what ultimately happens is they're stateful, like a stateful firewall. So they're going to watch the traffic that comes in, and they automatically know to allow the return traffic back out. And if they were stateless, like a network ACL, you'd have to specify rules in and allow traffic out. But they are stateful, like a stateful firewall, and therefore we only have to allow in. So what we're going to do is we're going to go to our EC2 environment. and we're going to look at the instances that we have running. We have one instance that's actually running. So we're going to click on this instance. And under security, what we're going to do is we're going to modify the security group. And you can see with the current security group that we have, we're allowing port 22 and only port 22, and that's SSH. But let's say we want a little more. So let's allow in HTTP traffic along with HTTPS traffic. And you can even give yourself a description to make it a little easier for you. So in this case, we're going to add a rule, and we're going to allow the protocols that we want to come through. And in this particular case, we want to allow HTTP and HTTPS traffic. So the first thing we're going to do is we're going to pick out HTTP, which is going to be port 80, and we're going to allow it from everywhere. And we can say allow web traffic. And we're going to add an additional rule to this, and we want to allow HTTPS. So we're going to look for HTTPS, which is going to be port 443. Again, we're going to allow this from everywhere because HTTP and HTTPS, unless it's an internal web server like for a corporate intranet, we're going to want these available to the rest of the world because they're going to be a public web server. We're going to save the rule, and that's it. As you can see in this inbound security group, what we're actually allowing is web traffic via HTTP, or also referred to as www. We have HTTPS and we have SSH, so that's what's going to be allowed into this instance. That's it. That's how you set up a security group on an instance. What we're going to do is we're going to create a network ACL. Remember that security groups are applied to instances, but network ACLs are applied to subnets. So because they are part of the networking function from the management console, in order to create a network ACL, we're going to go to Network and Content Delivery, and we're going to click VPC. So after we click VPC, it's a fairly simple process. We're going to go to Network ACLs on the left side of the page. And here we're going to quite simply create a network ACL. And we're going to name it. So when you do this, you're going to want a naming convention that's going to be very descriptive, so you can remember which network ACLs are applied to which subnets. But in our case, this is a lab environment, and because it's a lab environment and you're going to need to take these things down so you're not charged, pick something that's going to be very easy for you. So for me, I'm going to call it New Net ACL, just because I want to be able to remember it so I can delete it. And I'm going to create this network ACL. But of course, you have to select the VPC, and we're going to from the drop-down, select the VPC. Now from here, you can see we've got a new network ACL, and it's not associated with any subnets yet. But let's make our policies before we associate it with a subnet. Because if we associate it with a subnet before making the policies, and we have systems on that subnet, we're going to break them. Because the first rule of the default new ACLs when you create them is to deny everything. Which means if you've got a web server that's up and running and serving traffic, and you place this on during the time you're editing the rules, it will be completely unavailable to serve traffic. So let's create our rules right now. Now when we're creating these rules, they have to be applied in a sequence because they're going to be read in sequence. And we're going to leave a space of about 10 in between everyone, at least, because there's going to be new rules that you're going to need to create. A common example is, let's say you've got one bad host coming into your web servers. You can create a deny rule for that one host by placing it in front of somewhere where it needs to be earlier in the sequence, because we might want to deny one host but still allow an entire subnet. So you would do the deny before the permit for the subnet, because if you permit the whole subnet, the traffic is going to be through. So let's say you had a rule 100, for example, that said allow traffic from the 192.168.1.0 subnet in all traffic, and then you have one host that's infected with malware. You might want to create a simple deny statement for some one single host on that subnet. So that's why we want spaces, because you're going to find you're going to have to create new rules, and if you don't have spaces, you're going to have a problem. So we're going to pretend that this subnet has web servers and absolutely nothing else. And because they're web servers, there's only two kinds of traffic we need to allow in: HTTP and HTTPS. So good security practices involve only allowing necessary traffic in and nothing else. So we're going to create a rule 100, and we're going to say HTTP is allowed, source any allow, and then we're going to create a new rule. We're going to call it rule 110, 110, and we're going to allow HTTPS traffic in from any source. And then we're going to save the changes to this. And that's the inbound rules that we need for the subnet that only has web servers. And see, HTTP is allowed in, HTTPS is allowed in, and everything else is going to be denied. So now let's make our outbound rules. And because network ACLs are not stateful, we have to create the same outbound rules to allow the return traffic out. So in this case, we're going to create a new rule. We're going to call it rule 100. We're going to allow HTTP return traffic back out. And then we're going to add a new rule. We're going to call it 110. And in this particular case, we're going to allow the return of the HTTPS traffic. And we're going to save the changes. Now we've got a network ACL that for the inbound rules allows HTTP and HTTPS only, all else will be denied. And for the outbound rules, we have the same thing. HTTP and HTTPS return traffic is allowed, and everything else is denied. Now we have to associate the network ACL with a subnet. So we're going to click Edit Network ACL Subnets, and I had previously created a subnet called New Subnet. So we're going to associate that network ACL. And that's it. We're going to save changes. That's how you create a network ACL, and that's how you apply it to the subnet. I've created Internet Gateway, and we're going to place a route to the Internet Gateway called a default route. Now what a default route is if there's no more specific route in the routing table, send your traffic this way. So organizations typically have a route for everything they need to have in the router, and then they typically have a default route which sends traffic to the internet. The exception would be if the organization is connecting to multiple internet service providers for which they'd be running BGP, but very often, even on their network, while the router is connecting to the internet service providers will have full set of internet routes, they'll typically propagate a default route through their network. And that basically means if you don't know how to go somewhere, follow the default route, and the default route goes to the internet, because on the internet, that's where things will be outside of your organization. So we're going to do this by going to the VPC dashboard. The reason we're going to go to the VPC dashboard to create our internet gateways is that's where these kind of network functions occur. So we're going to click VPC under Networking and Content Delivery. Now when we get to this area, we're going to create an internet gateway. So you'll be able to see the internet gateways on the left side of the menu. And what's going to happen is we're going to create this, and it's going to ask us to create some steps along the way, and we're going to do just that. But in this particular case, we're going to create an internet gateway. Now we can name it anything we want. We're going to call it GCA, Go Cloud Architects, then we're going to pick Lab, because it's a lab, and then we're going to call it Internet, and then GTY. And this is going to make it easy for us to identify what it is. Now, of course, you could add a tag, in which case we have name, and we've got the value of what we're calling it. We're looking for something very simple. And now we're going to create the Internet Gateway. Now the Internet Gateway actually exists, which is terrific. Now, we're going to attach it to a VPC, but you'll see what happens when we try to attach it. It's going to tell us that we don't have any VPCs to attach it to, so we're going to create a new VPC. And we're going to call this GCA New VPC. And typically speaking, when I deal with networks, I typically delete the default VPC and create my own with my own subnetting and my own security standards. So in this case, we're just creating a VPC, and we're going to give it a CIDR block. And we really want to use a CIDR block that's not going to overlap with what we currently have. So let's try the 192.168.0.0/16. We're going to click Create VPC. There you go. We've created a new VPC inside of the RFC 1918 private address space of 192.168.0.0/16. Now that we've created this, we can make sure that it's attached to the VPC. We just created this. Now let's attach it to a VPC. And under our VPC, here's the new VPC that we created. There you go. We're going to attach an internet gateway. Now, we're going to have to add a route for unknown traffic to go to the internet. And what we're going to do here is we're going to just go to the routing table of our new VPC. So here's our new VPC. We can see about it. We're going to look at our route tables. For here, we're going to have to pick out our new VPC. Now, it's a little bit tricky where they actually place information in terms you're going to actually have to find out what that VPC is called. So I wanted to show you what it's going to look like. Now let's go back to your internet gateways, because the internet gateway will show us the one that we just created, and it's going to give us some good information, our VPC ID, and it's going to end in D Delta 1 F Foxtrot. And that's how I try and remember them. There's too many letters. I try to remember them by the end. So D1F. We get it. We know what it's going to look like. So let's go back to our route tables. We're going to find the one that says D1F, which as you can see is over here. We're going to go to the routes, and we're going to edit our routing table. You can see we have a route to the locally connected subnet inside of our VPC, but we're going to add a route, and we're going to add a 0.0. It automatically populates for the default route because it's a very common route. And then what we're going to do is we're going to choose our internet gateway. We're going to pick our internet gateway, and we're going to save the route. Now that's really all you need to do. We've created a VPC, we've created an internet gateway, and we've created a default route. So instances inside of that VPC that are on those subnets are going to look inside of the routing table, and the routing table that, of course, we'd have to associate the routing table with those subnets, but they're going to be able to reach out to the internet because they have a default route. That's it. That's how you create an internet gateway, and that's how you create a default route to the internet gateway. We're going to be setting up Route 53, which is the Amazon DNS or domain name system, at least the Amazon implementation. And we're going to set up something called a hosted zone, and we're going to set up something called an A record. And really, we're just going to create a simple record, the A record, that's going to map an IP address to a domain name. Very simple, the simplest form of DNS. So under networking and content delivery, we're going to click Route 53. Now, in an optimal world, we're going to register a domain, and we're going to import that into the domain management system. Having said that, this is a lab environment, and we want to make it as inexpensive as possible for the people that are here. So we're going to go to DNS management. We're going to click Create a Hosted Zone. Now, while we're here, we're going to need a domain name. Now, if you have a legitimate domain name that you own, feel free to use it. If you register one, feel free to use that. If you're just making up one to do the lab, that's completely fine. So we're going to call this gcadnslab.com. And you can put a description if you desire, and then we're going to just create the hosted zone. And as we do this, this is great. We've created the lab and the hosted zone. And you can see we have a name server record, and these are already there. But we want to create an A record. And by creating the A record, we're just going to click Create Record. And we're going to click Simple Routing. Remember, you've got multiple options: weighted, geolocation, latency, failover, and multi-value answer. And we covered them deeply in the lectures. But we're going to use Simple Routing here. We're going to create an A record, and we're going to create this just simple as, we'll even use the term blog because it's fine. It's the one that was suggested. And in the value, here's where we're going to put the IP address of our system. So I'm going to take an IP address that I created, 3.12.241.1, and I'm going to create the record. And that's pretty much it. We've created a record that maps this domain name to this IP address, and you'll be able to access the website, assuming this was a web server that you created from a browser. Up a very simple DNS record. Now, if you were going to set up multiple sets of web servers behind DNS, you might want to use a different type of routing, whether it be a latency routing, a failover routing. And in order to make that work, you're going to have to set something up called a health check. So the first thing we're going to do is we're just going to create a simple health check. And we're going to do that because we've shown you how to create hosted zones. You can see where you can easily change the routing policy, but knowing how to do a health check is absolutely critical. So let's create a health check. So the first thing we're going to do is going to go to Networking and Content Delivery. We're going to click Route 53. And here what we're going to do is we're going to click Health Checks. And from here, we're going to do something very simple. We're just going to click Configure a Health Check. And what we need to do here is we need to come up with a name of the health check. So we're going to call this the GCA Lab HEALTCHECK, just a name I made up. And we're going to monitor, the endpoint or what other we want, things that we're looking to monitor. And we're going to have to place the IP address. And in this case, we're going to use our web server, which is 3.137.194.184. And realistically speaking, we're going to click Next. We can set up an alarm, for example, if you want to be notified if something doesn't go well, or you don't have to. We're not going to do this because this is just a test. And then we're going to click Create a Health Check. And right now the status is unknown, and what's going to happen is it's going to start sending messages and check the status, and the status will come up as complete in a little bit. So that's really all you need to do to set up a DNS health check. You're basically sending a message. It's going to check a page on your server, and if that page is no longer there, it's going to mark the instance as healthy, and it'll remove it from your DNS rotations. Load balancer. And if you recall from the lectures, the reason we're setting up load balancers is twofold. If we want to scale up, meaning increase the size of a server, we can just get a bigger server. But no matter what we do, there's never going to be a server that's going to be big enough for our needs when we're dealing with global enterprise environments. So we have the opportunity to scale out, which means add more servers. But if you're going to use a dozen servers or several servers, you're going to have to find a way to load share across those servers. And you're going to load share across those servers with a load balancer. Now, we're going to create a load balancer. Now, with Amazon, they're considered to be elastic load balancers, but they're listed under EC2 because the load balancers are actually running on EC2 instances. So let's click EC2. And you'll notice in this area you have the opportunity to set up a load balancer. So we're going to set up load balancers. And we're going to create one. Now, when you're creating a load balancer, you've got a couple of options. You've got the classic load balancers, and whenever possible, they're legacy. It's recommended you use one of the newer load balancing options. So you can use an application load balancer, and this is really great if you're looking for intelligence at the application level, routing between microservices and the such. If you need extreme speed, you're going to use a network load balancer. A network load balancer can be much faster and maintain extremely low latencies. So know which one you want to use. If you're dealing with microservices or containers, as a rule, the application load balancer is a great choice. But if you need pure performance, you're going to go with a network load balancer. I come from the network world, so I'm going to just pick a network load balancer because I've been working with them forever. And realistically speaking, what you're doing is you're going to say that it's internet facing or internal, because you could use one for your internal purposes or your external purposes. Maybe you need to load balance across 10 servers for your internal users, then you would be an internal one. Or it can be an internet-facing one for your web servers. So we've got our listeners. They're going to listen and make sure things are they're going to listen for connection requests. And when we're dealing with HTTP and HTTPS, they can terminate these sessions on the load balancer, which is going to offload a lot of the work from the actual web servers themselves. And we're going to just select all of our availability zones because we want to be able to use the load balancer wherever we place our things. And now we're going to configure our security settings. But before we do that, we actually have to name it. So like anything else that needs a name, now generally speaking, come up with a naming convention that's going to make it very easy for you to identify. In the lab environment, pick something that's going to be easy to identify so you can find it and easily delete it so you won't be billed. So let's just call this GCA Mike ELB. Now, generally speaking, heavy security you should set up. You should set up your firewalls, your intrusion detection prevention system, your network ACLs, as well as your security groups. And then even on your systems, you should have a host-based firewall. But in this particular case, we're just going to set up our routing. And what we're going to do is we're going to come up with a target group, and we're going to set it up the way that we need to do this. So we're going to look at the target group, we're going to come up with a name of the target group, and it's going to call GCA Mike ELBTGT. So I want it to be something simple. And we can use the standard traffic port. What it's going to do is it's going to be healthy, and it's going to periodically check it every few seconds, and if it misses a few health checks, it's going to time out. We want it to time out faster, so we're going to pick an interval of 10 seconds. Now what we want to do is we want to share the two instances that we have running, and basically what's going to happen is the load balancer is going to share amongst all the instances we've set up. So I previously configured two identical instances. Next we're going to review our configuration, and you can see that we've set a load balancer, we know what it is, it's an internet-facing one, which subnets we're allowing it to be used on, and then you can see the targets for the instances. Now there you go. We've successfully created an elastic load balancer, which is being provisioned, and it's going to load balance traffic between our EC2 instances.
So this section is on security of the VPC on the AWS cloud. So we're going to cover a lot of topics in this section. And the first topic we're going to cover is who is responsible for security. Then we'll talk about the principle of least privilege, a little bit about industry compliance, identity and access management, also referred to as IAM. We'll discuss multi-account strategies, network ACLs, security groups, and WAF. And then from there, we'll touch upon intrusion detection and prevention, distributed denial of service attacks or DDoS attacks, and then we'll talk briefly about the service catalog and the systems manager parameter store. So now let's talk about security and who is responsible. And AWS uses something called a shared security model, and we'll talk a lot more about that. But in the security model, the customer is responsible for the security of their VPC, and we'll talk a little bit more about that, whereas AWS is responsible for the security of the cloud. So let's talk at least a little bit about the customer responsibility. And that the things that you're going to have to do as the customer is you're going to have to manage your access lists, your security groups, your ACLs, and all of the things that you would naturally do to maintain the security of your servers, your systems, or appliances inside of your data center. AWS will handle things like making sure the EC2 instances are strong. So for example, they'll make sure they're up to the latest hypervisor when it comes to security to make sure the servers are there. They'll make sure they have physical security of the cloud. They'll make sure that the cloud, for example, the CPU vulnerabilities that existed with AMD and Intel's CPUs, they'll make sure they're patched in firmware. So what they're going to do is make sure the infrastructure is secure, and what you're going to do is maintain the security of your VPC. Now in this graphic, you can see a little bit more about the AWS shared security model, but really it all boils down to is you're responsible for the security of the VPC, and they're responsible for the security and the integrity of the cloud. To begin, let's cover the most important topic of security, and that's simply the principle of least privilege. And the principle of least privilege is also referred to in the military as need to know. And what that really means is people are given access to the information that's necessary for their job or their mission and absolutely nothing else. Well, when it comes to designing your systems, only give whatever is necessary to your people. And the reason you're going to do that is you want to make sure they can't accidentally delete system files, they can't accidentally create systems that are going to cost a fortune, or you also don't want them accessing critical trade secret information that they could take with them to a competitor. So the principle of least privilege is one of the most critical components of security, and you definitely want to use that with your AWS VPC. Only provide access that's necessary for people to do their jobs. And if for some reason an employee is terminated, instantly remove them as one of your qualified users. But also if people's jobs change, for example, let's say they move from an engineering role to a management role, they may not need engineering access to systems. So you're going to remove privileges that are unnecessary for your users, and you're going to make sure your users have the appropriate privileges for them to do their job well, and absolutely nothing else. Now, we'll talk a little bit about industry compliance. And what I mean by industry compliance is several industries are highly regulated. And they're regulated with regards to security, things like encryption and data protection. They're regulated with regards to how long you need to maintain your data. And AWS supports many of the industry compliance standards that are actually out there. And a full list of all the standards is far beyond the scope of this course, but know that AWS supports critical industry compliance requirements. We're going to cover a few because you may see them in test questions and they're extremely common. One of the standards that are supported is something called PCI DSS, and that's really an industry standard for payment cards, like a credit card. There's several ISO standards related to cloud computing and other matters, and AWS is definitely compliant with those. FedRAMP is a standard for which AWS is compliant, and you need to be compliant with FedRAMP to deal with the US federal government. And AWS also meets HIPAA requirements, and HIPAA is basically a US privacy law related to healthcare and how we manage as healthcare providers organization. I spent a little bit of my youth practicing internal medicine as a nurse practitioner, so I'm very familiar with the HIPAA laws. But understand that AWS supports many of the industry compliance things. In this section, we're going to be discussing identity and access management. And identity and access management is a critical component to information security. And it's often misunderstood, so we're going to describe it the way most of the industry calls it, which is actually AAA, which is authentication, authorization, and accounting. Now, this is an older term, but it's very clear, and once you understand it, you'll never forget it. So we're going to use this means to describe IAM. So authentication basically identifies the user. And when you go to access a system on your computer and it asks for a username and a password, part of that is because they want to authenticate you. And if you have the right username and password, there's a good chance that you are who you say you are. Now, the next component is something called authorization. And authorization basically says, are you allowed to access resource? If yes, grant access. If no, block you. And then accounting is really finding out what you've done once you're actually on the network. What systems have you accessed? Have you gone to this hard drive? Have you gone to this server? That's really the accounting components. And accounting is a really key way to figure out what people have done and how to fix things and process improvement as well as good security. Now, AWS actually takes an IAM and they break it down into two things called users and roles. Now, an IAM user is a person. An IAM role is a system accessing another system. So if I were to log onto a system, I would be an IAM user. If my computer or my server needed to access DynamoDB, it would need an IAM role. So DynamoDB would know that it's an authorized system to access that information. So let's talk about a few more key components of IAM. AWS actually uses IAM to control users, groups, and access control policies. And the way you're going to use this is the easiest and most scalable way, because of course you could create an IAM user for everybody and then assign permissions manually. But imagine if you have 100,000 employees or more and you literally want to try and make an IAM user for every single person and give them all individual levels of access. That would be very challenging. So what most people do is they're going to create a group. And inside that group, they're going to provide permissions to the group. And then they're going to add users to the group. So for example, let's say you have people that are database administrators. You would create an IAM group called database administrators, and you would give those database administrators access to whatever information they needed to do whatever they needed on those databases. So that's really how the concept of IAM groups work. And for the most part, that's the scalable way that you could do it. You could just create an IAM user and assign permissions, but in most cases, especially in an enterprise environment, you're going to create groups and then you're going to add your users to the groups. And this is something you would do whether you're working with, Microsoft in an Active Directory environment, or for the most part, any other type of technology systems. So, AWS, as part of their IAM, has two concepts. They come up with the concept of principles. And they break this down into several. So there's a root user, and the root user, you can think of them as the king. The root user, or queen, whichever you like, but the root user has access to everything on the system. They can do anything they need, including delete the entire VPC. So you really don't want to use that root user account. You want to use that account and then you want to create other accounts. So the root user account is effectively the same thing as if you were to take a Linux system. You wouldn't log into your Linux system as the root or the super user and do things. You would do that to do administrative work, and then you would reduce your privileges as a user to use the system most of the time. Same thing's really going on here. Then of the principals, you have IAM users. And they're the people that are actually using the systems. And then you have IAM roles, which are specifically for the systems accessing other systems. Now we're going to be discussing roles and security tokens. And roles, specifically IAM roles and security tokens, play a big part with regards to security on the AWS cloud. And there's, realistically speaking, three kinds of roles that we'll discuss. We'll discuss EC2 roles, we'll discuss cross-account roles, and then we're going to discuss identity federations and, to some degree, single sign-on, but that's much more of a topic for the professional exam. So IAM roles, specifically for EC2, create a dramatic enhancement in security over what life would be like without it. So let's say if you didn't have an IAM role and you had an EC2 instance that wanted to access DynamoDB, the EC2 instance would have to maintain a username and password to then access the DynamoDB instance, or in this case, the DynamoDB service, which would work. But what happens if your EC2 instance is hacked? You're going to now gain access to the passwords to DynamoDB, as well as any other passwords that are stored on that system. So that's really not a great way to do things from security. So the way the IAM role service works with AWS is you assign an IAM role to an EC2 instance. The EC2 instance attempts to access DynamoDB, and through the API, it's given a token that expires. But it then uses that token to then access the DynamoDB or whatever service you've set up on the AWS cloud. And therefore, you're not storing passwords and you're using temporary tokens. And temporary tokens are fantastic because once they expire, they can't be used again. So there's no password stored on the system and you're using temporary passwords. So even if the server were to be compromised and someone got access to the token, it can only be used for a period of time. Now, a cross-account role is really used with partner organizations. So for example, let's say you're an organization and you've developed a partnership with another organization that's in a separate VPC. You can create a cross-account role that enables a user in your organization to access symptoms in another organization. So that's really what a cross-account role is. It enables one VPC to authenticate and authorize an account for users in another VPC. So the way a cross-account role works is a role is created for the external user. The external user will then connect to the AWS token service and receive a temporary token. And then the external user provides that temporary token to access the other VPC. Assuming they're authorized, they get access to what they need to. So now you understand the role of roles and security tokens, cross-account roles, and we'll talk much more about identity federations. So let's discuss identity federations. Managing large environments with hundreds of thousands or millions of users that all need IAM can become quite cumbersome. And one of the best ways to do this on a scalable manner is to use something called an identity federation. And an identity federation enables you to federate or connect to an external identity provider and then use their identity management services on your AWS VPC. So I'll give you two kinds of examples. One is you could use something called your Windows authentication system, which typically works with Active Directory. So you have a user that logs into their Windows system, they're authenticated by the Active Directory controllers inside of an organization, and then that identity is then passed through so they can access resources on the AWS cloud. And by doing that, they won't have to authenticate to the AWS cloud after they've already authenticated to your Windows systems. Another way to make this scale is you can federate to an external identity provider, like Facebook, like Amazon, like Twitter, like LinkedIn, even Apple. So by doing this, you can basically take users from another organization, authenticate against them, and allow them access to your system. So this can be something that scales really well. Now understand, when you make connections to an external identity provider or Active Directory, you're typically using something called Security Assertion Markup Language, or SAML 2.0. And that's an industry standard language to connect to other identity providers. And that's the way it would work with the AWS cloud. It's the way it would also work with the Google cloud. So one of the benefits of identity federations is it facilitates single sign-on. So with single sign-on, all that really happens is you sign on once to a system somewhere, like your Active Directory controllers, and all of a sudden now you don't need to sign on to receive access to AWS resources inside your VPC. So let's talk about something very briefly. It's more of a topic for the professional course, but I'd like you to understand it anyway. AWS has something called Cognito, and Cognito is a service that allows mobile devices to authenticate to the AWS cloud. And realistically speaking, the way this type of authentication works, whether it be anything in the identity federations or Cognito, basically you authenticate to some external identity provider, and you're then given a temporary token, and that temporary token is used by AWS. And anytime you can use tokens or one-time passwords, you greatly enhance security because you're not dealing with passwords that if they're compromised, they can be used again to attack an organization. It's one time, so if people, or a short period of time. So if a hacker, for example, were to obtain access to the token, they can't use it for very long. A little more about authentication, and then we'll move on to the authorization components of IAM. So let's talk a little bit about the AWS Directory Service. And quite simply, this is just AWS will host Windows-based Active Directory controllers. So these controllers can be used for IAM for an organization or their VPC, or both. They're hosted in the cloud, and that's it. They're high availability Active Directory, real Windows servers, and these hosted in the cloud, and these things are used great for Windows type workloads. Now, when you're going to authenticate to the system, you realistically speaking have three ways you can do it. You can access the system with a username or password. Systems can be accessed with an access key, which contains a 20-character key ID and a 40-character secret. Or systems can be accessed via an access key plus a temporary session token. And they're really your three authentication options on the AWS cloud as it pertains to IAM. Now let's talk about authorization. And what is authorization? We covered it a little bit before, but authorization is what are you allowed to do on the systems? And authentication occurs by using the specific privileges that are associated with IAM users, groups, or roles. And you do this by writing an IAM policy. Now, IAM policies are actually written in JSON format, and this could be done via manually writing it in JSON format using the policy generator. But there's several ways that you can create IAM policies, which will ultimately be in JSON, and we'll talk about that more later. Understand the default policy is to deny access. So you're going to have to authorize users or groups or roles to be able to access anything. So let's discuss authorization policies. And really first, what we're talking about is the effect, which is basically to allow or deny, and that's it. And then we talk about a service, and that's really about what service is being accessed. And then we'll talk about resource, and that's really the resource that's being accessed, and you're going to be very specific, and you're going to use the ARN name, or the Amazon Resource Locator. And when we put in a sample IAM policy, you'll see what we mean by this. And then we're going to have an action, and that action is really referring to things of like whether you're allowed to read or write, for example. And then we'll have an optional condition, which is going to enable you to get very, very granular with your IAM policies. So really what you're looking for is who or what is going to be accessing the resources. And then you're going to assign them specific permissions so they can access what they need to, but nothing else. And you're going to specify any resource by the Amazon Resource Locator like we talked about. Now when you create these, there's two ways to create your policies. And you can create your Amazon, you can use basically an Amazon pre-managed policy, which is pre-made for you, this Amazon managed policy, or you can create a customer managed policy. And we'll describe how you can do both. So AWS managed policies are standard policies, and they're optimized for common use cases, and they can be based upon job role. For example, I told you previously that the root user can do absolutely anything, and a power user didn't have access to IAM. Well, there's another user class, which I didn't want to talk about until we got to this section, called an admin user. And an admin user has access to absolutely everything, including IAM, like the root, but it's not a root account. And then there's a power user account, which can do everything other than IAM. Of course, there's other pre-managed policies, but those two policies we'd like you to remember. The admin policy can do anything, and the power user can do everything but IAM. So how would you create a managed policy? Well, this is quite simple. You're going to sign in to the IAM console, and that's going to be https://console.aws.amazon.com/IAM. And inside of here, you're going to choose your policies, and you're going to see a lot of policies, and these policies are going to give you tremendous options for flexibility of standard use cases. So now let's discuss customer managed policies in more depth. And these are policies that are created and managed by the customer for their account. Now, these policies are not going to be visible outside the customer's organization, and they're made for a customer's specific needs. And you can attach these policies to entities inside of your account. So let's talk about making them. So if you're going to create the customer managed policy, there's realistically speaking about 3 ways that you can do it. The first way is to copy and modify an AWS managed policy. And this is a great way to do it. Take an AWS standard policy, modify it for your specific needs, and you're much less likely to make errors by doing it this way than if you try to do it from scratch. And it's going to be much simpler unless you're an expert in JSON programming. The next way you can do this is to use the policy generator, and we'll show you what that policy generator looks like. But realistically speaking, it's a web page that you go to, and on this web page it asks you a series of questions, you input your answers, and then it helps generate a policy. And of course, you could create a policy from scratch. And if you do that, that's fine, but understand you really need to know what you're doing, and you need to be pretty good at JSON programming. And if you make an error here, it could obviously affect things. So if you're great at this, great, but otherwise we strongly suggest, take an AWS managed policy and then tune it for yourself, or use the policy generator. Now here, as you can see, we have a sample policy, and we have the effect, which is to allow, and then if you'll notice, we have the resource, and we're very specific with the actual Amazon resource locator. And of course, we have the condition topic there as well, but typical sample policy that you can look at. So now that you've built your policy, you're going to have to apply your policy, and you're going to apply the policy to a user or a group, or use like a managed policy that would attach to everyone. So a user policy is for a user, specifically a user. A managed policy is something that's managed by AWS and can be applied to users or groups. And then of course there's a group policy. So here's really what a group policy is. As you can see in this diagram, we have several groups, and then we put users in each group, and then inside of that, the users inside the group actually have access to specific resources that we've defined by their user-specific policy. That's of course one of the managed policies that we made specifically for our groups of users. So the last IAM topic we want to talk about is something called multi-factor authentication. And realistically speaking, you're familiar with multi-factor authentication as you've been using it in your daily lives, whether you've called it multi-factor authentication or not. So there's a concept in security of something you have and something you know. And it provides much deeper security than just something you know, like a password. So let's talk about a debit card or an ATM card. It's something you have. So let's say you want to go to a cash machine and you put your ATM or debit card, whatever you call it, inside of the machine, and then it asks you for a PIN code. The card is something you have. That's one factor of authentication. The PIN code is something you know. That's a second form of authentication. So we're going to take that old concept and we're going to bring it into security for computing systems. We're going to set up an token generation authentication application. And what that's going to do is it's going to create a one-time password. And this password is going to change every several seconds. And because it changes every several seconds, even if a hacker got the one-time password, they could only use it for one authentication session. And they'd have to get it within several seconds before that one-time password expires. So here's how it works. You log in with your username and password to AWS. AWS will then send you a challenge asking for the one-time password, which is going to come from your authenticator app, which could be on your phone, or your hardware authenticator device. You then provide the one-time password, and if the one-time password matches what it's supposed to match, you're now allowed into the system, and therefore you will have access to resources. So multi-factor authentication is a great way to enhance security by using two forms of authentication at the same time. So let's briefly discuss multi-account strategies. We cover this in much more depth in our Certified Solution Architect Professional course, but we'd like you to still have some understanding of it. And realistically speaking, when you design an architecture, anytime you can decouple or anytime you can make things more modular, the more reliability, scalability, and security you have. So all a multi-account strategy is breaking down one giant account into multiple smaller accounts. And you're going to do this to do something called minimizing the blast radius. So what would occur, let's say you have 4 small accounts inside of your one big account. If you set up your multi-account strategy correctly and you limit what traffic can go between the components of your organization, then a problem that occurs in one of your part of your organization will be less likely to affect other parts of an organization. So that's what we mean by limiting the blast radius. And if you hear the term blast radius on an exam, you know what we mean by that. So it's great to chop your organization into multiple small parts, but the problem becomes is, doesn't AWS give you a discount for volume purchasing? And the answer is they do. So what a multi-account strategy is it enables an organization to create a big unit, and they can isolate the big organization from the little mini organizational units. And by doing that, they can create a policy that would allow filtering of traffic in between organizational units, all inside of the same master account. So you're getting the volume pricing that you would get as if you had one giant unit, but you're able to chop or modularize the components of your organization into smaller organizational units and isolate between them. And that's really what you need to know about multi-account strategies. So you always want to restrict access to your network to only allow traffic into your network that's necessary for things to work. And we talked about using network access list, and we'll talk about it more throughout the course, to keep unwanted traffic outside of your subnet. We covered that in the VPC section. And we talked about keeping security groups on your services. But what firewalls do is firewalls create a strong perimeter around the organization. And firewalls block all unwanted traffic. And some firewalls, the way they're set up, can actually be fairly intelligent, and they can actually learn and look at patterns of traffic. And when they see patterns of traffic, they can implement new access lists or new policies to basically deny something that it views as dangerous. So using firewalls to protect entry to an organization's network is a great way to filter traffic, and you're going to use firewalls, you're going to use network ACLs, and you're going to use security groups. So when it comes to security, you want to layer it. If you were dressing up for cold weather, you'd wear multiple layers. In security, layer after layer after layer. We briefly discussed firewalls, and firewalls, as we described, are devices that keep unwanted traffic out of your network. And firewalls are stateful, so basically they allow traffic to leave the network and they allow return traffic to come back automatically. But you create a policy, and it could be based upon an access list, for example, or a set of rule groups, and the firewall will keep traffic out based upon these rule groups. Now, AWS has their own implementation of a firewall called WAF, or Web Application Firewall, which we briefly described. And WAF basically looks at all the requests, and based upon the rule set, it'll either allow them or deny them. And WAF can control a CloudFront distribution, an API gateway, or a load balancer, specifically an application load balancer. And it's constantly looking at the content. And because it's constantly looking at the content, it can stop very common malicious attacks like SQL injection attacks and other things that occur. But the key thing to note is that it's very granular. You can write a policy, and these things are managing traffic. So here's how that works. You're going to enable WAF on your application or device. And then you're going to create a policy that filters all unwanted traffic. And as traffic is coming in, WAF is going to, or out and return traffic coming in, WAF is going to really look at the traffic and is going to say, does it comply with policies? Is there something wrong? And if the traffic complies and it looks like good traffic, it's going to allow it to come back. So really what WAF is just another layer of protection that you can provide some firewall protection prior to your network ACLs and then prior to your security groups to enhance your security posture. And if you're going to use a web application firewall, you still are going to need some kind of DDoS protection. So the next thing we're going to talk about is DDoS protection on the AWS cloud. Let's discuss prevention of DDoS attacks, distributed denial of service attacks, but I'd like to describe what they are. So a distributed denial of service attack is when a hacker uses multiple systems on the internet to then attack your system. And the way this really works is, let's look at a web server, for example. And let's say when you do an HTTP request, you're going to open the session with something called a TCP SYN. This happens in every normal request. Now, a web server can handle a certain number of web sessions at one time, or a certain number of SYNs that would then be acknowledged by normal traffic. And under normal circumstances, the web server is not going to be overloaded, assuming the web server has been sized to handle all the requests of your organization. But what if a hacker attacked 1,000 servers on the internet, and those 1,000 servers constantly tried to start new sessions with your web server by sending SYN messages, SYN messages, SYN messages, and all these servers are doing it all at the same time? Now that can easily overwhelm your web server and take your web server down, and that's called a distributed denial of service attack. So how do we prevent distributed denial of service attacks? Well, for one thing, multiple layers. So we block unwanted traffic. We block it by the perimeter with a firewall. We block it at the subnet with a network ACL, and we block it at the server or service level with a security group. We shut down unnecessary services because they could be used against us, and we use DDoS protection. And in this case, AWS has a form of DDoS protection called AWS Shield. Now, AWS Shield will automatically block the majority of DDoS attacks that are out there. In fact, Amazon says that the basic version or Shield standard will actually block 96% of common DDoS attacks. So let's talk briefly about the two types of AWS Shield. So there's Shield Standard, and Shield Standard is free for anybody that's using AWS WAF. And it protects against the majority of DDoS attacks, and it's based upon a policy. And it gives you some pretty good basic DDoS protection. Now, there's another version called AWS Shield Advanced, and this is additional protection, but you have to pay for it. But with that additional protection, you can apply it to elastic load balancers, EC2 instances, CloudFront, Route 53, so you can apply it to many more things. And this is going to look at layer 3, layer 4, and layer 7. So layer 3 is the network layer where the IP addresses would be. Layer 4 is the transport layer, which is where you're going to have your TCP or UDP, and it's going to also look at the application layer. So this is much more substantial protection. And because you can apply it to more things and you have better policy access, you're going to have much better DDoS protection. Now, one of the things is that Shield Advanced comes with, which is fantastic, is it has a 24/7 number that you can call for DDoS response. It may not be a number, it may be a website, but whatever the point is, you've got access to specific experts that can actually help you, that you can reach out to when you need it. But in order to be able to use that, you're going to have some kind of enterprise support or business level support with AWS. But the point being is AWS Shield is another means that you can layer on to your security architecture. Because with security, it's layer upon layer upon layer upon layer in order to improve the security, which will ultimately improve the availability of your organization's systems. The last two things I want to discuss, or at least touch on briefly, are the service catalog and the systems manager parameter store. Now, we cover these in substantially more depth in the professional version of this program, and it's really mostly tested in the professional exam. Having said that, we occasionally see questions pop up on this. We want to cover it just briefly. So we'll begin with the service catalog, and the service catalog is a great way to enhance your security. So one of the best ways to control security is to control what you place on your network. Only put things that are necessary for your business on your network and make sure they are hardened, patched, locked down, and you want to make sure that what you put in your network is secure. So the service catalog enables you to do that. It enables you to create a list of approved services, AMIs, servers, softwares, databases, applications, and servers. And you allow your systems administrators to choose only from the service catalog. And that way you can control what's placed on your network. Last thing we'll touch on is the systems manager parameter store. And when you run an organization, you're going to have a tremendous number of passwords, you're going to have license keys, you're going to have critical information that you don't want in the wrong hands. So the Systems Manager Parameter Store is a secure, encrypted environment for you to secure passwords and other licenses and other relevant important things.
In this lab, what we're going to do is we're going to create a new IAM user, and we're going to assign them administrator positions, and we're going to show you how to do it. So the first thing we do from the AWS Management console is we're going to go to the IAM section. So now that we're in the IAM section, we want to create a user. So from here, what we're going to do is we're going to choose users, and then we're going to add a user. Now in this particular situation, you're going to pick a very strong username and a very strong password, because whoever has access to this can, specifically administrator access, can do anything on the account. They could do things in your own name. They could be highly expensive and set up anything, or they could delete instances that you have. So you really want to lock down your users. So in our particular case, we're going to create a simple username because we want to be able to remove them as soon as we're done this lab. So we're going to pick the username. We're going to type Cindy, which happens to be my cat's name, and then we're going to call it the cat. Pick something that makes sense. And here you have the opportunity to choose whether they can use the CLI, the API, the software development kit, or whether they can access the management console. So because this is going to be an administrator password, we're going to come up with an administrator. We're going to come up with something solid. Now we're going to take the auto-generated password, but you could create your own custom password. Make sure you choose a secure password. So the next thing we're going to do is go to permissions. And under permissions, we're going to add the user to a group. So let's see what kind of a group we actually have. So we have a power user group access. So let's create a group. And we're going to call these group names admins. And we're going to make sure that we select administrator access from the pre-managed policy. You could create your own policy, but these are pre-made policies and they typically work great for most situations. So now we have an admin group with administrator access, and we have the power user. So now I'm going to add the user, the one that we just created, to the group. We're going to click Add Users to Group. We're going to click Next. We're going to come up with a name, and we're going to call it Admin Group. So now we have a username that has programmatic access and console access. We've auto-generated their password, and we haven't set their permissions boundary yet. So we're going to create the user. And now that we've created the user, you definitely need to make sure you write down your secret access key as well as your password. So I'm going to do that real quick. In a normal environment, this would be completely secured, but we're going to need this information to log into things. So the first thing that I'm going to do is I am going to go to an application where I store things, and I'm going to store the username and the password, or at least the secret access key and the password. And obviously you don't ever want to do this sharing a screen, but we're doing this in a lab context, and I have to show everyone how to do these things. And then we're going to close this. Now we're going to take our IAM user and let's verify the group that they're in. They're in power user access, but I want them to be in something more. So let's put them in the admin group that we created, which basically has full access. So now we can see that our user is a member of the admin group. And in this particular case, since admin can do everything and power users can do everything except for IAM, but admin can, I'm just going to remove that user from that group. And there you have it. Now we have our user, and our user is actually part of the administrator group. And that's how you create a user, and that's how you place them part of a group. what we're going to be doing is we're going to be creating a user access key. And we're going to disable the current access key and create a new user access key. So what we're going to do is we're going to sign into the management console, and then we're going to go to the IAM section. So from the IAM section, we're going to choose users. And we can pick any user, but we just created Cindy the cat. So let's go to Cindy the cat as a user. And let's just, because we created this before, let's remember that it's following, they can change their password. They're a member of the administrator group, so they have access to everything. We created a basic tag just to know what it is. We can look at their security credentials. And from here, what we can actually do is we can create new credentials. So we currently have an access key, which I'm going to make inactive. Now we're going to create a new access key, which is really not that complicated. We're going to go to create access key, and that's pretty much it. We've created a new access key. You're going to want to download this file because that file contains all the information you need. You can see your access key as well as your secret. And we're going to close that. Now we have created a new access key for your IAM user.
So in this section, we're going to be covering AWS applications and services, for which there are many. We'll cover SQS, SNS, SWF, Elastic MapReduce, Kinesis, ECS, EKS, Elastic Beanstalk, CloudWatch, CloudTrail, AWS Config, CloudFront, Lambda, Step Functions, CloudFormation, and Certificate Manager. And we're going to begin this with AWS SQS. And high availability, high scalability applications do best when you make them modular. And if you segment your applications, just like we talked about segmenting our organizations into manageable pieces, if we segment and decouple application architectures, we can dramatically improve scalability by removing system bottlenecks. So AWS has a solution for that, and it's called the Simple Queuing Service, or SQS, and it can help decouple your application architectures. So what is SQS? SQS is a message queuing service that provides temporary storage of messages. And it's going to enhance application availability by basically giving messages a place to be stored. So for example, you could have a web server that's going to an application server that's going to a database. And the database may be constrained. So we may want to put SQS between the application servers and the database, for example. And that way messages from the application servers can be stored on the SQS service prior to being delivered to the database, should their database be busy. So it's really a transient place to store your data. And the data can be stored for quite a long time. In fact, the default retention period is 4 days, but you can configure this all the way to 14 days. So if you've got some busy systems, the SQS system can really help. SQS enables you to right-size your applications, because without SQS, you would have to scale larger, because you're going to have to make sure that you can handle all the messages as they would occur. But with SQS, you could right-size your application, so you could use a smaller computing instance, because the messages might be chaotic for a period of time and then slow all day. So if you're using the queuing service, you could take the messages, stick them in a queue, and when the database or whatever, the other server is not busy, you could drain the queue. So SQS really facilitates a lot more scalability. SQS can also facilitate auto-scaling. For example, you could have something monitor the depth of messages in the SQS queue, and if it reaches a certain length, then auto-scale the environment. So SQS is a great way to actually add some modularity and scalability into your application architectures. So it's a queuing service. So there's, realistically speaking, 2 ways that you can queue your messages. Actually 3, but primarily 2, and we'll talk about all 3. The first and primary method is the standard queue, and that basically says messages come in and messages come out. Now this is super fast, but there's no guarantee of the order. For example, the first message might be a large one, the second 3 might be small, and the next 3 messages might be delivered before the first one. And in most cases, that's fine. But if it's not fine for your applications, if your applications need to have messages delivered in the order they were received, then you're going to need to do something called a FIFO queue, which is first in and first out. And this is a high throughput environment, but it's still slower than a standard queue. But it does guarantee messages are processed in the order they're received. Now, the last type of a queue you can set up is something called a dead letter queue. And what a dead letter queue does is if a message never reaches its ultimate destination, it can be stored in the dead letter queue, so it's actually not lost. But the primary queues that you're going to be using are going to be your standard queues, which is basically messages come in and messages come out. It's super fast, but there's no guarantee of the order. Or you're going to use the FIFO option, which is first in and first out. So now that you know about SQS, at least from an architectural perspective, let's talk about how it works. So a message is going to be sent from the computing platform to the queue. And as soon as the message is in the queue, it can be scheduled for delivery. Now, if the ultimate destination where the messages will be delivered is busy, the messages can stay in the queue until they time out. Now, I had mentioned the default time is 4 days, but it can be configured for up to 14 days. So you can store your messages for a relatively long time. Now, when the message is deliverable, meaning the recipient is ready for it, the message is pulled from the queue. And then after the message is pulled from the queue, it's deleted from the queue. And that way you can pretty much guarantee that you have a place for the messages to be stored until they're delivered to their ultimate destination. Now we're going to discuss the Amazon Simple Notification Service, or SNS. And SNS is a messaging service that's used to deliver messages between systems. And it's also a great way to decouple messages between microservice-based applications. And you're going to use this to send an SMS, an email, or push messages to mobile devices. So the way this works is there's publishers and subscribers. Publishers communicate by sending messages to a topic, and the subscriber subscribes to the topic and then receives the messages. Kind of like a mailing list. You enter your information to the mailing list, and every time they send, you receive it. So we'll talk a little bit about the SNS platform functionality. It's a high availability platform that by default is actually run across multiple availability zones. And because it's in multiple availability zones, it's going to be secure and reliable in case the data center were to go out. And SNS is often used to fan out messages. So if you've got a large number of subscriber systems or computer endpoints. So SNS will enable you to create like a filter policy so that only people that need or systems that need to receive a notification will. And SNS will encrypt your messages immediately to protect from unauthorized access. So where are you going to use SNS? You're going to use it for application and systems alerts. So an SNS can send you a notification when a predefined event occurs. Say your CPU utilization hits 80%. It'll notify systems admins. It'll send email and text messages. So these messages can be sent to you. For example, if a company's CEO is going to be on TV, it could even send a message to everybody in the organization, watch this. And the concept of push messages. So SNS can send a push message or a notification directly to mobile applications. And you've seen this with applications. You've got an application and all of a sudden it sends you an alert. And what happens is the alert is a push message that basically tells you what you need to access. So SNS is the Amazon Simple Notification Service that uses a messaging service. Now we're going to discuss SWS. And SWS is a workflow management solution. And it really enables the coordination of different tasks across distributed applications. So, for example, if you've got a multi-step workflow, SWF is a solution to help you do that. Because what it does is it coordinates the execution of tasks across an application. So by using SWF, it kind of mitigates the need to code and coordinate these tasks on your own. Because it's a pre-built workflow management solution. So all that's really necessary is to tell SWF the steps and it'll manage the workflow. So let's take a sample workflow. It's pretty common that organizations have video and they do some transcription and other processing to the video prior to actually utilizing it. So let's say we were to make a simple SWF workflow for a common video solution. Let's say I want to upload a video, but I want the video to be processed. So let's say I upload raw video. And I want that to be converted into a format that's efficient for web distribution. So I can first upload the video. I can create a second step to have the video processed and converted into like an MP4 file with an H.264 or 5 codec to make it a much smaller file. And then after the video is formatted, I might want it transcribed. But I might want those transcriptions to be placed as burned-in captions to the video. And then after that, after all the work's been done to this video, I want it to be stored somewhere. And then I want to actually be notified, hey, by the way, Mr. Customer, video is ready for download. And this is the kind of application that you can do with SWF. And therefore, we tend to love it. Now, a little bit about Elastic MapReduce. It's much more of a topic in the professional exam, but we just want to touch it just so you know what it is. And it's an application for processing large amounts of data. So the Elastic MapReduce, or EMR, is just an application for processing tremendous amounts of data. And it's really a managed cluster, and it's really for big data frameworks. And it's been built on open source tools such as Apache Spark, Apache Hive, Apache HBase, Apache Fink, and a few others. And it offers some fairly high performance compared to some other solutions. And it's a great way to actually deal with large amounts of data, and you don't have to code it. And because it's basically pre-made, there's not the expenses that are required with heavy management or heavy coding. Now we're going to discuss Amazon Kinesis. And Kinesis is a big topic, and it's heavily covered in AWS exams. So we're going to spend some time here. And Kinesis is an AWS service for collecting, processing, and streaming real-time data. And Kinesis can collect this data from a lot of sources such as video, audio, application logs, website clickstreams, Internet of Things, and many other devices. And unlike a traditional environment where you're going to take all this data, you're going to store it, and at some point analyze it, with Kinesis you've got some type of real-time analysis that you can perform to make better business decisions in real time. So there's 4 versions of Kinesis, and one is video streams, another is data streams, then we have data firehose, and we're going to have data analytics. And we're going to start with video streams. Video streams is basically just a service to collect and aggregate data from multiple places. And it can be then ingested, sent into storage, and then indexed. So really, Kinesis Video Streams is about capturing video. Now, Kinesis Data Streams is pretty important, and it's a highly scalable platform to collect real-time data. And this can capture gigabytes a second of data, and it can capture it from hundreds and thousands of sources. So it's a great way to collect data. So think of a financial transaction application for a trading organization, how they have millions and millions of trades being placed at any one time. This is a great way to capture this type of data. So what happens is the streaming data is captured by Kinesis, and then it's sent for processing. And after the data is processed, it can quickly be input into business intelligence tools. But you can also, in some way, shape, or form, use these Kinesis streams to do some more analysis, and we'll talk about that later. But understand for right now, we're talking about collecting data from a lot of sources and then being able to ingest it and process it in real time. So some use cases would be you've got a large event that you're trying to collect data, more real-time analytics, capturing gaming data from multiple game players, mobile data coming from all different sources, but it's really about capturing, streaming live data. Now we mentioned Kinesis Data Streams is for collecting streaming data. Now Kinesis Data Firehose is really taking streaming data and loading it somewhere. So Kinesis Data Firehose is a managed service to load streaming data into like a data store, a data lake, or an analytics service. Often people will use Kinesis to capture the streaming data and put it into S3, and often they'll put it into Redshift as well. So they've got that concept of big data applications they can use it for. And it's a fully managed service, and it scales to match the needs of your data through auto scaling and monitoring. Now, throughput is actually based on something called a shard. And a shard is actually 1 megabit per second. And when you use this service, you pay for it based upon the number of shards that you need. Now, obviously prior to use, the organization is going to try and guess the number of shards they need, because if you're going to provision your capacity and you're going to pay for your capacity, you would like to know ahead of time what you're going to use. Now, generally speaking, you can create up to 10 different shards, and you can go beyond that, but you're going to have to call AWS first, their service, and they're going to have to authorize you, because you only get 10 standard shards, which is still 10 megabit a second of streaming data, which is really quite a lot. And you can set up a policy to auto scale up the throughput. in terms of the number of shards. And you set Kinesis data firehose up through the console. It's essentially just setting up the sources and destinations of the data. Now we'll discuss Kinesis Data Analytics. And Kinesis Data Analytics is a managed service to transform and analyze real-time streaming data. So Kinesis Data Analytics uses the built-in Apache Fink application in order to process the data. So Kinesis Streams is auto-scaling and will definitely meet the needs of an organization if it scales up. And data on Kinesis Streams can be queried with standard SQL queries. So this is really a way to take your real-time data and analyze it in real time. So people often use this. They'll basically take their streams, they'll do a quick analysis, and then they'll pump it into business intelligence tools to make long-term better business decisions. Now we're going to be discussing the Amazon Elastic Container Service, and I'd like to begin this discussion with what is a container. So a container is a modern version of a virtual machine, and it's very lightweight, because what happens with a virtual machine, each virtual machine needs an entire operating system, then it's going to need the application dependencies, and then it's going to need the application. And a container is a much lighter version. Basically what it is, each container is going to have like a little mini version of the operating system, and that's really going to be system libraries and dependencies of the such. And then you put the application. But they're still logically separated from the other applications. So now you can have one system, and the system can hold multiple containers, and each container is almost as if it's like a virtual machine for just the application. So they're higher performance, they're much lower system resources. Because look at it from an architectural perspective. With a virtual machine, you have your bare metal hardware, then you have your hypervisor, and after that, you're going to have a virtual machine, which is basically going to have an operating system, the libraries and dependencies you need, and then your application. Whereas the container, it's going to be a server, the operating system, and a little container, which is just those things that are necessary to make the application work. Understand when you're dealing with containers, if you're going to use a Windows system, Windows containers can do Windows applications. And if you're going to use a Linux system, the containers can do Linux applications. Now, so let's talk a little bit more about the container service. So it is a very high availability service to manage containers wherever they would be on your VPC. And we'll talk about the locations. But it's a 4 nines available container service. And it's deployed in a VPC, which gives you the ability to use NACLs and security groups. You've got some good security you can use with it. Now, it's a management service for your containers, and you can host your containers on one of two locations. You can host it on an EC2 instance, and the containers themselves will be managed by the container service, or you can host it on something called AWS Fargate. And Fargate is a serverless platform. And one of the things that's really great about using a service like Fargate is if you put your container on a Fargate location and you need more power, it'll just scale up in an unlimited manner because it's serverless, so whatever resources it needs. And because it's Fargate, it's going to be much easier to manage because you don't have to manage the server, then you don't have to manage patching the operating system, then you don't have to manage patching all the applications. All you're going to have to do is worry about your application. You may have to patch your own application, but you're not going to be dealing with the operating system, and you're not going to be dealing with anything else. It's going to all be managed, and all you need to do is just update your container. So it's going to be much simpler to manage. And that scalability component is great. So because you can run your containers either on an EC2 instance or the serverless environment, when would you choose one? Each other. Generally speaking, most people are probably going to do better with Fargate because of its scalability and its simplicity. Having said that, if you need complete, total autonomy over the systems that house your containers, choose EC2 because it's your own systems and therefore you can manage it. But they're the two options to use the Elastic Container Service. Since we're discussing containers, we'll also discuss the Elastic Kubernetes Service, EKS. And realistically speaking, EKS is a fully managed Kubernetes container service. And Kubernetes is just an open source container management platform. And for the most part, you could almost call it the industry standard because most of the containers are actually using this service. It's very popular. But realistically speaking, it's just an open source version of it as opposed to EC2. And ECS. And like ECS, the EKS service can manage containers on EC2 instances or Fargate, whichever you choose. Let's briefly discuss Elastic Beanstalk. An Elastic Beanstalk is a service to provision and deploy scalable web applications and services. And it's quite easy to use. Realistically speaking, all you do is you upload your code, and then the Elastic Beanstalk will automatically deploy your infrastructure, whether it be EC2, containers, load balances. And the infrastructure that's deployed is actually auto-scaling by default, and it's also load balanced by default. So it pretty much sets you up for a great infrastructure by just putting your code in. And it supports, multiple programming languages. It works with Go, Java, .NET, Node.js, PHP, Python, and Ruby. So it's pretty flexible with regards to the code that you're actually uploading. And the good part of it is that it actually provisions, but it also manages the environment, and it's watching to see what's going on with the health of your applications. And you can get your logs with this because it integrates to CloudWatch logs for performance monitoring. Let's discuss CloudWatch. CloudWatch is a monitoring service to monitor what's going on in your VPC, and it can monitor applications that you deploy as well as other AWS resources. And what happens is it will provide metrics, and these metrics can not only help you monitor performance, but it will also help you troubleshoot issues when they occur. And CloudWatch has two kinds of metrics: built-in metrics and custom metrics. Now, built-in metrics, or the default metrics, give you things like CPU utilization, disk read and write, and network utilization. Now, you can set up a custom CloudWatch metric if you need to know something more. For example, you might want to monitor memory utilization or API performance. And when you set up a CloudWatch custom metric, it can be very useful to understanding what's going on in your systems and making changes to make them run even better. CloudWatch has an event type of a notification as well that can be set up with thresholds. And when something happens past a threshold, you could get a notification, for example, or you could set off a Lambda function to change something. So CloudWatch events really gives you a really good idea of what's going on, but at the same time, it helps you mitigate things, whether it's a Lambda function, an SNS notification, triggering auto-scaling. So CloudWatch is really an integral part of your service when you're using the AWS cloud. Now, there's two versions of CloudWatch. There's basic monitoring, which gives you data automatically every 5 minutes, and it's included at no charge. Now, if you need more monitoring than that, there's an option for detailed monitoring, and this provides data every minute, but you pay additionally for this. And you also have to enable detailed monitoring on the EC2 instance level. Now we're going to discuss CloudTrail, which is an auditing service. Again, I'm going to mention it again, CloudTrail is an auditing service. So what CloudTrail does is it provides an audit log of the things that actually occurred. And it will tell you what changes were made by what user account or what role or what service. So it gives you good information what goes on. And CloudTrail is enabled when the account is created, but to start using CloudTrail, what you're going to do is you're going to create a trail on the console, the CLI, or through the API. Now you're going to get an event history that lets you see events that have occurred over the last 90 days. And you can configure CloudTrail to store logs in S3 should you need to keep it longer than that. So when you make a CloudTrail, you basically have two trails. So you have a CloudTrail that's local to one region, and you can make one that applies to all region. So when you need a simple trail with less features and functions, realistically speaking, you're going to use the local CloudTrail local. But if you need much more sophisticated options, you're going to use a CloudTrail that applies to all regions. Now we're going to be discussing AWS Config. And AWS Config is a service that enables assessment, auditing, and evaluation of configurations you have in AWS. So it really gives you a good idea to see what's actually going on. And I say this because you may think you know about everything that occurs inside of a network, but every once in a while things pop up, configurations pop up, devices pop up that you just don't know about it until you look. So this will help you see a change inside of your VPC, because what can happen is an SNS alert can be sent to all the system's admins as soon as something occurs. So this is going to provide constant monitoring of your infrastructure. And what's going to happen is, as a new device comes online, it's going to say, does this meet the organizational standards? Does this meet best practices? And if the answer is no, it can give you the opportunity to do something about it. So it's really a great way to find out what's going on and then determine what you actually need to do about it. So think of it this way. It begins in the following structure. A configuration change is made. AWS config notes it and says, okay, I see it, and then it records it. And then it's going to check what's there and see, does it conform to organizational policies? And if it does, that's fantastic. And if it does not, it's going to notify a systems administrator. So this is a great way to know what's going on. This next section is on CloudFront. And CloudFront is the Amazon branded content delivery network. And what content delivery networks do is they bring content closer to the users. And if the content is closer to the users and it rides over a higher speed network, which they typically do in content delivery networks, the user experience is improved. So what happens is CloudFront has a network of caching servers that are also at edge locations throughout the entire world. And when a request is made for a web page, the request's location is determined and they get sent to the closest CloudFront server. And these servers are spread throughout the world. Additionally, the CloudFront servers actually cache the content. So here's what typically happens. A user makes a web request, which gets sent to CloudFront. If it's a new web request and no one in that region had ever requested the information before, what'll happen is the web request will go to the web server. Now the web server will then send that data back to the CloudFront location, and the CloudFront location will deliver it back to the user. Now the next user that's in that area that's going to use the same CloudFront location will have that frequently accessed information from me available to them. So their web request will go from them to CloudFront, and if it's the same thing I requested, it'll get sent right back to them. So that can make performance much faster because you're bringing it closer and because you don't have the latency of the distance of the packets that need to travel across the network. But caching web servers can make them much more scalable. And the reason they can make them more scalable is a lot of the content that people request from web servers is typically the same content. And if it's cached, the content will be coming from the cache servers as opposed to the organization's web server. So that will enable many less web requests to go to the web server, which will be very helpful in terms of server performance. Now, CloudFront integrates with a lot of AWS services, specifically S3, EC2, Elastic Load Balancers, and Route 53. And CloudFront is very frequently used as a front for a static website that's stored on S3. But you can still use CloudFront in front of an EC2-based website, provided an Elastic Load Balancer is part of the architecture. So let's just summarize. CloudFront can really help with performance because it helps with caching. There's 217 points of presence at the time we made this course, spread throughout the world, so this can really get content much closer to the user. It improves routing efficiency because instead of data being sent over the internet, it can be sent over the AWS high-speed backbone, which is typically faster. CloudFront can also substantially help protect an organization from a DDoS attack, especially when Web Application Firewall and AWS Shield are enabled. But the reason CloudFront can help so much with the DDoS attack is first, it'll distribute content throughout the 217 points of presence throughout the world, at least at the time of this filming. And CloudFront is only going to forward legitimate traffic to the actual web server. So typically you would see in a DDoS attack illegitimate traffic that's sent to the web server and it's flooded. But now you're dividing it among 217 points of presence, and only the legitimate requests will be sent to the server. So this can really enhance the availability of a web application because it can prevent against DDoS, but also improve the performance through caching. CloudFront can also provide some encryption in transit for data. It can work with and enforce the SSL TLS-based protocols, and it integrates nicely with the certificate manager for certificates. Now you can tune CloudFront, for example, because it is a caching system, if you change your data quite frequently, you might want the cache to time out sooner so that you don't have stale data. And you can set the minimum, the maximum, the default TTL, or time to live, which is the expiration time of data in the cache. And you can clear the cache if necessary from the CLI. For example, if you'd have stale data in the cache and you need to clear it, it can definitely be cleared through the CLI. And we have a command that you can see we'll post in the video that will show you how to do that. Now we'll discuss Amazon Lambda. And Lambda is a way that you automate simple functions across an organization's infrastructure. And Lambda is a serverless computing service, and it works by simply you write your code, you update your code for the Lambda function, and that's it, it just runs. And Lambda enables you to write your code in C#, Go, Java, Node.js, and Python, so most of your scripting type languages. One thing to know is that Lambda is stateless. So you set up a Lambda function. Once the Lambda function is finished, it's done. If you want something else to occur, you're going to have to set up a second Lambda function. And Lambda can be used when you want to automate things, processing data across multiple systems, remediation of security events, patching of operating systems. So it's a good way to do some automation. And let's walk you through an example of how this can work. Let's say you upload a new file into an S3 bucket. And in this case, it's going to be a video file that needs processing. We can set up a Lambda function so that when S3 detects the new video file, send it somewhere else, or do something else with it, or activate another system. So that's typically the way you would use a Lambda function. Now there's a way you can bring Lambda functions closer to the user, and that's called Lambda at Edge. What Lambda at Edge does, it works with the CloudFront Content Delivery Network, and this enables small Lambda functions to be run very close to the customer. So we've already discussed Lambda, so now we're going to discuss step functions. And what step functions are is they're really a means to just sequence multiple Lambda functions together. And like Lambda, it's completely serverless, but it's really about just scheduling multiple Lambda functions. So here's how it's going to work. You're going to design the steps of the application. You'll then create your individual Lambda functions, and you'll configure the workflow with step functions. And you'll connect the workflow components to the individual tasks, and then just execute the step functions. So basically what will happen is step 1 will occur, then a Lambda function will occur. When Lambda function 1 is completed, step 2 will invoke another Lambda function. And then when that function is completed, step 3 will invoke another Lambda function, and so on and so forth until all the necessary steps of the workflow have been completed. Now we'll briefly discuss CloudFormation. And CloudFormation is really a means to template known good configurations so you can repeat using them. And let's say, for example, you have an application, and it's a common application in your organization that requires the configuration of several servers, specific patches, specific dependencies in order to work. And if you miss any of those steps, or you do any of those steps incorrectly, the performance might not be the same as you need it to be, or the security might not be good. Well, with CloudFormation, basically you're going to create a template, and the administrators can then invoke that CloudFormation template, and they're going to get the same results every time. So it's always good to template your configurations, whether they be in a format that's even a text file, but at least a means to get to the same place, and CloudFormation is a great way to do it. So you're going to write a CloudFormation template in either JSON or a YAML file, and you store the content on S3. And basically what happens when you want to actually build something, you're going to pull that template from S3, and CloudFormation is then going to provision your services for you exactly the way you want it to be based upon the template. The AWS Certificate Manager is a service to essentially manage your SSL or TLS certificates in the cloud. And it's going to add protection to a website by using a certificate to establish safe and secure connections. And really, this is just a service to simplify provisioning, management, and deployment of your certificates, whether they be public or private. So the Certificate Manager provides free and private certificates to AWS services like a load balancer or an API gateway. There are, realistically speaking, two options when deploying your certificates. There's the standard AWS Certificate Manager, and this is for customers who want encryption and security using TLS. There's also a version called Private Certificate Authority, or Private CA. And this is really for making private certificates to really secure an organization's internal communications. But these are private certificates, not for a public website, and these private certificates are available at an additional cost.
What we'll be doing is we're going to be setting up CloudWatch. Now we're going to specifically set up a dashboard. Remember from the lectures, and this is very important going into the exam, that you remember CloudWatch is used for logging and CloudTrail is used for auditing. So in this case, we're going to be setting up some widgets so we can look at certain things related to the logging functionality. So we're going to go from the Management Console to CloudWatch under Management and Governance. We're going to click this section under CloudWatch, And then we're going to create ourselves our own custom dashboard. So we're going to go to the dashboard section and we're going to create one. And we're going to call it whatever we want to, but I'm going to call it GCA dashboard. And from here, we're going to figure out what we want to monitor. So we're going to monitor some metrics. And to be fair, we're not going to see many metrics on my CloudWatch logs because I keep a lab environment. I spin up instances as I need them. I shut them down when they're not needed, at least for our lab environment. And because of that, we're not going to have a lot of data, but we're going to set it up anyway so you know how to set up a widget and add it to the dashboard. So here you have the option to pick which metrics you're interested in. You could look at logs or metrics. So we're going to pick metrics. And when we get here, we can find the kind of metrics that we're interested in. For example, we can go to EC2 and we could look at per instance metrics. And we can pick out what we're really interested in looking at. So we could look at, say, CPU utilization, because we care about that. We can look at disk input and output and see what's going on with our disks. We can see what's going on with our network. We can pretty much pick any of the things that we need, and we can look for some serious problems, such as system failures. And we can create our widget. And that's pretty much all there is. We've created a dashboard, and now you can look and see, and when we have more information coming in, you'll be able to see exactly what's going on with disk reads, disk writes every 5 minutes. That's pretty much all you have to do to set up a dashboard under CloudWatch and set up a widget to give yourself easy access to the information you want to monitor. Setting up CloudTrail. As you recall from the lecture, CloudWatch is used for logging and CloudTrail is used for auditing. So we're going to begin by setting up our CloudTrail by going to the Management Console. In the Management Console, we're going to go to the section where it says Management and Governance, and we're going to click CloudTrail. So when we get to this page, we're going to create a trail. And we're going to click Create a Trail. Now we can come up with a name. I had cut and pasted in the management events right before this to make sure we had a name that would be simple to use. And we're going to create this trail. So what you can see here now is we have a trail called Management Events. And we're going to be collecting the information, and so the trail has been created. Now let's see where the trail is being stored. Because typically we want to store something in a bucket of some kind. Now in this particular case we could have created our bucket, but we can use the bucket that was explicitly made for us. So we'll click on the bucket, and there's no objects in the CloudTrail because we haven't done anything yet. But that's really it. That's about how you set up a CloudTrail, and you'll go back to your CloudTrail to be able to see what's actually going on with regards to who did what on your systems. We had set up some CloudTrail, and I had mentioned that some of the logs were not available at the time because we hadn't done anything yet, but now there should be. So in this lab, what we're going to be doing is we're going to be taking CloudTrail and actually integrating it into CloudWatch logs. So the first thing we're going to do is we're going to go check on our trail, and we're going to do that by going to the Management and Governance area of the Management Console and clicking on CloudTrail. From here, what you'll be able to see is in the previous lab we had set this up, but now there's things you can see. I've deleted some things, I've placed some bucket policies. You can see everything that's going on. But let's go back to our CloudTrail dashboard. We can look at what's going on here, and let's actually go to our specific trail. Go back to the dashboard. We'll click on the name of the trail management events. So here what you can see is generally what's going on. It tells us where our CloudTrail location is. It can tell you when the last log file was delivered. I chose not to use encryption because I wanted to make this as simple as possible. But now we're going to set up CloudWatch logs. So we're going to click Enabled, and now we're in a position to generate CloudWatch logs. Now, we're going to create either a new log group or an existing log group, come up with some names, letters, numbers, something that's quite easy. And we're going to have to create an IAM role. Remember, IAM users are for users to access a system, but IAM roles are for systems to access a system. So what we're going to do is we're going to create a name of a role. And you can pick something that is going to make sense to you. I am going to pick Cloud Trail underscore GCA for Go Cloud Architects underscore Mike. I just want something that's going to be easy for me to remember. Now you can look at more under the policy document, and that will show you what's actually going on from the IAM roles, that it's allowing access into CloudWatch from CloudTrail. We're going to save the changes. And with some of these actions, it takes a few seconds or so. But at this point, as soon as this is finished, we should have completely integrated our CloudTrail into CloudWatch logs. So we'll give it a few more seconds, and now we can verify things. So we're going to go back to the Management Console. And under the Management Console, now let's go to CloudWatch. Now while we're in CloudWatch, we're going to be able to see certain things that are going on. We're going to have some dashboards. We're going to have log groups. And you can see this is the group we just created. And in here, we'll be able to look at the log stream. And you can see what the recent events were. So that's it. That's exactly how you would take a CloudTrail and integrate it into CloudWatch logs. We're going to be setting up a CloudFront distribution. If you recall, CloudFront is the AWS Content Delivery Network. And what the Content Delivery Network does is it brings content much closer to your customers, and it brings the content closer to your customers through the AWS network backbone, which in many cases is going to be faster than the internet, because AWS can create some service level guarantees on their network, but it's impossible on the internet to create any kind of service level guarantees. I mean, you can guarantee your connection to the internet, but once your data gets on the internet, it's going to be routed through so many organizations and internet service providers, it's impossible to actually guarantee any level of performance. So it'll bring your content closer to the customers, but not only would it bring your content closer to your customers, it's going to cache your data. So it's going to store frequently accessed data closer to the customer, which is going to mean less content needs to actually traverse the network backbone, which is going to reduce your data transfer costs, and at the same time, it's going to improve the performance for your customers. So you can set up CloudFront to work in front of an elastic load balancer with EC2 web servers, or you can use it in front of an S3 enabled bucket. And so let's say we created a website, which we already have on S3, and we've showed you how to do that in the previous lab. So now what we're going to do is we're going to create a CloudFront distribution to our S3 bucket. Now we're going to click CloudFront, and we're going to create a distribution. And this is going to be pretty easy. So for the origin domain, and we're going to set this up straight out of the S3 buckets. If you had set up a fairly complicated S3 Route 53 routing policy, you could with custom domains. But we're going to do, just because this is a lab, the basic infrastructure to set up a CloudFront distribution for your S3 bucket. So for the origin domain name, you're going to pick your bucket, and it's going to give you the origin ID. It's going to give you connection attempts. It's going to tell you the cache behavior. Do you want it to cache? What do you want it to cache? And under price class, you can have you can choose different options, whether you want it to cache in all edge locations or just certain environments. You can set up AWS WAF ACLs directly on the CloudFront distribution, which is fantastic because you'll be able to block bad content at the location of CloudFront prior to it even getting on your network. So your web servers will never have to see, or in this case, your S3 bucket and your WAN will never have to see the bad traffic that would be associated with this. And if you had set it up with a load balancer and an EC2 enabled website, those servers would never actually see the bad traffic. So it's going to be blocked directly with CloudFront, which is going to substantially enhance your distributed denial of service protection, as well as improve your performance. And then we're going to just create our distribution. And that's pretty much it in order to set this up. We've already set up a CloudFront distribution, and it's going to point to the S3 bucket. And you can see that it's up and it's running, and you can see the origins of where they're there. Now, realistically speaking, that's all we're going to do in this lab. Now, if you were to set this up for a production web environment, you're going to go to Route 53, and you're going to create a record that's actually going to point to the CloudFront distribution instead of where your website would actually be, which is the S3 bucket, or your EC2 instances behind an elastic load balancer. So that's it. That's how you're going to set up CloudFront to work with an S3 enabled website.
This next section is about cost management. When an organization chooses to move their data center to a cloud computing environment, it can have a profound effect on the cost of running an organization's technology. Now, in most situations, the total cost of ownership will be less in a cloud computing environment than a traditional data center, but not always. But one thing is for sure, when you migrate to the cloud, the cost structure changes and it changes dramatically. So cloud migrations will shift expenses from predominantly capital expenses, also known as CapEx, to operational expenses called OpEx. And in a traditional data center, you have incredibly high capital costs. And the reason is you have to buy the servers, the routers, the switches, the firewalls, load balancers, racks, power, whether that be PDUs, UPSs, generators, transformers, and then there's data center cooling. And then of course there's the property or the real estate associated with it. So this is heavy duty capital expenses. And there's a reasonable amount of operational expenses with a data center, and that's realistically speaking the large staff, the electric bills from both powering the servers and cooling them, and the connectivity of the WAN. But most of the costs are actually for an organizational equipment and its capital costs, and the remaining costs are for operating the equipment. Now with the cloud, there's going to be a big shift to operational costs, and we're going to talk about that in a moment. So while with a data center, the costs are very high because there's a lot to purchase, in a cloud computing environment, there's really nothing to purchase, or almost nothing. But the organization pays for the cloud computing environment every time it's used. So this means that ongoing expenses in a cloud computing environment are going to be very expensive. Now, in most cases, the operational expenses of a cloud computing environment are still cheaper than it would be for the organization to buy the equipment, run their operating systems, meaning power, cooling, all the other things that are associated with it, and paying for the networking and the WAN connections, but not always. But understand with the cloud environment, it's going to be this operational expense because you could be paying for instances by the second, for example, and every little bit adds up. So what we're going to talk about now is how we actually manage costs to the best of our abilities in a cloud computing environment to make sure the move to the cloud is financially viable for organizations as they start using cloud computing. Keeping costs low, or at least as low as feasible, is absolutely critical for a successful cloud computing deployment. And the first step is to provision only the resources that you need. So don't provision things that you don't need. And I also want you to monitor your systems. See what's going on with the CPU, see what's going on with disk performance. Look at your systems, because you might have systems that are bigger than they need to be, or you have systems that are smaller than they need to be. So pick the optimal systems, and you're going to do this by monitoring your systems. So now that you know what your needs are, step 2 is going to be to properly size your resources. Size your equipment based upon average usage and not peak usage. In a non-cloud computing environment, you have to plan for the statistical outliers, what happens under peak conditions. But in a cloud computing environment, you don't need to do that. You can plan on whatever your normal usages are, and you can use auto-scaling to scale up as needed. Along with this, anytime you can decouple your systems and your architecture with things like SQS, you'll be in a much better position to use smaller systems that'll even scale better. So the next step is to purchase the right platform. And what I mean by that, there's going to be times where on-demand is best, times where spot instances are best, and times where reserved instances are best. But the better you know your systems and the better you're able to plan and the better you monitor them, you'll be able to make better decisions. But on-demand are going to be the most expensive, but they're perfect if you don't know the application's requirements. Spot instances are really going to be the cheapest, but they can be preempted or terminated should someone outbid you. So this may be a great way to get a lot of work done if your application can tolerate a batch job being shut off and turned back on at a later time, for example. And if you know you have an application that's going to be up and what its utilization is going to be, and it's going to be there for a long time, and you can purchase a reserved instance, you'll be able to get a discount. And if you can purchase a reserved instance for 3 years instead of 1 year, that's fantastic as well. So your cost optimization is going to be achieved by a mix of on-demand, reserved instances, and spot instances. Step 4, whenever possible, leverage managed services or serverless, because they're going to be a lot easier to maintain, and for most people, they're going to be a lot cheaper. And step 5 is really about managing data transfer cost. So if you have an S3 website that's hosted in multiple locations, you're going to pay for the inter-region transfer of your S3 data. But it might be cheaper to use S3 cross-region replication, so you can have something, say, in the US and something in, say, Asia. That might be cheaper. Use CloudFront so you can serve content locally, because that'll decrease the data transfer charges. And think about the type of, whether you want a direct connection or a VPN. Typically speaking, a VPN is cheaper, but data in and out of a VPC over a VPN can get expensive if there's a lot of it, and in some cases it may actually be cheaper to use a direct connection. So this is really about planning and understanding your applications, understanding your use, and knowing how to best plan for the future. A service that can help an organization keep to their budgetary requirements is called AWS Budgets. And AWS Budgets basically helps an organization make sure they don't overspend. And it works very simply. You create a budget in the AWS Management console or the billing console. And in that budget, you can set some custom alerts. And if the organization gets close to exceeding their threshold, their budget threshold, an alert is sent. So this can tell you that maybe you need to look into a different instance type, perhaps maybe you no longer need on-demand, maybe you need to move up to a reserved instance, but you can see what's going on with your data and it can help you plan. Now the next service that can help an organization keep their costs low is something called the Trusted Advisor. And the Trusted Advisor is a tool that helps organizations optimize their spending. And what happens is the Trusted Advisor actually will scan the organization's infrastructure, and it'll compare it to best practices, and it's going to provide recommendations. And in many cases, these recommendations can not only help an organization have a better, more available, more secure network, but they can also help an organization lower costs. Now there's 2 versions of Trusted Advisor. There's a basic and developer support plan, which has some limited advisor benefits, and organizations that have the business support plans or AWS enterprise plans get a lot more notifications and advice. But realistically speaking, these are 2 applications that can help an organization reduce their costs of the AWS cloud. Let's discuss building high availability systems. And availability refers to the service being available for use when you need it. So a high availability system means that it's highly likely that the systems are going to be available for you when you need them. Now, designing for availability, specifically high availability, can become relatively complicated and costly based upon the availability requirements. Most organizations would consider high availability to be 99.99% or greater, which is referred to as 4 nines. Now, some organizations are going to need much more availability than that. For example, a service provider, a bank, or a healthcare organization for which if their network or their systems went down, then someone could die if they're dependent upon technology. So you're going to design your systems based upon that. Now, a 4 nines available network, meaning 99.99% of the time, will have about 52 minutes of downtime, more specifically 52.6 minutes. Now, organizations that meet 5 nines or better will have, meaning 99.999% of the time, will be limited to basically 5.25 minutes of downtime per year. Now, building high availability networks like this takes a lot of work. It takes work with change management. It means no single points of failure. It means security. And we're going to talk a lot about how to build these systems. The first tenet of building a high availability system is you can't have any single points of failure. And that means redundant power, redundant cooling, redundant network connections, redundant routers, redundant switches, load balancers, firewalls, DNS systems, storage. Even your applications have to be redundant. So this is what we refer to as a high availability system. But when I said no single points of failure, that may mean that you need multiple availability zones, and that'll get you to 4 nines availability. But if you need truly high availability, meaning 99.999% or greater, you may have to use multiple availability zones and multiple regions as well. So you can always build a high availability system, but the architecture can get very expensive. So you need to know what your availability requirements are and how to get there. Now it's going to be much easier to build a high availability system on the cloud computing environment than it would be in a traditional data center. And here's the reason. AWS maintains redundant power. They've got redundant cooling in their data center. They have redundant connections to both the internet and across their backbone. They've got redundant routers and switches. So it's going to be much easier to do this with AWS. Plus, they also have a highly skilled staff that can maintain the underlying infrastructure. And they also have a change management process to make sure that changes are made in a time that will have less effects on others. So let's talk about some best practices when designing your high availability systems. Multi-AZ. So since every availability zone is effectively a data center, you're going to want to use multi-AZ anytime you even want to talk about high availability, specifically 99.99% of the time or greater. Now, if you need greater than that, greater than the 4 nines availability, you need to get into that 5 nines range, which is about 5 minutes of downtime each year, like we described, you're going to have to use multi-region and multi-availability zone. So anything that needs high availability, you have to just think redundant. So if you've got EC2 compute instances, they're going to be in multiple AZs. If you've got databases, multi-AZs. Load balancers, multi-AZs. Route 53, same thing. And if you need to get to that 5 nines or greater, you're going to even have to do some of these things in multiple regions. So we're talking about multiple network connections. And this means if you're connecting to the AWS cloud, their network is redundant. But if you're going to connect to them, you're going to need at least a primary connection and a backup connection. So for most organizations, that's going to look like a direct connection and a VPN backup. But some organizations have critical bandwidth requirements, and they may have multiple direct connections to meet their bandwidth requirements. But guess what? When you have multiple direct connections, if one of them goes, you still have multiple backups. So the point being is you're going to have redundant connectivity, whether it be a single direct connection and a VPN backup, multiple direct connections and a VPN backup, you're always going to have some form of backup. Now, if you had a VPN as your primary thing, you can conceivably have 2 internet service providers and 2 VPNs set up. But it goes back to that adage that 1 is none and 2 is 1. So you never want to have a single point of failure. And anything that matters, you're going to need to have redundancy. So 1 is never enough. Now let's discuss some other critical elements that go into building a high availability system. And one is security. If your systems are compromised, your systems will not be available. So let's review a few concepts. We want you to use the principle of least privilege, meaning grant only the minimum access necessary for people to do their jobs. On any of your systems, disable unnecessary services. Unnecessary services could be used against you to help a hacker gain access to your system. We talk about using AWS organizations to limit the blast radius should something go wrong. And you want to keep unwanted traffic out with firewalls, with network ACLs and security groups. Use Amazon WAF, use as a firewall, use AWS Shield for DDoS protection, use IDS, IPS for intrusion detection and prevention. Make sure the access of your router that connects to the AWS data center is secured in a locked environment so no one can gain access to that, because if they can gain access to your network, they can hack you. If and when passwords are required, make sure you're using strong passwords and template known good configurations with CloudFormation templates so you can build things that you know work. Now, an organization's data in many cases is its lifeblood. So backup, backup, backup. And consistent backups will protect against lost data. But create images of your production servers. And that way that if your data is lost and your servers are lost, you have access to your data and your servers, you can relaunch them in another region should need be, another availability zone, or whatever you need to, but you can do it quickly. And backups should be stored in at least one alternative and secure location. It's no good to secure backups in a building, and if the building catches fire, you lose your backups. Another way you can add security is by using auto scaling. And this is about performance, because look at it this way. If you have a distributed denial of service attack and they're trying to take your system offline, and the CPU is 80%, but it can scale up to 10 more instances, it's going to be really hard to take all those systems down where it would be much easier to take one down. And anytime you can decouple your application architectures, you're going to have better performance, and it's also going to protect you. caching can do wonderful things to improve performance. It can do this because it's going to offload your systems. So not only will less requests go to the systems, which will make the CPU lower, but caching can also help prevent adverse security incidents like a DDoS attack. DNS, this gives you great options to optimize system performance, but it also can use things like health checks to make sure that it can improve the availability of your system by only allowing servers and services that are functioning to be available for use and remove everything else from the rotation. And the same goes with load balancers. If you're going to have 10 web servers, you're going to need something to balance that load, and the load balancer is the ideal way to do it. Now, part of a high availability system is monitoring your systems. So you want to monitor them for system health, but you also want to make sure they're able to meet up with demands. So use logging functions from CloudWatch and use auditing functions from CloudTrail. And really look for system alerts. And you're going to really want to monitor for security breaches, because if hackers gained access to your network and you haven't found it, they can do damage. So it's really about monitoring. Monitor for usage, monitor for performance. Know what's on your systems. Monitor them and then optimize them as necessary. Another critical component to high availability is something called change management. And what this really means is before you make any changes across an organization's systems, make sure all stakeholders are notified and that they agree. For example, you don't want to reboot a system that's in the middle of a batch job. And you also don't want to be doing a reboot of a system or a patching of a system at a time where someone else is doing something else. And if you both reboot at the same time and you cause a problem, you don't know which is which. So you have to be very careful and diligent about what's being changed, when it's changed, and how it's changed. And change management is an absolute requirement for high availability systems. But it's not just making sure everybody's there, it's finding a time. So is it 3 o'clock in the morning when the systems are most idle? When are the systems not being used? And that's the time to make changes on the system, assuming it's okay with all other key stakeholders in an organization. Now, there we've covered the key components of building a high availability system on the AWS cloud. Let's discuss passing the exam. So you've completed this class. We've given you a tremendous amount of content. One of the things to know about AWS exams is they can ask a variety of questions on pretty much any topic on the curriculum. And these questions can be a bit challenging to understand. In fact, we find the hardest part of AWS exams to actually read the questions. They can just be so wordy. And when you read the answers, there may not be a clear answer that's the best one, especially if you've been around in tech for a long period of time, because they may give you 4 options, and of the 4 options, 3 may be acceptable. Now, 2 may not be the Amazon way, but they're still acceptable, and 1 may be the Amazon way. So don't overthink these questions, select the best answer. So our recommendations are to really go through this at least once and go back to any sections that you find challenging. Now, we also want you to read the AWS white papers that are there. And the reason we recommend reading the AWS white papers is not only can it give you some additional knowledge, but it's in AWS's words. And we find that AWS often pulls test questions directly out of white papers. So now that you understand all of the tech that's involved, reading the white papers are not only going to be easy to read, but we think you can get some additional questions answered on the exam, as well as deepen your knowledge. Now, we love and hate practice tests. We find that people that use practice tests as a means to study don't understand the content much at all. And I can tell you, in years of interviewing technology professionals, I can tell you someone who passed with a practice test, because they have lots of certifications. And when I ask them what they know and I ask them any questions on it and say, describe this to me, they can't. Whereas people that read, people that take video courses like this will truly understand the technology. Now, I told you that we hate practice tests as a means to learn, but we love practice tests as a means to prep for the exam. So our recommendation is, prior to the exam, find a practice test. It doesn't matter which one it is, just something with a lot of questions. And really what you're doing is we want to take the knowledge that you have from finishing this course and get used to reading questions the way AWS would write them, because they're going to be complicated, they're going to be tricky, they're going to be hard to read. And at least if you get used to the way they would ask a question by a practice exam, it's a great way to ensure your success on the exam. We wouldn't want you to study this way, but since you've already completed this program and we know you have good knowledge, this is just a way to make sure you can do better. So we recommend taking a practice exam, and when you can consistently score 95% or better, go take the exam. These exams are expensive, and we want to make sure you're going to be successful. Now, One of the hardest parts of these exams is really reading these questions. They can be written in a very tricky manner. So the day before the exam, get a good night's sleep, eat well, and avoid any kind of alcohol or anything that could affect with your thinking. And on the day of the test, arrive early. And if it's online, still arrive early. I've taken exams and I've had to wait 30 minutes due to some technology challenges. And at least if you're there early, when you deal with some computing challenges, whether they be at a facility or your own house, and you will run into them, at least you have time to do it. You don't want to worry about losing time on your exam. And remember, have a valid photo ID with you for the exam. You'd hate to study, you'd hate to prep, you'd hate to do everything and then show up and not have a valid photo ID and not be allowed to take the test. Thank you so much for taking this course. We love our students. We'd love you to reach out to us and tell us about your success. And we look forward to seeing you in the next class. Wonderful luck in your career, and we hope to see you soon in another program.